So good morning, everyone. Good morning to all. I, Rohit Sharma, warm welcomes you all on the third day of Nano Era, Nanotechnology for Global Sustainability. This session is coordinated by Dr. Robin Kumar. So let us start this blooming informative session about the nanotechnology in electronics and energy sector. We are honored to have Dr. Ajit Mohapatra with us. After receiving his PhD degree in physics from School of Physics, Physical Sciences at Jawaharlal Nehru University, India. He has pursued postdoctoral research at many places such as Brick Nanotechnology Center from Broad University, USA, Department of Physics, Cyprus University, USA, and also worked at Nano Center in the Cornell University, USA. He has several publications in peer-reviewed journals and conference proceedings. He has also co-considered as a guest editor in different research journals, and he has actively taken responsibility as roles in organizing various international conferences at University of Delhi. Currently, Dr. Mahapatra is affiliated as Associate Professor in the Department of Physics and Astrophysics at University of Delhi. His research interests including the understanding the basic physics and material concepts of nanostructures and applying this in-depth knowledge of science and nanotechnology for the next generation technology and application. The title of his talk is Utilization of Nanotechnology in Nanoelectronics, Biosensor and Thermoelectrics. Let us invite Dr. Mahapatra with a warm welcome to enlighten us with this topic. Sir, I humbly request you to confine your talk to 45 to 50 minutes, followed by 10 to 15 minutes for question answer session. So platform is yours, sir. Please kindly share your presentation with us.
Thank you, Rohit, for the introduction. Can you see the slides? Yes, sir. And first of all, I would like to thank the organizing committee of Nano Era in MIT University to give this kind of platform to present the knowledge what I have acquired during the period of time, and also what is the research going on in the advanced sector to the students online at this moment. So today I'll be focusing on how we use the nanotechnology for different applications of nanoelectronics, biosensors, and thermoelectrics in various fields. So basically, this nanotechnology came in just 2 decades ago. I'll go through the little bit history of that, and then since it is a workshop, I will probably go through some basics of nanotechnology and how we deal with physics and engineering. Then I'll give you some examples like what we do for electronics, biosensors, and thermoelectrics. So if you see the evolution of life, why actually we are doing it, everybody in this world,
Sir,
yes.
Your slide is not visible. Can you reshare the slide? Yeah, now it's fine.
Okay, I'm sorry for that.
Yes, it's fine. Just go to the presentation mode and then. Yeah, thank you.
Okay, so right. So the topic is utilization of nanotechnology in the nanoelectronics, biosensor, and thermoelectrics. So if you see the evolution of life, how we evolve with time, and during that in the history of humans, if you see at every point of time, what we are looking for is to having a life that is healthy and safe to survive, and we can survive with each. So that is the basic concept of basically life. Okay, so if you see the basic advancement in how science and technology is basically this is
Just double click on the slide. Probably it will move.
So
Lalit ji, IT support.
Yes, sir.
Slide is not moving.
I think the double click is working. I got it.
Okay. Center पे click कीजिए, sir. Center.
Huh?
You just click on the center and then it probably will move.
Okay, so here basically in the evolution of life, what humans are generally the only species in the nature that they try to progress the science and engineering so that they can utilize the current technology to live little bit happily and to deal with all kind of issues that they are going to face. So what exactly how they live? They so if you see the history, basically in the first when we started living in the earlier days in 1800s century and 1700th century, first the textiles, then the railroads we developed, then the automobile came, then the computer came in the 20th century at the end, and now we are basically in a situation where we are trying to use the computer fully, and also we try to learn the nanotechnology by now. So what is the, if you extrapolate the same curve, what we think is that by the end of this, by the end of like after 2050 or 2080, there basically we can use the nanotechnology fully. So still we are not using the nanotechnology to the full extent. What we are doing with the concept, when we grow, we try to understand the nature, how basically we live, and what exactly we are, and what are the things inside us, that we understand ourselves and the nature in a much closer way to live a healthy and safe in the life. So first we will see that why we deal with, now we are like always in the life, we try to overcome the limitations of whatever we are having the capabilities, and to achieve it, we implement all our scientific understanding in the technology development with appropriate engineering. So the thing is that first we have to understand scientifically, and we have to use the available technique to develop more technologies by using the current engineering. So what exactly this is, I will go through it. So if you see the last 50 years, the advancement of technology, if you see, we are now using the electronic and sensing devices, which are generally made up of solid state electronics, and that those are used by they use inorganic materials as active elements. But if you also, we are now using some organic optoelectronics using that utilizes conjugated molecules. So currently, we are trying to use the technology available to fabricate and characterize different materials and devices utilizing nanostructure material whose dimensions are basically 1 micrometer to 10 to 100 nanometers. So here basically what are the materials? The materials we are dealing with are the graphene, nanowires, quantum dots, organic biomolecules, and carbon nanotubes, nanoparticles. All these are the nano materials that we are using to fabricate devices. So to before that, first we need to see uh, how these structures look like, and then we utilize them in the electronics, chemical, and biosensing platform. So basically, how we are doing it, that we'll see. So if you see the development of this miniaturization or the electronics, everything started back in 1947 after the development of transistors at Bell Labs. There, the size of that transistor was 2.5 centimeter. But if you see the with time, the size of the one transistor basically reduced with time, and it reduced with time. And also simultaneously, we started to develop a technique where you can use multiple transistor in one chip, call it the chip, and multiple transistor in one chip, so that they can work together to enhance the capability of the technology. So currently we are using in a chip probably 10 to the power 15 transistor in a chip, which is having 1 square inch dimension. And our theme at this moment is to scaling down the device dimension to improve the performance, to reduce the power consumption, and also to reduce the cost per element. So this is how we are uh, uh, progressing towards the development of various techniques. Now, if you see, the term nanotechnology is basically came just 20 years ago. Like in the end of the 20th century, we got all are jumping into the nanotechnology, and before that, people were not aware of that. But if you see different branches of science and technology, you see that the chemistry people are always working with the molecules and the concept of the molecules, preparing new molecules and properties of the atoms. So whatever they study, they are always from 100 years, they are doing the or dealing with the material which are in the nanometer range. And if you see a little bit more, the biology people, the medical science, they are searching something which are inside the blood. They know what exactly is going on inside your body, physical body. So there basically we are dealing with some cells. So those cell structures are 1 micrometer, but if you go to the organelles of the cells, the dimension is always less than 100 nanometer. So the people which are working in the medical field, they are also in the they are dealing with the materials and nanometer scale from ages. But in last 20, 30 years, the term came because the engineering and the physicists, they came together so that they can access the materials, those are of dimensions in the nanometer range. So in science, what you see, what you believe. So that is the deal. So when we developed the scanning tunnel microscope, when we developed the electron microscopy, where we can see the structures at nanometer scale, then we believed that we can manage, we can fabricate, we can engineer various kind of devices or studies at nanometer scale. So during that time, it is not the chemistry, not the biology, not the physics or engineering. Everybody came and made a complex structuring system that where they can collaborate each other and also they can understand the language of each other. There basically we started a new era which is called the nanotechnology, that we are dealing with all the materials, all the elements which are at the nanometer scale. And from that, we started this journey of developing new technology using nanometer scale materials we call the nanotechnology. And the basic thing is that if you see the basic life, the utilization, first in the transistor is an electronic element, and using that now we are using all these computers, cell phones, all these electronic equipment we developed using different kind of electronic elements. And similarly, if you see the mobile phone was not there like 50 years ago. So with time, we try to build up and we try to reduce the size of all the electronic equipments by reducing the dimension of all the elements present inside that. Also, if you increase the number of elements inside, then you can improve the quality of the equipment and also the effectiveness of the equipment. So that's how we are trying to put more number of transistors, more number of electronics inside a particular device so that we can use in a multidimensional systems. Okay, now in the sensors, same thing. You can take one material and if you see in the environment, all the gas molecules, all the chemicals, those are all molecules. So your body is also a chemical. So if you see, water is also a chemical inside the chemistry lab. So the thing is that when they get together, they do reactions. So by finding the reactions between the known and unknown version, you can diagnose the unknown particle, and also we can study more about the unknown particles. So we sense the unknown molecules and we call it the sensors of a particular kind. And depending on the functional group, all those things, we can make various kinds of nano sensors. And you can use it in the healthcare diagnosis and as a medical devices. So to realize all these things, what you need to do first is that we have to develop or create new materials using the known elements. So in the periodic table, whatever the elements are there, first you need to develop different kind of materials and alloys, and we can then characterize those materials, new materials and alloys, so that we have to find out what is the good quality about a particular material. Now, once you know the good quality of the material, what is good, what is bad, who will decide that when the material is exposed to any kind of energy, what kind of changes it gives in their signal. Like if you have a material and you develop some kind of nanostructured material using a particular element, then if let's say we out of these all these nanostructures, we have nanowires and carbon nanotubes, organic molecules, graphenes. You let's say you develop some nanowires, and first you have to characterize them and see what it is made up of, what is the constituents are, how it looks like. And after exposing this material to any kind of external energy, the external energy can be anything, like your electric field. You can you can expose them to the light, you can expose them to heat. So all kind of energy or magnetic field, this kind of energy, when you expose the material, then what kind of changes you get in the same kind of signal. So if you expose to the electric field, how the current is changing. If you are exposing to magnetic field, how the magnetization is changing. You are exposing to heat, then what kind of other spectroscopic things you can change. So looking at all kind of signals and change in signals after exposing to different energies, you can say the effectiveness of the material to that particular energy. And by using that enhancing properties, you can make whether it magnetic devices, electronic devices, surface functional kind of sensor devices, those kind of devices, then you can think of depending on the characteristics of a particular material and the nanostructure. So to use a particular nanostructure into the devices, what you need to do, you can fabricate the device at the same scale of the material each. So if the nanostructure is of 10 nanometer length and you need to pass electricity, then you have to make 2 electrodes at least, so that you can make a electronic circuiting using that particular nanostructure. So first thing is that to develop these new materials. Second thing is that making nanomaterial devices using device fabrication technology, and in the engineering, the lithography techniques, etching techniques, and all these top up and bottoms up, top down and bottoms up techniques are available, so that we can deal with the range from 1 nanometer to 100 nanometer for a nanostructure system that contains both the nanostructure materials and the electrical contacts or the electrical probes you need to make. So now the engineering is available, and the technology is allowing us to access and to fabricate devices at 1 nanometer to 100 nanometer range, and see how the physical changes and chemical changes is occurring, and depending on that, how we can capture the signals and to study whether it is good for electronics or sensing properties or various kind of other things. So if you see how to realize these nanostructure materials, we can realize them to go into the 1 nanometer to 100 nanometer, generally we use some either physical techniques or some chemical techniques. So first, I will say how this nanostructure we are making using various techniques. The first thing is that you have to prepare the nanostructure materials using different elements. So then the periodic table. So various physical techniques and chemical techniques are available. I'm not going through all this. You can send me offline sometime if you need to ask me any questions about this one. And also we use various kind of lithography techniques to develop various kind of device structures. Means these techniques are used to make different kind of contacts directly onto these nanostructure materials. So depending on the dimension of the material structure, you can use various techniques. Like if you are going for the photolithography, we are using the photons or the UV lights as the exposure. And here, depending on the wavelength of the exposure system, we can go up to 500 to 100 nanometer, means up to 0.5 to 1 micrometer range. If your materials are, then we can go to up to that level. And if you want to really go to the 10 nanometer scale, then we have to use the electron beam lithography, where we can fix the feature sizes into very smaller scale. And also today's date, we have X-ray based lithography and fixed ion beam lithographies, where we can go up to 10 nanometer and we can fabricate the devices, or we can engineer the devices. Now, after making all the devices, what are the things we first need to do? Let's say we expose this, we have to expose the material into various kind of energies. Now, let's say with the nanoelectronics, what we do? With nanoelectronics, we study the electronic properties. That means we have understood that whatever the material is, it is based from some elements in the periodic table, and those materials contains electrons. So when there contains electrons, if we can apply some electric field, these electronic charges, they try to flow through the electric field. Now, by deliberately, if you apply some extra field, and after that, if you can understand how the electronics and electrons are moving inside the material, then you can see whether it is good conductor or bad conductor, and what are the other different kinds of properties is basically the material is having. So what do you do? What you take the material and just make two contacts, two metal contacts, and then you try to apply the voltage. That is the minimum thing to understand the electronic transport of the electrons from one material to other metal contact through this material. So here basically we know the current flowing in the circuit is always defined as the charge flow per unit time, and Q, where Q is the total charge. So here basically what is the deal? If you take any kind of material, what we understood is that when you flow this, the electrons are coming from the one material side to the metal side to the material, and then it exits from the material to the metal and the other contact, and then it flows to the circuit. So we have two kinds of currents. One is ball current, means where the electrons are basically how the electrons are flowing inside the material, and how the electrons are behaving when there is a contact from metal to material. So these are the deal. So we see this current flow inside the circuit. And then what we do, when you apply some electric field, then whatever the electronic structures are, you are implementing some potential difference, and during that time how the electrons are moving from metal to material and material to metal, depending on that how many number of electronic states you are accessing, depending on that you can have the current flow into the system. And depending on the dimensionality of the material. If it is three-dimensional, two-dimensional, one-dimensional, and zero-dimensional, in there you have different kinds of density of states, how the energy states are distributed, and depending on that, you can access how many number of electronic states, and depending on that, you can measure the currents and how it is depending. Okay, if you see how the resistance is changing from a lower dimension, if you go from 3 dimension, 2 dimension, those dimensions, then if you see define R is the resistance is equal to length divided by area times the resistivity, which is 1 by conductivity. Then if you reduce the dimensionality, that means if you take a 3-dimensional system and chop it off into very little bit slices whose thickness is less than the characteristic transport length, then basically in that direction your electrons are constrained. So electrons are freely moving in 2 dimensions. That's why we called it a 2 dimension. When the classically electrons are moving in 2 dimension, and when you again slice down to the 2-dimensional sheet into making this 1-dimensional lines, there means in one direction electrons are flowing classically, and the other sides you have the quantum mechanical things going on. That's why you call it a 1-dimensional system. Now again, if you restrict the electron flow in the other side, you can say it is a nanodot, or you are studying in the quantum mechanics, it is particle in a box. So the resistance and the dimensionality of the resistance is also varying depending on the dimension of the material. I've heard because if you take 3-dimensional, the current flow you are defining dq by dt at a particular surface area. So the surface area is the transverse section through which electrons are flowing is area. So you call that as the area. But if you take 2-dimension, the cross-sectional area is just like 1-dimensional in 1-dimensional wire kind of thing. And then if you go to the 1-dimensional wire and flow the current, then the density, the ND, the number density of electron density, you can say that the number of electrons per unit length. So depending on the definition of the electron flow, you are defining all these of dimensionality. And if you go to the really low dimensional system, there basically we are going from a diffusive system to ballistic system, where there is no collision between the electrons taking place after applying the electric field. So you can calculate the resistances by using the Landau formula, and the total resistance is the contact resistance plus the resistance of the material, where there is, if it is ballistic and there is no collision, there is no resistance, but the only resistance is coming from the contact. So those are the little bit things. So of the low dimensional systems and physics of the low dimensional systems for electronics. So today, as an example, I'll include a few of our research works of titanium oxide nanowires, and using graphene oxide and this calcium cobalt oxide are the different materials that we have used to see what is good characteristics, or what are the materials are good for, and then we have tried to use these materials in different kind of actions, and in different kind of electronics, sensors, and thermoelectrics. So here is the first kind of nanostructures that we have prepared. It's gallium antimonide, and it is prepared that we basically bombard this with argon ions irradiated at low energy of 100 keV, and we have seen that if you increase the number of doses for, or you can say you can optimize the parameter of irradiation to get nanofibrous kind of thing on the surface. So once you prepare this kind of nano, you can say mesoporous systems, you can see that you can increase the surface area by much if you take only a plain area, plain surface, and you can prepare a surface of this kind, then the surface area of these structures are much more. Then this surface will be much better, a much better surface for detection and for sensing purposes. So if you go and irradiate with a very high energy particles, then these nanoporous structures are preparing nanodots. So this is a kind of thing like how the nanostructures are nanostructure materials are prepared using various techniques. And here is a nanowires that we prepared using hydrothermal methods, and various kinds of nanostructure materials you can prepare, starting from the nanowires to nanopencil to nanoflower, by varying the chemical recipe and the parameters. So you can optimize a particular recipe, and you can prepare different kind of nanostructures. And these are the characterization of all those nanoparticles, nanowires. So I'm not going through it. You can see the papers. Now, once you prepare the nanostructures, what else to be done? After preparing these nanostructures, the other thing, the second thing is that how to make a device. So for the particular device, what you need at least two contacts if you are thinking of preparing an electronic element, so that you can apply the electric field. One is negative terminal, one is positive terminal. So these nanowires, titanium oxide nanowires, we are preparing on a FTF substrates, and the nanowires are vertically standing upwards. Now, if you want to prepare another contact on top of the nanostructure, what will happen is that generally in the thermal deposition techniques, we are keeping the substrate normal to the surface. The source from which we are depositing, those are 90 degrees onto the surface. So if you use a traditional thermal deposition or any kind of deposition system, then you cannot prepare a top contact which is isolated and separated on the top. So what will happen? They will deposit inside the gap region also, and you can end up with particulars making a short circuiting if you want to prepare a top contact on top of this nanostructure. So what engineering wise we have developed is that instead of taking one particular source, if you can take two different sources at an angle to each other and deposit simultaneously, then the shadow of one nano wire will fall onto the other, and it will not go, it will not impinge inside the nanowires, and it will not make any short circuiting, and you can get a floating layer on top of the nanowires. So for that, we did some mathematics and calculated what would be the dimension, or what would be the distance of the substrate with respect to the sources, so that you will get at least 10 to 20% of the nanowires covered with the metals without impinging inside or without making the short circuiting. So after this calculation, you can also do it by taking this one. We can calculate what is the distance, and then we have prepared that a floating layer on top of these nanostructures. So the material characterization also shows the surfaces which are floating on the nanowires, and some developed means applied some electric field and have seen what are the different kind of IV characteristics and electronic conduction is taking place, and all these are at the research stage. So in engineering wise, we have now successful and got the data for electronic conduction data, and the next step is trying to understand the techniques. The other thing is that we have taken this graphene, and graphene oxides are really important materials nowadays, and always in the talk. And in the graphene, basically, it is a atomically flat monolayer of carbon atoms, and it is packed with the two-dimensional carbons only. And if you see the graphene oxide, what happens? just if you put some any kind of oxygen functional group onto the graphene structure, then automatically this one carbon chain breaks down and some functional groups is there. So you can see some of the oxygen functional groups floating around the graphene backbone. So that is your graphene oxide. So if you see the FESM of and the TEM image of graphene and graphene oxide, you can see in graphene you have like crystallographic properties, but in graphene oxide you can see because of the rupturing, the network is totally amorphous like. That's why you are not getting the crystalline property, but the amorphous property of this one. And in the same SEM image, if you see the graphene sheets are generally very flat, but the wrinkles we observe in graphene oxide films. So after getting into graphene oxide, we make this graphene oxide on top of a particular substrate, ITO substrate, so that the ITO can be used as one electrode for electronic transport. And then we go for different kind of annealing processes so that you can have different, you can expose the graphene oxide into different materials so that you can take out some of the oxygen functional groups from the carbon backbone itself and make it more into the reduced graphene oxide and see how the electronic conduction is taking place. So you can see like from room temperature preparation, if you increase more and more the reduced graphene property and amorphous nature of the property is really going high because the effects are basically more and more. The crystalline property is going up because of the more number of oxygen functional groups they are detaching from the surface. And what we have seen is that if you take a particular graphene oxide thin film over FTO and prepare some aluminum contact onto that, there basically we have seen the bipolar transition properties. So to see this one, we have taken this graphene oxide and prepare, and all these electronic conduction properties are observed in the Faraday cage, so that to reduce the electromagnetic wave interactions into the to the graphene oxide thin film. There, what you see is that if you increase the voltage from 0 to higher bias and without stopping the or without detaching the electric field, if you coming down, and then what happens is that first the graphene oxide is basically giving very high current, and then after some time there is a transition or the reduction in the conduction, its conductivity is taking place, and that continues even if you come down or if you reduce the voltage towards zero. But in the same cycle, if you go to the other side, means if you apply the negative side of the electric field, again this low conduction state is jumping to a very high conduction state in the negative side of the electric field. And this is basically a continuous flow. If you make the cycle one by one, then automatically this kind of transitions are occurring at a particular threshold voltages. So the shadowed portions are the transition temperatures where basically the graphene oxide layer is transiting from a higher conductivity state to lower conductive state in the positive bias region, and in the negative bias region it is getting repaired when you are applying the negative electric field. And what we have seen is that if you anneal the graphene oxide layers which are annealed around 200 degrees centigrade are giving much more difference in the conductivity, means the low conductance state and the high conductance state. This ratio is basically very high when you anneal the graphene oxide at 200 degrees centigrade. So this is the log plots. We see that that there is a transition in the three order of difference. So, and also in the when you increase the temperature, basically the oxygen functional groups are decreasing because the OH functional groups will evaporate. So the oxygen functional group increasing. So the C by O ratio is basically increasing by increasing the temperature. And also it has been seen in the XPS, HPS. So why this is happening? This when you are basically preparing this aluminum contact on top of graphene oxide, what happens? Graphene oxide is automatically a porous structure, atomically porous structure. So these aluminum atoms are basically infusing inside those defects and making this kind of aluminum filaments into the structure. So when you first applying the voltage, you get the electronic conduction through the aluminum filament, and you get the ohmic property and very high in conductivity. But when you apply more current, what happens is that the electrical conductivity, the Joule effect, heating effect, is in addition to the Peltier effect at the contacts of the heterogeneous materials. There basically there is a breaking in the breaking taking place, and at that junction the filament breaks down. So you are losing contact between the positive and negative terminal through these material wires, and that's why you are basically reducing the conduction process. But if you apply the negative electric field in the same cycle, what happens? The again the atoms which are little bit left over of these aluminum atoms on ITO, when they break, due to electromigration, they get the repairing, and then again they bridge the circuit and get the get into the higher current in the fourth cycle. That means into the negative cycle of the voltage. So that's how basically the breaking and again making of this aluminum filament is responsible for this kind of switching, and this occurs only in the aluminum contact or not in the other contacts. So also this graphene and graphene oxide can be functionalized with various organic and bio molecules, so that the functional groups or active functional groups on the graphene oxide can be increased, and so that we can use those things into our collecting more sensing or the signals, so we can use the sensors and for other electronic events. So also this graphene oxide we have used for detection of this triglyceride, and here basically there are chemical routes to go through. I'm not going to all this chemical process. So yes, we can sense the or we can detect the triglycerides on the FTO surfaces, and the graphene oxide here we are prepared by the CV techniques, cyclic voltammogram, and then right. And using the cyclic voltammogram, we can see the current, how it flows just for when you are ITO, when this graphene oxide is deposited onto the FTO, and then a linker lipase is acting, and this lipase is basically can attract those or detect the triglycerides. So that's how we work. Since it is okay, the time is very reduced. Okay, so the other materials that we are trying here is that we are preparing various kind of calcium cobalt oxide based material or powders, only calcium cobalt oxide, also graphene oxide mixed calcium cobalt oxides, all these particles, and we are preparing those are the powders or the materials for utilized for thermoelectric purposes. Thermoelectricity means when you expose this material onto the temperature, high temperature, it produces electricity. So that is the thermal effect into the to develop this electric current. So that is basically thermoelectricity. There basically these materials, calcium cobalt oxides, are much more better or showing good properties in thermoelectrics. So we are using this as a base material and mixing with graphene oxide and other kind of material to prepare that. But the only thing is that here the powders are, you can prepare the powder, but you have to have 100% dense material so that there will not be any scattering processes or inside. So to reduce that one thermal conductivity, there basically we use 100% dense, and there we can hot press the powders to make near equivalent like 100% relative density, so that there will not be any gap between the nanostructures or the materials and highly dense fake materials. Then you can use that in the thermoelectricity. So by hot pressing, we do that. And here are some, again, first you have to see the electronic properties, then also the thermal properties, and you can mix them to see how the thermoelectric property is defined. And what we have seen is that we have observed significant enhancement of the thermoelectric power factor when you use the nanostructure calcium cobalt oxide instead of bulk calcium cobalt oxide. So, okay. So here basically a 10 times increase in power factor is observed when you prepare these calcium cobalt oxide ceramics instead of like bulk materials. And so what are the research activities going on in our we are studying the bipolar switching in graphene oxide and any other oxide materials. And then we are developing biosensors using this graphene oxide and functional graphene oxide by putting various kind of molecules onto it. And we have developed few materials for thermoelectrics and preparing metal oxide nanowires for that can be utilized for nanoelectronics, and nanoporous structure we are preparing for nanosensor background. Also recently we have started this magnetic hyperthermia, where we are preparing the magnetic nanoparticles and sending them inside the cell, and depending on the toxicity, we have to optimize the toxicity of the material, and you can say which particular magnetic material or nanostructures can be sent into the cell. And after that, if you apply the magnetic field, then automatically the local heating at the place will can kill the cancerous cells. So that is the magnetic hyperthermia, is that after applying the magnetic field, it generates heat. So if the magnetic particles somehow can send into the effective cells and then apply the magnetic field, local heat will generate and the effective cells will be can be damaged. And that's how, that is the concept of magnetic hyperthermia we are using. And I would like to acknowledge all the facilities that we have used at central facilities at UC Delhi University, Department of Physics. And then also we have used Institute of Nanotechnology in MIT University. One of my co-student was there. And we are using National Physical Laboratory facilities and the facility at Jawaharlal Nehru University to characterize and study all kind of physics and engineering things. And the workforce behind all this work I have presented are like Pooja Saini, Satish Kumar, Sheetal Lishar, Nidhi Puri, Rajkumar Gupta, my students, and Manjari SP Singh students, and Sheetal Bhardwaj is MED, and I was the co-guide. Professor Tinku Bas was the guide from that side. And we collaborate with different people. Professor R.P. Tandon is in Delhi University, SP Singh from NPL, Professor Tinku Basu in the MIT University, Professor S. Ghosh from JNU, and Dr. P. Misra from SSPL. And I would like to thank all my the funding agencies I got from Delhi University, UGC, DRDO, and RTS. Thank you. And Stay home, stay safe, explore the nanotechnology.
Thank you, Professor, for the excellent and informative talk. Is there any question from the panelist side?
Uh, Thank you, Dr. Mahapatru, for such an extensive talk. And the initial slides were so beautifully explaining the era. I really loved it. Thank you so much. I'm sure especially the research scholars and students must have enjoyed. A quick question on the magnetic nanomaterials. Which material you've been synthesizing for this hypothermia treatment?
Oh, this is like iron oxide, but a little bit
It's
into
pure only. Okay,
yeah.
mixed with. And are you like how you've been testing that in so far?
Right.
Like it
So we
started right now?
have like SARS experiment. We have SARS specific absorption rate we can measure. So I have this instrument where you can apply magnetic field with different frequencies and different magnitudes, and you take that magnetic particles in a solution form, put the test tube inside it, and apply this magnetic field and strength and you can say frequency, and see the how the temperature is changing by putting a thermometer over that.
Right.
So that is a nanotherm, you can say. So magnotherm. So that instrument is there with me, and I'm checking it. And after
That's good.
making this, yeah, after so that is the deal. You have to apply the magnetic field and see how much temperature change is occurring, so that generally inside our cell we have like 38 degrees centigrade. But
Right.
if you
Not
can,
beyond 42. Otherwise, I mean,
yes,
beyond 42 cells will.
excellent. So that is the optimization that you need to do. Or you need to find out what is the strength of the magnetic field and the frequency you need to apply, so that if the magnetic particle, what has been sent, that can increase only this delta T, which will go from 38 to 42, not more than that. So you have to optimize it by changing concentration of the magnetic particle inside the solution, and that is different for different kind of material depending on the magnetization, because when you apply the magnetic field again, this cycle, magnetic AC cycle, then there is a contraction and rarefaction. Because of that, this heat is getting generated. So yes, you have to measure that delta T using magnetron machine, and you can go for that. And also we have collaboration with genomics in XR and AIMS also. Indrajit Roy is also our partner on that. So we are basically doing all these things.
Yeah.
Trying to learn is a very new thing for us.
Thank you so much. We would like to hear from you again.
Sure, anytime.
Any other question from panelist side? Okay, then we have one question from the attendees. Could nanomaterials extend the Moore's curve? Could nanomaterials extend the Moore's curve? Moore curve.
Also, Moore's curve. Oh, I see. Well, it is time to tell. We cannot tell. Probably after Moore, there will be another law will come after 10 days. We never know. But yes, so far it is going. So probably Moore's curve will follow, or something else curve will add up onto the Moore's curve, modified Moore's curve. So you have to wait for the time and watch.
Okay. So I request all the attendees, if you have any question, then kindly put your
Dr.
answers into the
Ravi
chat box.
Kumar, there is a question in the question and answer section also.
I cannot see.
I cannot see, ma'am.
Could I read, ma'am?
Okay, I will read it out. Student wants to know what is the prospect of using aluminum nanowires before you could characterize and know how they would act. Dr.
Before characterization, you need, first you need to characterize, and the characterization process, what I have shown you, is that after making this aluminum contact, we have taken the transverse section TEM and see the aluminum filaments inside through the transverse section of the thin film. And also we have taken the XRD of those nanowires, and what we observed is that is exactly matching with the aluminum 111. So, and after that, we have taken the temperature dependence IV curves where the resistivity, the temperature coefficient is basically exactly matching with that of aluminum. So we have done all the cross techniques to see whether the filament is of aluminum or not. So we are sure that it is of aluminum from various kind of characterizations. So yes, that is put. I think I have shown you the TM structure. Probably I'll share you the slide again if I can pull out that. Yeah, can you see it? So this is a aluminum filament in the transport section of TM, and also this 111 of aluminum.
Dr. Mahapatra, you have to share it. It's not visible.
Oh, I'm sorry.
Yes, now visible.
Yeah, so here basically the see this is first it was like very much ohmic, and then it is reduced, and following the space limited current. So this is the first definition that it is going from a metal towards the insulator, and this insulator is remaining, and we are getting again the ohmic curve in the negative side. So it is going from a metal side to some insulator kind of thing. When the transition is occurring, that is from the IV curves, and the temperature dependent IV curve is not there. That also we have done. That is the temperature coefficient is matching with this aluminum. And from here, the TEM, you can see the aluminum filament, which is going from the top side to bottom side. This is the transfer section. And also the TEM shows the aluminum 111. So these are the characteristics that we see that filaments are formed. But after that, this kind of effect we have not observed when you take gold or gold or gold aluminum, any kind of things. If aluminum is not there, then this kind of thing is not happening, because if you take gold on the top, and this filament structure is forming. But again, when you apply the electric field, the melting temperature is so high in aluminum that it cannot break very decently, or all the nano wires which are formed, they are not basically detaching. So you are not getting a this kind of metal to very much insulator kind of transition there. If you take aluminum, you take materials other than aluminum. Also, if you take only aluminum, there are so many cross-linking from both the sides that there also we are observing all kind of properties like bipolar switching, so unipolar switching, you're switching after one cycle. So various kind of things we are observing because of the atomic filaments which are forming from to both the metal structure. So yes, we have characterized everything inside the graphene oxide structure. Also the XPS, I think I have shown here also in the XPS, we have seen the aluminum content is basically increasing. So this is a clear picture that aluminum, if you increase the depth profile and see the XPS in depth profile is showing the presence of aluminum inside the graphene oxide layer. So that is also a proof that aluminum filament is basically there inside the graphene oxide and responsible for all these kind of switching, bipolar switchings in graphene oxide.
Okay, sir, I have a question. In this angle deposition technique for contact formation, how the density and the length of the wires affect the formation of a faithful contact?
Excellent. Yes. See, the thing is that if you have to, let's say, if you have like too many trees, and when sun ray falls, if sun is at the 12 o'clock, if the sun rays can hit the ground, the same technique. So if sun is into like sunset and sunrise, the shadow of one tree can fall into the other tree. So it cannot come inside that. So the same formula, that length and the dimension of the nanowire to form the shadow effect during deposition, that is basically can be found out from this one. The which one? I'll show you how we are finding it. This is, so you need to find out the angle between this this theta 1. So if this is the source M, and if it is making theta angle, then this theta angle and this portion will be the deposited, means this is the shadowed region, and below that region the atoms which are coming from the source, it cannot come inside. So only this portion will be CD portion will be deposited when you take one source. So we are taking basically two sources simultaneously, so that the shadow effect goes one by one in the other side, and they fill the distance between that one. And this Z is the percentage, Z% that you can define, where the H, this H is the height of the source from the substrate, and then you can calculate what is the length of the nanowire L, and the S is the separation. From a little bit of you can say trigonometry calculation, you find out what exactly is this Z compared to this H and this distance D. So the distance from the substrate to the source on the vertical side and the lateral side, they decide what would be this theta, and this theta decides what is the the length and the spacing between S. Depending on that, the Z%, how much percentage of the nanowire will be deposited on the top so that it will float on the surface without impinging inside, that can be calculated by just by trigonometry, and this is the calculation on that. And first, you basically we need to like see this. This is the simulated curve. By using that formula, you first simulate and see for a particular structure of your own what is the length and the diameter that you can, and the spacing between the nanowires, you can find it from the ACM. Once you found out from the ACM, then put it into that formula and generate this curve, that what exactly should be the distance D for a particular edge, so that the Z% will be fall between the 20% of the region. So that D, the distance between the source and substrate, and height, those things you need to find out for, and that will be different for different structures, that you can find it from the ACM.
Okay, thank you, Professor. So if there is no further question, then let us thank Dr. Mahapatra for the wonderful lecture. Thank you, Professor.
Thanks a lot. Have a nice day.
Thank you, sir, for sharing such a valuable information. So moving ahead, as a gentle reminder to all the attendees, be attentive at the end of the session and complete the assessment, for which the link is provided in the chat box. The link will be activated till 7 p.m. as per IST. So moving ahead with the session, our next eminent speaker is Professor Ashish Kumar Sen. He is an associate professor. Hello. He is an associate professor in Department of Mechanical Engineering, Indian Institute of Technology, Madras. He joined IIT Madras after his PhD from USC Columbia and postdoc at the University of Southampton, UK. Dr. Sen has received several prestigious awards and fellowships in recognition of his excellent contribution to the field of microfluidics. Some awards are Swarn Jayanti Fellowship Award, NASI Scopus Young Scientist Award, Gandhian Young Technological Innovation Award, and many more. Dr. Sen's research commitment and accomplishment are centered on micro-nanoscale interfacial phenomena and lab-on-chip innovation. He has dedicated himself to understanding the behavior of interfaces in microfluidics and its application in the lab-on-chip technology. He has eminently contributed to the field of droplet microfluidics, and his contribution to the field of acoustic microfluidics is unique in the country. The title of his talk is Microfluidics-Based Lab-on-Chip Devices. To know more about microfluidics and lab-on-chip devices, we like to call Dr. Ashish K. Sen. Sir, it is humbly request you to restrict your talk to 45 to 50 minutes, followed by 10 to 15 minutes question answer. Now, platform is yours, sir. Kindly share your presentation with us.
Yeah, I have already shared. Are you able to see my slide?
Yes, sir. I'm able to see it.
So thank you for the kind introduction. Good morning, everyone. So the title of my talk is Microfluidics-based lab-on-a-chip device. So first, I would take some time to introduce microfluidics and lab-on-chip device, since I'm not sure how familiar the audience is to the field. I would go a little quicker in this section. And then I would try to cover two of the recent work that we have done. One is development of a microfluidic device for measurement of gasotransmitters, where our goal is to try to predict onset of sepsis. And then the second work on rapid detection of dengue NS1 antigen. So first, let me introduce briefly to the field of microfluidics and lab-on-chip. So as Professor Mahapatra was showing the evolution of technology, so we are already in the era of nanotechnology and this conference. So microfluidics actually originated from a larger field called MEMS, and you can visualize MEMS as the path and link between semiconductor technology and nanotechnology. So that is where my work is. So if you look at origin of microfluidics, it basically deals with devices or systems that involves fluids. And so that is why initially the field was known as fluidic MEMS, and later it got recognized as microfluidics. So if you look back, the origin of microfluidics can be traced back to 1950, when we had inkjet printing technologies coming up. And if you look at the evolution subsequently, there was this gas chromatography devices that came up around 80s that use the principle of microfluidics. And then between 1980 and 90, you have these devices, microflow sensors, balls and pumps and so on coming. And in a conference in 1989, Mans et al. Said that microfluidics will have two major applications. One is in chemistry and the other one is biology. So after that, people got interested more into microfluidics, basically looking into these two fields. And but there was a challenge in terms of developing devices, because mostly it used IC technology, which was already developed, to fabricate silicon and glass-based devices, which are expensive. But then around 2000, soft lithography was invented by George Whiteside's group, and then the field saw a rapid explosion. And soon, in last 2 decades or so, we have devices, microfluidic devices, being used for things like PCR, rapid diagnosis, single cell technology, and lately organ on chip. So there are several applications that microfluidics has seen last 2 decades, and several of them have been commercialized. So if you were to define microfluidics in a single sentence, I would define it this way. It is a technology that deals with science and engineering of devices and systems that involve miniaturized fluidic space, having length scale of the order of 1 to 1000 micron. So in microfluidics, the fluidic space is important. The fluidic space needs to be miniaturized, because as you would see in subsequent slide, there are some special effects that come up when you actually miniaturize the fluidic space. And for example, the channel length is not important. It is the cross section of a channel what is very, very important. For example, you can take a credit card size microfluidic consider liquid volume above 1 milliliter. Then other side, you have the nanofluidic devices, which would have dimensions between 1 nanometer to 1 micron. and or devices of volumes less than a femtoliter. And then in between, you have these microfluidic devices, which have dimensions going anywhere from 10 micron as the channel size to about 100 millimeter as the overall footprint of the area of the chip. And the volume could be anywhere from a picoliter to could be as high as a liter for certain applications. So if you were to call a device microfluidic device, it should satisfy at least one feature. It should have either small volume, small size, low energy consumption, or use special phenomena that appear at microscale. So typically, a microchannel will have a fluidic connection. You can have fluid in, fluid out, and then you can have external fields such as electric field, acoustic field, magnetic field, and so on. And you can also have various mechanisms for detection, for example, optical detection, electrical detection, and so on. Yeah, so talking about microfluidics, how small the fluid quantity has to be. It really depends on what we are interested to measure or detect. For example, if you look at different analytes in blood, so these are concentration of different analytes. And if you were to decide on the volume of the sample, it will really depend on what analyte you are going to detect. So for example, if you compare HIV virus to glucose, you can see that the concentration of glucose in blood is much higher compared to if you were to look at the HIV. Right, so the volume requirement really scales inversely with the concentration of the analyte. If the concentration is low, you would require much higher volume to be able to get the detectable limit. So the question is, when it is so small, what happens to continuum? So it really depends on the length scale. If you go to nanometer scale, you do not really satisfy continuum. At micro scale, the continuum is still valid for a liquid, but if it is for gas, you really do not know. It again depends on the length scale. And if you were to simulate using some numerical scheme, you have to again know, if you are in nanometer scale, you need to talk about non-continuum, where the micro and mesoscopic methods, such as either molecular dynamics simulation or lattice Boltzmann method, has to be used. If you are in micrometer scale and for liquid, the continuum is satisfied, so you can still go for solving the conventional Navier-Stokes equation and find a solution. And if you are in micrometer for gas, you, depending on the dimension, you may be going for either microscopic method where you use MDS or the LBM, the lattice Boltzmann method. You may have systems where you can have multi-scale. So you can have nanoscale, microscale coexisting. And in that case, you really need to model using multi-scale modeling. So it is very important because if you see here, the time scales are intimately related to length scale. So for example, if you are talking about quantum scale, the things happen very fast of the order of picoseconds. And if you are in, for example, in microscale, that contribute to the development of microfluidics. And fluids in microfluidics could be as simple fluids or complex fluids like DNA, cells, and so on. The advantages of microfluidics are many. You need low sample reagent. You have small physical economic footprint. You can actually parallelize things and you can automate things to get high throughput. And there are some unique physical phenomena that appear, such as flows are laminar inherently. You have very strong contribution from capillary forces and molecular diffusion at at microscale. The surface forces are dominant, the flows are laminar, the entrance effect could be dominant, and you also need to worry about continuum. Some of the unique application of microfluidics into immunoassay, droplet microfluidics, isolation and detection of rare cells such as cancer cells, stem cells, and so on. And it has lately been used into the field of organ on chip, where you build artificial organ using microfluidics technology. So these are some of the processes that you can carry out in microscale, and you can use various kinds of energy, external energy like electric field, sound field, magnetic field, and optical fields for actuation. And these are some of the example processes, how you can mix fluids, how you can generate these tiny droplets of picoliter volume, and how you can separate particles or pump fluid in a powerless manner into channels. And these are some of the examples of various processes. You have electroosmosis, how you pump fluid by applying electric field, how you fractionate analytes using electrophoresis, and how you sort particles using dielectrophoresis, and apply magnetic field to actuate ferrofluids, or use sound wave to focus, separate, sort particles. These are some of the components. You can have micro pumps, micro valves, micro mixtures, droplet generators, and micro reactors serving a microfluidic system as a whole. And talking about the concept of lab on a chip, the concept is the entire function that you do in a typical lab can be squeezed into a credit card size chip. And that concept is lab on a chip. So for example, if you do typical molecular analysis where you lyse the cell, you extract DNA and you purify, and then you do the PCR process, and then you do the detection, everything can be squeezed into a single device, a chip. That can do the same process. So hence the concept of lab on a chip. And these are some of the successful lab on chip devices. So this is probably the first one, the iStat. And then there have been several. I've just put a few which have really transformed the field of chemistry and biology in general. So now I would, so that gives some background of the area of microfluidics. And now I'll move on and talk about two different research work that we have done in our group. And the first one is about detecting gasotransmitters in blood in an effort to detect the onset of sepsis early. And here I would be talking about a blood plasma separation device that we have developed, which is an important unit of this platform that we developed for measuring gasotransmitters in blood. So the motivation really is that we're trying to diagnose sepsis early, which is a life-threatening condition. And as you will know, when that happens, when body responds to an infection, damages the own tissue and organs. And the idea is to build a lab-on-a-chip device for accurate and reproducible point-of-care measurement of gasotransmitters. And this is really a concern because sepsis carries a huge socioeconomic burden, and it is having more and more impact on the society. And what is interesting is the reports say that nearly 80% of deaths could be prevented by early diagnosis and appropriate therapy. Time is very important when you are talking about sepsis, because the risk of death basically increases by 10% with every hour gone. So that means you really need to develop it early and rapidly. Unfortunately, most of the available technologies are either time consuming or they lack specificity and inaccurate. So there is really a need to develop a rapid measurement tool. So if you look at gasotransmitters, you can see that gasotransmitters play a very important role in cellular function, and as well as when cell wants to respond to the inflammation. So gasotransmitters such as hydrogen sulfide, hydrogen peroxide, nitric oxide, and the carbon monoxide very intimately participate in the systemic inflammatory response process. And hence they could emerge as promising biomarkers for sepsis. That's a hypothesis which needs to be proven. So what we're trying to do is to develop a microfluidic platform and later validate that this is useful as an early indicator of sepsis. But right now, our effort is to develop this platform. So if you look at this platform, so typically as the patient is waiting, our effort is to collect the sample, which is blood, and then try to look at the level of these gasotransmitters in blood. So since we have decided to use an optical technique for measurement, we would like to filter out the blood cells and before we actually look at the chemistry and then the optical detection. And that is done using a continuous plasma separation module. So that I will present subsequently. And then I will talk about how we can integrate with the rest of the system and then do the measurement of gasotransmitters. We have been able to measure hydrogen sulfide and hydrogen peroxide so far. The work on CO and NO is currently ongoing. We have done some preliminary clinical trials with the hospital just to observe how these two gasotransmitters evolve with time as a patient is inducted and then comes out. We have seen some trend, encouraging trend, although it has to be fully validated once we actually have an instrument, because it's very difficult to carry the system that we have in the lab and to an ICU and do the test. Nevertheless, so I would first talk about the plasma separation module that we have developed, and then talk about the rest of the platform and some of the results that we have. So the first part is to develop this blood plasma separation device, which can work continuously. And we have decided to use the approach of sound wave to achieve that. So if you look at blood sample, it constitutes red blood cells and white blood cells, platelets, and a major part of it is plasma. And plasma is in particular very relevant because although the most part of it is water, it contains the biomarkers of interest like proteins, and it could contain bacteria and microorganisms, viruses, and metabolites, and nucleic acids, etc. So if you really want to understand the health of an individual, you really need to, apart from looking at the cells for some diseases, you also, what is more important is to look at various constituents in plasma. So that is why separation of plasma from blood becomes very relevant. So the microfluidic devices, the lab-on-a-chip devices that have been developed, most of them actually extract plasma from blood and then look at the biomarkers of interest in the plasma. So there are various methods that have been developed in literature for separation of plasma from blood. The most primitive one is the sedimentation method, where you leave the blood in a tube, and because of the sedimentation effect, because the cells have higher density than the medium they sediment. The second method that became popular was the microfiltration method, where you push the blood sample through a filter that has a pore size smaller than the size of the blood cells. So you end up getting the plasma at the underside of the membrane. The problem with that is as you push the blood, these cells, they deposit on the top side of the membrane, and this layer of this deposit grows with time. So that basically impedes filtration. So that sometimes it happens that the membrane ruptures because you're applying too much pressure, which you need to be able to filter. The solution to that has been if you can use cross-flow filter. So here, the cells flow in a direction perpendicular to the filtration directions. So that is why, so you don't have any buildup of deposits. So that problem that you have in dead-end filters do not exist. And then there have been newer methods using obstacles. So this method is known as deterministic lateral displacement, where you push this blood sample into an array of posts inside a channel, and with each subsequent row offset from the row ahead. And so that when this blood sample is pushed, the cells actually deviate from their original streamline and get separated from the flow path. And so that is why you get, you end up with collecting the cells on one side and then the pure fluid on the other side. The second method is based on non-inertial lift, because the cells are deformable. When you flow them into a channel, they tend to lift off from the wall because of this hydrodynamic lift effect. And so that is why you end up, all the cells are the center of the channel with clear plasma at the walls. And then there have been this centrifugal effect. So you have the curved channel where you flow this blood sample, and the cells, because of the centrifugal force, would end up following the outer, the fluids closer to the outer wall, whereas the clear fluid can be collected by simply creating a bifurcation. You can have it closer to the outlet, closer to the inner wall. Then there have been active methods where you impose external fields such as magnetic fields. So here, since RBCs contain hemoglobin, and which is magnetic in nature, there have been reports that magnetic field can be used to separate cells from blood. And people have also been able to use electric field, such as dielectrophoresis, which basically relies on the difference between the permittivity of the cells and the medium to be able to isolate the cells from the plasma. And then the acoustic method, which we have also worked on, and I'm going to talk about that. So first of all, a little bit of a background of the acoustofluidics. So this shows the cross section of the channel. One can create a standing wave by appropriately choosing a piezoelectric transducer, which can be bonded to the bottom of the chip, and the dimension of the channel and the wall material. So typically you need to have materials of high acoustic impedance such as silicon or glass, and you need to have the width of the channel as half the wavelength if you want to create a acoustic node at the center of the channel. And by adjusting the frequencies such that the width becomes half the wavelength, you can create nodes at the center and antinodes at the wall. As you know, the standing wave is basically a superposition of incident and reflected wave. So the walls are reflective, so you end up creating nodes and antinodes. So if you have a particle which is exposed to the standing wave, it is subjected to what is known as the primary acoustic radiation force, and which is given by this expression. It is related to particle size, the energy, how much acoustic energy you are putting in, the wave number, and a parameter called contrast factor, which is phi here. So you can see that if for a larger particle, this force is going to be higher. And if you put in higher amount of acoustic energy, this force is going to be higher. The contrast factor is actually a function of density and compressibility of the particle and the surrounding medium. And it has been found if the contrast factor is positive, that means phi is greater than 0, those particles will end up getting focused at the nodal plane. And if it is negative, they end up going to the antinode. So that is the contribution of primary acoustic radiation force. In addition to that, you can have secondary acoustic radiation force, which originates because of the interaction between the particles, the scattering of one particle influencing the surrounding particle. But typically, the secondary acoustic radiation force is at least towards a magnitude smaller than the primary acoustic radiation force. So it is neglected in most cases, except, one case where the particles first get focused at the nodal plane because of the primary acoustic radiation force, which is 0 at the nodal plane. And when this force vanishes, the secondary acoustic force, which is, even if it is slow, it starts to play a role. The other contribution comes from acoustic streaming, which originates because of the attenuation of the sound wave due to the viscosity of the fluid. But again, for large particles, the effect of acoustic streaming is quite negligible. And acoustic streaming is really becomes prominent when the particle size is less than a micron. But as you know, the cells are greater than 1 micron, so the effect of acoustic streaming is neglected. So this is the experimental setup. You have the device and you have the piezoelectric element that is required for actuation. So you have the function generator and the power amplifier to actuate this PJT, which is typically requires a megahertz frequency. So 1 to 2 megahertz or maybe about 10 megahertz is what is typically used in such cases. And since you have interfaces and you have viscosity of the fluid, the energy attenuates and eventually gets converted to heat. So you need to have a cooling arrangement to make sure the rise in temperature doesn't affect the sample or the process. So our effort was to be able to focus the cells at the nodal plane. There has been work in the literature where they have used use of sound wave for focusing of red blood cells. In fact, this work from Lund University, they are the first group to have shown that. But what we found was the physics of this acoustic focusing of red blood cells, although demonstrated experimentally, was not very well understood. And that is where our focus was. So these are some of the work from the same group at Lund University. And they have shown the plasma flow rate about 10 microliter per minute. So our effort was to understand the physics better and then try to improve this throughput. So that is where we looked at this problem. So typically, if you want to focus cells and separate plasma, you would infuse the blood sample into the chip using a pump. And you have this PJT actuator, which would focus the cells at the center. So you can extract the cells here and the plasma can be extracted there. And so this video shows two cases. One is for a dilute suspension, which can very nicely be focused at the center. But in case of dense suspension, this is whole blood, it is very difficult to focus. And so that to be able to maximize the plasma flow rate. So we try to understand that how the physics of acoustic focusing of dense suspension such as blood can be understood. We found that in case of dilute suspension, the theory I talked about the primary acoustic radiation force works really well. And for example, if you double the acoustic energy, the particles would focus half the distance from the inlet. Similarly, from the migration physics, you can show that if the flow rate is doubled, it will take twice as much distance for the particle to come to the center. This simplified argument actually doesn't work when it is dense suspension. So we tried to look into the literature, and we found this paper which have actually shown that when you put some suspension into a flow, they tend to migrate outward from the center line. And that is because of the fact that the medium is flowing. And the force is known as shear-induced diffusion force. And we hypothesized probably there is a contribution of shear-induced diffusion force, a competition between that and the acoustic force, which is trying to focus this dense suspension. So this was also sort of proven by early experiment where, let's say we already have focused a dense suspension using sound wave because of the primary radiation force. When we switch up the field, it actually goes back to its on-focus state, covering the entire width of the channel very quickly within 2 seconds. And this time is actually longer than since it is in a flow, this 2 seconds is much shorter than the time the fluid would take to come from upstream to this location, which is under observation. So that is at least 1 order of magnitude smaller. So he says that something is pushing this already focused cells outward. And we hypothesize that is the shear-induced diffusion force, in fact, here as a flux. So you have basically acoustic force, which is trying to focus this particle toward the center, and the shear-induced diffusion force, which is trying to take these particles away from the center, from the node. So we did follow some theory, and I'm not going to go through details. So with some theoretical analysis, we could actually show that WC is the width of the focused stream. And that is related to, that depends on this factor. One is the energy density, how much energy, acoustic energy you are putting into the system, the concentration of the suspension, and the flow rate. In fact, it is written in terms of shear rate. So you can see that if the concentration is high, WC is going to be higher. That means it's more and more difficult to focus this dense suspension. Similarly, if you drive the sample at a much higher flow rate, WC is going to be higher. That means it's going to be more difficult to focus. And if energy is higher, then WC is going to be smaller. That means if you put in more acoustic energy, you can actually focus into a narrower stream, which makes sense logically. So this is basically summary of result. It says that at every flow rate and every energy density, there is a flow rate where you cannot focus the stream at all. Okay? And this was also verified from experiments. And then, so this was a simplified model that carried many assumptions. And then we carried out a full-scale Navier-Stokes simulation and showed that, I'm going to skip these details. We actually showed that this model can predict the experimental results of the focusing of dense suspension. And we could explain that from the timescales. So we defined the acoustophoretic timescale, the shear-induced diffusion timescale, and the advection timescale, and corresponding dimensionless number, the Strohal number, which is the ratio of the advection timescale to the acoustophoretic timescale, and then the Peclet number is the ratio of shear-induced diffusion timescale to the advection timescale. And we could actually understand the width of the focus stream and the length that you need to focus this dense suspension in terms of the Peclet number and Strohal number. So once we have understood the physics, we could find that to be able to focus this dense suspension, your shear induced diffusion timescale has to be much greater than the acoustophoretic timescale. That means you really need to make sure that by either using a smaller concentration or a larger energy density. But since you are dealing with whole blood, because you do not want to dilute the blood, because the concentration of the analyte is going to be reduced, compromised. So you really need to know what is the energy level, what should be the channel dimension, so on, to be able to satisfy that and focus. So through this understanding, we could actually develop a device, and we showed that. So this is how it shows. So it gradually starts with whole blood, which is about volume fraction of 40%, and then going into the plasma outlet in steps. And this is the actual working of the device. So this is when the sound wave is on, and you can see the plasma is being extracted from both sides, and this is when the sound wave is off. So all the cells have really covered the entire channel, and then when the field is on again. So we could actually increase the throughput through understanding of the physics of the problem, and then we could also provide some rule of thumb depending on the flow rate that one desires, what should be the structure of the design. So I discussed about a plasma separation device. Now I'm going to talk about the rest of this system, and then show some results where we have detected the gasotransmitters. So I have about 10 minutes, I think. So this is the design of the chip that we have used to detect gasotransmitters. It's kind of a generic design. So this plasma actually comes from the previous blood plasma separation module. And you really need to mix this with some chemical probe that our chemistry collaborator has developed, which is originally non-fluorescing, but upon reaction with the specific gasotransmitter will emit fluorescence. And in this particular case, we were trying to, since this was a study, we were trying to infuse exogenously these gasotransmitter and control its level and find out the signal. So to be able to establish a calibration curve. So that is why this inlet is there. And this shows for the hydrogen sulfide how the initial non-fluorescent becomes fluorescent upon reaction with sulfide in this particular case. So first I'll talk about detection of hydrogen sulfide. So this is a photograph of how these three different modules are combined. So you have this acoustic plasma separation module, and this is the mixing module. You really need to design this chip for the mixing and incubation module, taking care of the diffusion constant for the probe and the plasma, and satisfying how much channel length that you would actually need for both to completely mix, and also the reaction time from initial experiments that we carried out off chip, where we mixed these two, and we waited for different time and ensured that after what time the signal actually is saturating. And the detection is quite trivial. It is like a typical afterfluidic detection, which we have shown here. So this shows that the original probe and the plasma are actually non-fluorescing, and as you have more and more hydrogen sulfide, the fluorescence intensity actually goes up. And this result shows the fluorescence intensity with time. And it shows that as you mix and you bring into the optical module, the of course, you have a mixing time of minimum 10 minutes. So you need to design this channel so that they at least mix for 10 minutes. But beyond that, you actually see a deterioration in the signal. Okay. So that is where the microfluidics detection becomes important, because if you were to mix it off chip, and for example, let's say you extract the blood sample from the patient and you carry out centrifugation and carry out the mixing and detection off chip in the conventional laboratory way, you will end up actually deteriorating the signal. So that is where the microfluidics technology becomes important, because all these are automated and seamlessly integrated, and so that you can actually capture the maximum signal. And this result shows that with the increase in the gasotransmitter, initially there is a fall in the signal and then there is a rise. And we did exhaustive experiment to actually say that there is some interaction that happens between these different gasotransmitter when we did studied individually with the plasma proteins. So when we actually separated the plasma proteins using a 10 kD protein column, we were able to suppress this. And rather, since the integration of deproteination with on-chip was a little difficult, we could solve that by simply diluting the plasma. And we found about a dilution factor of 3, this intensity picks up. And we performed experiments with various plasma samples, and we could come up with a calibration curve where you can, depending on the signal, you can find out what is the concentration of the sulfide in the sample. And then later, we also studied detection of hydrogen peroxide. In this case, the assay is different. The probe is different. But the working of the module 1 is the same. The design of the mixing and incubation module has to be different, because now we are talking about a different analyte and different probe. So that had to be redesigned. And we also carried out a similar study where we showed that you could deproteinize, you could dilute the plasma and detect hydrogen peroxide reliably. And we were able to again establish and validate the calibration curve. So that you can see that this is the comparison between the measured and predicted. So as a future work, so we also did some initial clinical study where we measure sulfide as the patient goes through from induction to recovery, and we have seen that it actually keeps on increasing, and then as the patient recovers, the levels go down. And we have seen cases where the patient becomes more critical. The hydrogen sulfide levels actually picks up. It's normally higher than the patients which have recovered nicely. We are trying to develop the prototype because to be able to validate, one needs to have an automated system to put into an ICU kind of environment, because we faced a lot of challenge in actually even doing some preliminary work that we have done. So once we have a system in place, the validation will become a lot easier. So that is where we are. I would probably, and then we also have this detection of nitric oxide and carbon monoxide is going on. And the final idea is to, after we do clinical validation, we would do collect a significant amount of data, and then we have collaboration with IMSC, Institute of Math Science, who would help us in doing the risk score prediction. So that is where that's what our goal is. I would skip the second part because of paucity of time. But before that, I would acknowledge the work from our group. Many of the students work on what I just presented, and the funding agency for supporting our work, and also the collaborators, Professor Muralidharan from Chemistry Department, and Dr. Paul Ramesh from Apollo, who were collaborators as part of this initiative. With that, thank you so much for your attention. I'll be happy to answer some questions you may have.
Thank you, Professor Singh, for the brilliant talk. We have a few questions from the attendees. So I'm taking first those, and then we will take a few questions from the panelists. So one of the attendees has asked how the concept of microfluidics can be used in early detection of Alzheimer.
Okay, I really don't know, but I think what microfluidics brings in is the capability to to improve the way conventionally it is being done, meaning it could process things faster, and because it also helps in integrating various systems. And the other thing is it also makes systems affordable. Because as compared to doing things conventionally, if you can develop a chip, they are commercially more viable, and they are affordable. So I really don't know about how exactly the Alzheimer it can benefit, but in general, detection of any disease can benefit from the microfluidics technology in general. Yeah.
Yeah. Another question is on the same line. It says, can microfluidics detection can be used in SARS-CoV detection?
Yeah, there have been a surge in the publication in the last couple of ever since it emerged. So in fact, some of them have gone to the next level of actually developing devices. And so if you look at the challenge was this. So there is this gold standard RT-PCR technique, and then there are this antigen-based test strips, right? Rapid diagnostic test strips. So they are extremes. One is really, it's very reliable, but it takes time. The other one is, really fast, the antigen test, but the reliability, as you all know, has been a concern, right? False positivity, negativity has been a concern. So what some of the work coming from microfluidics has been trying to breeze is to make something accurate, at the same time the detection rapid. So that is what this technology is promising. As you know, to do things like RT-PCR, you have to lyse the virus, and you have to extract the RNA, you have to purify, and then you do the PCR, and then do the detection. Could be laser-induced fluorescence or any other techniques. So in fact, each of these techniques were quite matured in microfluidics. So that is where rapidly only the biochemistry part is needed to be understood. And once the interface was done, people could come up with such systems. So they are coming up, microfluidic systems for SARS-CoV-2. In fact, we also started doing some work in our group. It is still, we are working on it, because we have been also working on bits and pieces things like particle extraction and DNA purification and so on, and laser-induced fluorescence. But yeah, things have come up commercially, and then there's a lot of research effort being put also in this direction.
Thank you,
Another
sir,
question
for
is,
Naveen sir. In this context, I want to ask our speaker. In this case, for microfluidic device for this COVID detection, is the sample will be saliva or blood?
They have taken saliva, and there are methods where you can just collect and dip into a fluid reservoir, and then that can later infuse into the device. And there are also some papers that have lately come which also uses blood. But that would probably be useful at a later stage. I think the first occurrence would be in the saliva. But yeah, both will have pros and cons.
Can be possible. Another question, sir, what will be the cost for that?
I really do not know. I really do not know, but I think the real issue that it is trying to address, as I said, is bridging the gap between the gold standard technique and the rapid test kit. But yeah, I'm sure if it has to be commercially viable, the cost is very important.
Thank you so much, Dr. Sen, for your so enlightening talk. Thank you once again.
Thank you.
So one more question is here from one of the attendee. The question is, would a hybrid acoustic magnetic field blood separation technique be easier than using just one type of field?
Yeah, so it's a good question. In fact, the combined acoustics and magnetic field is particularly for microfluidic application. Now, in physics, it's probably a little more mature, although it's still very challenging, very complex phenomenon. In microfluidics, people have started looking into this direction because people have looked into this combined, for example, acoustics and optics. If you talk about things like sonoluminescence, so that's a combined acoustics and optics, right? So similarly, the research in acoustics and magnetic had started. But the coupling is so complex. If you want to build a device based on that, you really need to understand the physics first and at the micro scale. So it is still evolving. Yes, I would say it's futuristic. You may see maybe after a few years, there will be papers coming.
Another question is, can microfluidics work in environments except that of Earth without being energy extensive?
Okay, if I understand the question, you were asking that can microfluidics be useful in space application, for example?
Without being taking much energy or extensive energy.
Okay, yeah. So I mean that is in fact one of the important application of capillary flows is into space application. So for example, NASA has put a lot of effort in developing capillary based flow devices, because if you just take the device and it works of its own, you don't need to really carry a pump with you, because every gram matters when it comes to space. In fact, if you look at the simple structure like a cup they use to drink coffee in space is designed in a special way to be able to to enable drinking. So similarly, when in space, if you want to manipulate fluid, you want to have pumping. There are work where they want to study capillary flow in microgravity environment. In fact, when the gravity is smaller, the capillary effects are much stronger. And I mean, we also have some interest to work in that direction because we didn't simply have the facility, we didn't have the facility yet. Now we have a combustion center where they have a drop tower where you can actually mimic sort of, reduced GE. And we want to do some work also in that direction, similar to capillary flow at reduced gravity, etc.
Another question is, what are the some simulation tools that can be used in the field of microfluidics?
Yes, COMSOL is a very powerful tool. In fact, if you look at the scientific papers in microfluidics area, almost more than 90% would be using COMSOL multiphysics. Because, as you know, in microfluidics, we look at small length scale of the order of micron, 10 micron, 100 micron, so on. And also we have effect of electric field, magnetic field, acoustic field, and optics, and so on. So COMSOL multiphysics has nicely brought together a package. So that is very popular. And then there are other techniques, other softwares like ANSYS and so on.
Okay, so due to time restrictions, I think we can take one or two questions from the panelists also. So if any question, then please ask.
Thank you, Ashish. Thank you for your extraordinary talk. I think we need to call you again for guest lectures. In fact, audiences, Dr. Sen has an entire course in SWAM NPTEL, isn't it, Ashish?
Yes, I do.
Chennai. So that's a very extensive course. I have questions like regarding this plasma separation. Do you ever see these clogging effect while in these channels while we are doing these kind of effects? And secondly, is it temperature dependent? Because when we do traditionally, like say centrifuge and all, we need a cold environment. How about this via acoustic?
Yeah, so talking about the first question about clogging, yes, blood is a very complex fluid, as we all know. It's one of the most complex fluids. And when you put into microfluidic channel, often you encounter clogging problem. So in flow condition, you have the channel roughness, which can affect, it can enhance or suppress clogging. If the channel is rough, what happens is the cells tend to interfere with this micro nano asperities, and then they adhere because of the surface energy, and the clogging proceeds from there. If you make sure that the channel is having the roughness problem is sorted out, and if you can hydrophobize for the channels, for example, you can put some liquids that can create a nano coating on these channels, you can suppress clogging to a greater degree. We also use one such chemical in our lab and treat the channel, because before these these blood plasma separation experiments were carried out. In the acoustics chip in particular, we also see a very small layer of blood, particularly when you used whole blood. And if you're using slightly older blood, it actually creates a very thin layer closer to the wall, partly because the blood was already there and it has the viscosity has gone up, and then also partly because there is a boundary layer streaming at the walls. But we are able to suppress. Every time we are doing sample, we are using fresh samples, and we are treating the channels to overcome that. I think the second question was about temperature. Temperature has effect. In fact, for the work that I presented, temperature has a significant impact on the process. In fact, the resonant frequency would change if the temperature is different. If the temperature is different, the blood characteristics would be different. So that is why if you use things like acoustics, you have to have a heat sinking mechanism so that you still have an ambient temperature and isothermal condition, throughout a channel where the fluid sample is. And Yes, we have seen temperature can degrade the sample faster. But we were using at room temperature, and which was fine. We didn't face this issue.
Thank you, Ashish. Probably we can discuss more later about this.
Yeah, we are running late. So I think we can take these questions in the chat box and we can email those questions to Dr. Sain, and if he agree, he can reply back.
Sure. It will be,
thank you.
We can do that. Thank you very much. Thank you, Professor Naik and the organizing team and all the staffs and everyone.
So let us thank Dr. Sain for the wonderful and useful lecture, and let us move to the next talk. Thank you, Dr. Sain.
Thank you. I will answer.
Yes. And please be attentive at the end of the session and complete the assessment, for which the link is provided in the chat. So this is the last talk before the lunch. Our next eminent speaker is Dr. D.S. Mehta. He is currently a professor at Department of Physics, Indian Institute of Technology, Delhi. Previously, he worked as associate and assistant professor at the Instrument Design Development Center, IIT Delhi. Before joining the institute, he is a JSPS postdoctoral fellow at the University of Electrocommunication, Tokyo, Japan. He is also a postdoctoral fellow at National Donghua University, Taiwan, STA postdoctoral fellowship at fellowship in Japan, UNESCO Research Fellow, Tokyo Institute of Technology, Japan, and also research associate in NPL. He has actively working in the area of biophotonics, green photonics, and optical metrology. He has contributed more than 140 research papers in the international journals and several international and national conferences. He has received Teaching Excellence Award twice from the IIT Delhi, India. He has filed 9 patents and 1 technology transfer to the industry. Several awards and he get up several awards and fellowship. The title of his talk is Optical Nanoscopy, a super resolution imaging technique for nano size object and living shell. I may request Dr. D.S. Mehta to throw a light on this topic. Sir, I humbly request you to confine your talk to 45 to 50 minutes, followed by 10 to 15 minutes question answer session. Now, platform is yours, sir.
Okay. Thank you. Thank you, Rohit.
Thank you so much, sir.
Can you hear me?
Yes, sir. I can hear you.
Welcome. Yeah, okay. Thank you, the organizers, Professor Opishina and other members of the Nanotechnology department. So, good afternoon to all participants and panelists. So, let me share my talk first here. Hello.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. So, I go straight away for this thing. Okay. So, this is the topic I'm going to talk today, optical nanoscopy. And I decided because the seminar is being organized in nano era. So this is one of the important technique for this nanotechnology department of MIT University and nano era. And particularly, I would be focusing imaging of biological cells. Yeah, could you see the next slide? Hello.
Yes, sir. Please carry on.
Yes. Okay, so I will start from here. The resolution range of various imaging instruments, basically microscope, various imaging instruments I will talk. And you can see the scale bar here starting from the right side, pointer is here. So right side and left side here, 1 millimeter, you can see the ant, then you have 100 micron, 20 micron, 1 micron, sub-micron range, going down to 1 angstrom, which is basically single atom. So this is the range of basically different sizes. And if you look at the human eye, our eye can see the smallest object, which is about 100 micron, not less than that. That is why we do not see any biological cells, bacteria, or virus is impossible. So the scientists started building this optical microscope, which is basically what we call is a wide field microscope or bright field microscope. And you can see easily here the red blood cells, white blood cells in the range of 20 to 10 microns. Even the diameter of red blood cell is typically about 7 micron, thickness around 3 micrometer. So it can be seen, those cells can be seen easily by the optical microscope. And coming back to the bacteria, so particularly let's talk about E. coli bacteria, which is about ranging from 1 to 2 micron. In this range, again, you can of course use optical microscope and also slightly improved version of microscope we call is a confocal microscope, and particularly fluorescence microscope. And both these microscopes can see the object up to sub wavelength, basically up to 500 nanometer or something like that. This is the range. Beyond that, these microscope, both optical microscope or laser confocal microscope, cannot see the object. Then, of course, various scientists around the world, they build extreme resolution like atomic force microscope. You already know the scanning electron microscope or tunneling electron microscope. All these are called a near field scanning microscope. And they all are called scanning probe microscope. They all come in the category of scanning probe microscope, and their resolution is very, very high. And this is very, very useful for all material scientists. They could virtually see the single atom defects in the graphene and so many things. And if you see all other multi-layer structures, you can also see. And moreover, at the moment, the most important object right now in the world is the virus. And that virus is also seen through these atomic force or scanning electron microscope or all those things. So what I would like to say, this is a typical structure of virus, coronavirus. There's about 100 nanometer diameter, but it has a spike protein which is much smaller than that, something like 10 nanometer down to 5 nanometer. So that is why scanning electron microscope, all these can be used for this. So look at, I come back to this one, super resolution nanoscopy or super resolution optical microscopy. So scientists did not leave that resolution limit. They have kept on working, and then they developed that super resolution microscope, optical microscope, and now you can see up to single molecule, something like single molecule, 10 nanometer or 20 nanometer range with the optical microscopes, optical nanoscopes. So this is what I am going to show you. So why this optical bright field microscope, conventional microscope could not see the small object because of the diffraction limit. So I will show you what is this diffraction limit. And if you see after breaking this diffraction limit, then we can see really the sub 100 nanometer, 50 nanometer range object sizes, nanoparticle, nanostructures, and maybe some people may be trying with the viruses also. So this is possible. So this limit was very, very important, and till 2000, around 2000, everybody, all the optical scientists believed this limit, and that limit is also basically written on a statue on this in a Heidelberg, Germany, and that because the Abbe, this we call it the Abbe diffraction limit, and this was basically the smallest object we can see is that is lambda by 2 n sine theta, and which is two times of numerical aperture of the objective. But now, since 2000 onwards, or even 1995 onwards, that scientists have developed super resolution microscope, how to break the optical, this diffraction limit of the microscope. So this is what I'm going to show you. So to begin with, sir, microscopy has been there for a long time.
Yeah, it is there.
So we are able to see your slides.
Yeah, I'm saying. So you can see that it starts from along by 1960, 1560s, first microscope here. Then came the most famous microscope is a Leeuwenhoek, and Leeuwenhoek developed this microscope. And then comes basically the Hooke's microscope. These are the oldest microscopes. Then that time they could see the virus, the bacteria, and then field of microbiology was developed. So now, okay. So since then, this lot of work has happened in the field of microscopy and nanoscopy. Now you can see so many Nobel Prizes have been awarded in the field of microscopy, starting from 1953, what we call is a phase contrast microscopy by Jernak. And then Dennis Gabor also got Nobel Prize in 1971 for developing a holographic microscope. Right now, this microscope is very famous among the researchers of the optics people to build a quantitative microscope. We are also working in this area. And then SEM, scanning electron microscope, tunneling electron microscope, developed by Ruska and these two scientists. They also got Nobel Prize in 1986. And look at this one. Nobel Prize in Chemistry was awarded jointly to these three scientists for the development of super resolved fluorescence microscopy. It is given in the chemistry, but it is a purely optical nanoscopy. All the optical techniques are used to break the diffraction limit, to go beyond the 200 nanometer, 500 nanometer, and to see up to 50 nanometer. And of course, most recently, the 2017, this again Nobel Prize in Chemistry was given to these three scientists, and for the development of cryo-electron microscopy. So I will be focusing mainly on this optical nanoscopy here, and how the diffraction limit of the optical microscope can be overcome, and by various techniques, and why we are focusing. All the scanning electron microscope or atomic force microscope cannot be used for biological cells and living cells particularly. So only the light field and electromagnetic field of light is useful for such kind of entities. So to begin with, a simplest microscope is a simple microscope, which is nothing but the magnifier, and we call it a hand lens. And all of you are familiar with the hand lens. If you put this hand lens close to the object, you could see the magnified image. But typical resolution of this hand lens goes to 50 micron. That is again a poor resolution. Now you can see the most famous optical configuration of an optical microscope is this one, which we call is a compound bright field or wide field optical microscope. This is having a combination of lenses. So light coming from the left side, which is basically coming from the light source, and collimated, made it parallel, and focused by this diffraction, this condenser lens on the object. Object being, let's say, 1 micron or sub-micron bacteria, 1 micron bacteria, and that scatters light. And the scattered light is collected by this objective lens. And if the object is exactly at the focus or within the focus of this objective lens, it will magnify. And maximum magnification of this lens could be 100x, and maximum numerical aperture could be 1 in the case of dry air, or if you put an oil, that can go to up to 1.5. This is the maximum limit. So maximum magnification. So then this microscope, 1 micron will be only enlarged by 100 times. You are still not able to see with the naked eye. So you use another lens, what we call the eyepiece. An eyepiece, let's say 20 times magnification or 10 times magnification, you can use a slightly larger focal length. Again, this object comes exactly close to the focal length of this one. So it will further magnify. So total magnification of the 1 micron bacteria becomes several times, that is around 1000 microns. So 1 micron bacteria becomes 1 millimeter size in your eye. And that is why you could see a bacteria of 1 micrometer size or a RBC cell and in your naked eye with the help of all these three combinations. So all these three lenses are very important: condenser lens, an objective lens, and the eyepiece. And two-stage magnification is useful, obtained by this objective lens and eyepiece. And condenser and objective is basically playing the role in the case of resolution. So this is the limit of this microscope. So what is the minimum size of the object we can see is not less than 200 nanometer in the lateral direction. And in axial direction, it is basically about 500 nanometer. So any object whose size is smaller than in these two dimensions in the axial and lateral direction, you cannot see. Say, for example, there are suppose 50 nanometer nanoparticles in the object plane, and then you try to use a maximum most powerful objective lens, and the focus spot will be like this one, and so you could not see any nanoparticle. You will finally conclude that it is only one. There is no small particles. This is only one object, or no object is there. So this is what is the diffraction limit. And look at this. This is a single molecule, like we call green fluorescence protein, which is very famous for biologists, and that is having this kind of structure. multiple elements, multiple molecules, and then that is very small, about 2 nanometer. So in such kind of microscope, it is impossible to see such kind of thing. So what is this diffraction limit? So we know already that the total resolution of a microscope is governed by this formula, which is about 1.22 lambda by numerical aperture of objective plus numerical aperture of condenser lens. And normally we use both the lenses same. And then we come up with this final equation, which is about 0.261 lambda by Na. So if you use this microscope, so we always talk about the Rayleigh criterion of resolution. And since light is so according to the Rayleigh criterion of resolution, so we can say that there are two objects in the focus point of the sample plane only when the intensity maxima of one coincided with the first minima of the second object, then the two object points are called just resolved. This is the middle one. Otherwise, the first one is not at all resolved. You cannot conclude. And then you have to go always beyond this. You in the just resolve also you cannot make sure that there are two. So you have to go beyond that. So that should be the actual picture. So whenever you try to image the such small nano-sized particle, 100 nanometer, 50 nanometer, so what you see is this kind of diffraction pattern. So from bright field microscope, you have a super resolved microscope. This will be the case here. Then that is what is the diffraction pattern we obtain. So what this is the only limit what a microscope imparts in the hinders in the super resolution. And why this is so? Light is an electromagnetic wave, and diffraction limited resolution is due to the wave nature of light. And light gets diffracted, scattered whenever it passes through small objects, edges, and corners with sizes comparable to the wavelength. Let's say, for example, you have a 2 nanometer size nanoparticle here, or fluorophore, fluorescent dye. You shine with the excitation light, that light will be diffracted like that. So what you will see is a diffraction pattern, and hence the size of the particle will be completely not visible. So this is what is the diffraction limit of the optical microscope. So how to overcome this diffraction limit? So there are methods how to break the diffraction limit of resolution. That is what we call is a resolution beyond diffraction limit. So of course there are electron microscopes. You already know that for nanotechnology department, this is the most important equipment: scanning electron microscope, tunnel electron microscope, and you also have atomic force microscope and near field scanning optical. These microscopes are very popular for very important for nanotechnology, material science, nanoparticles, nanostructures, nanorods, so on. So all whatever the nano era you are talking about, this is except biologists or for material science, this is important. But these microscopes are not good for living cells, tissues, biomolecules. Damage to this leads to damage to cell. A rigorous sample preparation is required. Of course, coronavirus image was taken by the electron microscope, but with a lot of sample preparation. So if you want to see live cell, let's say a red blood cell, which is a donut shape and central part is a membrane. If you want to see the thickness of membrane fluctuation, so you cannot see with the atomic force microscope, scanning electron microscope, and none of them will be able to see. So we have to build an optical microscope which is working only within the range of 400 nanometer to 700 nanometer visible light, and we have to break the diffraction limit. And such kind of microscope is useful for all living cells, and without harming, without damaging them, and without any other rigorous sample preparation. So here is the story behind this optical nanoscopy. And that is basically comprising these 4 types mainly. What we call the stimulated emission depletion microscopy, structural illumination microscopy, and photoactivated localization microscopy, PALM, stochastic, STORM, and T-STORM, direct stochastic. All these techniques were scientists working in these techniques were given the Nobel Prize in physics. More details you can see this their talk, basically lecture, is available on this website. So you can see. So I will talk about a couple of these techniques, how we can break the diffraction limit. So here, before going to the optical technique, let's look at this electron microscope. The basic configuration of optical microscope is this one. You have a light source, condenser lens, sample, object plane here, and objective lens, and then a projection loss or tube lens or eyepiece, you can say, then eye. This is the optical lens, optical microscope. And similar to that, this Ruska and other people, they developed 1930s electron microscope, a scaling electron microscope. So how to replicate such kind of phenomena? So you can see now electron beam is generated, and then condenser lens is kind of magnetic field, basically focusing the electron beam on the sample, then it again diverges, then again further focusing, and also so on. And finally, you see the image on the screen, and that screen has to be a fluorescent screen because our eye can see on the visible light. So electron will be bombarding on the fluorescent screen, light will be emitted, and then you could see the images of the small nano size or even atomic size structures. And this is a scanning electron microscope structure, similar one. So why these electron microscopes are so powerful resolution? This is the cause. Despite the fact that the formula used for calculation of resolution is same, which is basically 0.61 lambda by 2 Na. This is what is, or Na, simply Na. And for optical microscope, so you can see maximum 200 nanometer. But for electron microscope, you can go down to 0.24 nanometer, means one angstrom. How? Because of this wavelength. The wavelength of electron is very, very small. So you can calculate wavelength of electron, which is about Planck's constant h divided by 2 of mass of electron, q basically charge, v potential applied to this, which is 1 over 1 by 2. And this is for non-relativistic electron. And if you have a relativistic electron, means slow acceleration, small velocity and high velocity electron. So you can compute the wavelength, and that wavelength comes out to be in the small range, something like, less than 1 angstrom, So this is why their resolution is very, 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 very large. So because resolution is directly proportional to lambda. So this is what is the cause. But this microscope cannot be used for biological cells. And this is the resolution or wavelength range for 10 kilovolt electron applied potential, which is about 0.12 angstrom. So this is the lambda. So that will give you very high resolution. And that is why, and come to this atomic force microscope or scanning probe microscope. These probes have very sharp tip, something like 50 to 100 nanometer tip. That tip moves on the sample. So think of a delicate biological sample, that tip cannot be moved. So hence you cannot see the live cell. So these two are very powerful for material science, but not very good for optical technology. So we are going to again work. We have to build, or scientist has to build the optical nanoscope by means of using light, visible light, and break this diffraction limit. So the first thing comes is this one. How to break the diffraction limit. You can see the focus spot. So if you have a single lens here, light beam, this is a typical microscope. We call it a 4-pi confocal or interference microscope. So light beam coming from here, passing through this dichroic mirror, divided into two beams by this beam splitter. 50% light goes to this path, 50% light goes to that path, and these two paths, L1 and L2, they are equal, and they are counter-propagating beams coming, illuminating the sample. So the two lenses are very powerful, and the focus spot looks like this one. So if both the beams are passing through the sample, then this single beam will be modulated. Is basically the interference pattern of this beam. So you can see multiple bright spots and dark spots. So now you can improve this resolution, and those spots can be further improved by moved by this one and make like much smaller by some mechanism here. And then you can basically, if you see that the full width half maximum of the dotted line is if you take the cross section here, so that will be about 400 or 200 nanometer, and that 200 nanometer comes something like 100 nanometer or less than that. So you could see a smaller object. So with this technique, you can improve the resolution about 2 times. So next category in this one is structured illumination microscopy, SIM we call. Then in the SIM, you have again one laser, and that one laser is divided into 3 beams by a diffraction grating. And those 3 beams are collimated, passing through the microscope, same microscope objective lens. And all the three beams will be focused on the sample. And on the sample plane, what you will see is not this red color. What you will see is this one. So those spot sizes are now something like 50 nanometer, 100 nanometer. So by means of doing some phase shifting mechanism, you can, of course, first you will take the image of this one image, then you want to take the image where there was no light, and you shift the pattern, then you record the another image, and you build the final image. And what you see is the difference between these two. So this is the diffraction limited resolution microscope. This is the structure beyond diffraction limit. So you could see all fine structure with this one. So this is what is the one of the technique was awarded the Nobel Prize. And this is how people build the most powerful. This machine is sold like this now, the structural immersion microscopy. So these are some of the results out of this SIM microscopy. You can see all comparing with the wide field or 3D SIM. And you can see much finer structure. Resolution improvement is 2 to 3 times. So 200 nanometer becomes something like 100 nanometer or 80 nanometer feature sizes you can obtain. So another most powerful technique for breaking the diffraction limit is the stimulated emission depletion microscopy, STED, stimulated emission depletion microscopy. What is that? This is basically coming from the fundamental concept. So if you know the fluorescence, for any fluorescence sample, having a fluorescent dye, let's say green fluorescence protein or something, some organic dye is embedded in the sample, then that organic dye has a ground state represented by this S0. It also has this excited state S1. These closed lines are vibrational relaxation, vibrational states. And the typical time scale for excitation is about something like 10 to the power 15 minus 15 second, very fast, almost spontaneously. And some time is taken for the molecule to come to this bottom of this X1 state. And this lifetime of this stage is about 10 to the power minus 9 second, nanosecond. And after nanosecond remaining here, after nanosecond, it will come down, will give you the fluorescence, green fluorescence. So let's say if you have used a blue photon to excite a fluorescein dye, and that molecule goes to this one immediately in the femtosecond scale, and it takes about picosecond to come here. After picosecond, within nanosecond, it has to come down. So this time scale is quite important here. So in a normal fluorescence microscope, all the molecules will come down like that, and they will all give you fluorescence. Hence, again, you have a diffraction limited spot like green color shown here, and then there is no way of seeing smaller objects. But what this Stephen Hell did a very fantastic or very intelligent trick, that he injected another laser, what we call the depletion laser, and that depletion laser, so beam shape was kind of donut shape like this one. And the wavelength of that donut shape was slightly slightly larger than this green color. So what will happen? So if you have two lasers, one is in picosecond range and the other one, nearly same picosecond, but delayed by 10 picosecond. So what it will do, it will not allow all the molecules to come down spontaneously, give you fluorescence. What will happen? Those photons which are injected here, slightly delayed, they will basically instigate or stimulate those molecules which are on the upper state to come down, but not to give the green fluorescence, give its own characteristic, that is basically red color or orange color fluorescence. This is what is called stimulated emission. This is the famous principle behind the laser, basically. So stimulated emission, basically by stimulating an excited atom or a molecule on the upper state by a photon, and to come down that molecule and gives it a clone photon, and that so most of the fluorescence molecule excited were basically brought down by this depletion laser or by a stimulated emission. So what is left is only at the center. Look, this is a donut shape. If you overlap here, so the remaining part in the periphery, all the fluorescence molecule will come down by this depletion, and only central part will be left. And that is what is shown here. You can see here the red color is showing is basically depletion laser via stimulated emission. Only central part, only few molecules are allowed to come down through fluorescence, and that is made use to you make use the fluorescence. This is what is the, so then this spot is scanned across entire sample volume. So the nanoscopists pick up only those bright spots like that and build the image, and they can build basically super resolution, and the formula is now changed. The formula modified a bit, the diffraction limited formula, which is about delta x lambda by 2 Na. 2 Na is multiplied by under root 1 plus I upon I saturation. So this is the intensity of that depletion laser. So larger and larger is that ratio, and then this entire factor will be multiple times more, and the lambda by say 50 times, 100 times, now not 2 times, it is lambda by 50 times, 100 times, you can improve the resolution. So say for example, for a confocal microscopy, that was the spot size of the laser, and which is about 250 nanometer, and with the help of STD microscope here, it has become to 50 or 40 nanometer. So you can see virtually all basically super resolved microscopy images. You can see here the confocal microscope is, of course, we are able to see something, but not very good. And again, there are so many the very poor image. At the same time, with STD images, the microscope, you can see fine details of all these protein stimulated emission microscopy for proteins, and all fluorescent tubulin, laminin, tubulin are all this labeled with antibody. And more results you can find here. Protein structure, all details. Look this one now with the help of this one. So you can also see super resolution image of living neuron. So living neuron captured on a STD reveals the dendritic spine. So many beautiful features can be seen with this optical nanoscope. But you can of course see with the atomic force microscope SEM, but you have to freeze the sample, dye the sample, then fix it, then you will see. But this microscope shows living cells. So that was the part what around the world. So we are also built our nanoscope, and our nanoscope looks like this one. And in fact, we have combined the nanoscope with the holographic microscope. You can see here again we have a laser beam passing through a grating, then we generate 3 beams. 3 beams are basically, this part is a holographic microscope. So not only one microscope objective, we are using 2 microscope objective, and one is coming to this reflector, which is mirror. The other one is going to the sample, and at the same time we are looking for a TIRF, total internal reflection fluorescence microscopy, TIRF imaging, because if the axial resolution also we want to have higher. So this part will work like this one. You can see here, the light will be propagated through the glass sample like this one, and wherever this is reflecting, it is basically generating the evanescent field, and that evanescent field excites the fluorescence molecule, and this light will give me the holographic concept, and so I can measure the device. These are the various concepts of this one. So you can see this is the prototype Green Photonics. Our lab's name is Green Photonics and Biophotonics Laboratory. So this is all entire multiple lasers coming here, and the chip is here, the laser coming from thine, and this is a holographic microscope. So light coming from this side, there is a beam splitter, 50% goes to the sample, 50% goes to the reference mirror, and they all reflect back and then collected with this one. And then we also coupled the laser from the side. So you can see the TIRF image unit here, and you can build holographic plus nanoscope. So holography gives much more detail. Combining holography with the micro nanoscopy gives much finer detail, like thickness measurement, all these things you can see. You could be able to see. Yeah. Okay, you are not able to see that. I wanted to show you this. So we also do similar kind of TIRF imaging and build this fine spots, and at the same time we measure this is showing the bright field image of multiple spots, you can say, and then you cannot see anything, but with the nanoscope you can build this with this all concepts. So with our microscope you could see the thickness, the phase map. This is given by the holographic microscope. This is given by the D-storm or the nanoscope, and nanoscope gives me fluorescence images, and the holographic microscope gives me measurement, and this is published in the scientific report. You can see, and so you can see the size of the fenestration here is about 100 nanometer, because the pore size is 100 nanometer. So you could see all these details, much finer details. You can 100 to 150 nanometer, basically the LSEC or liver cells, sinusoidal endothelial liver cells being measured. So not only our microscope is not only seeing, our microscope is also measuring. By measuring the thickness and refractive index and the pore size gives much more details about the sample. And this is how we prepare our turf waveguide structure here, and by multiple steps. And we can also use our microscope for this kind of nanometric surface profilometry, and something like 100 nanometer, 200 nanometer, or 100 nanometer flight, this thing. So this is our, through our holographic microscope, we can use not only for biological sample, we can also use for industrial object. And look at, this is one of the interesting thing. So with a normal holographic microscope, we try to build with a conventional holographic microscope, conventional one, the human sperm cell. So you could see only the head part of the sperm cell, and remaining tail part is not visible, because tail is basically something like about 100 nanometer thick. So, but with our new microscope, holographic structural illumination microscope, you could see both head as well as tail, long tail. And with the help of some computer program, we can build the image. This is the complete image. However, with the conventional microscope, holographic microscope, we cannot build it. So an order of magnitude better sensitivity, you can see it is 0.5, it is 0.02. So order of magnitude high sensitivity in height measurement we can do. So these are the fine structures of some basically macrophages. Macrophages are also human cells, and then phage map we can build. So our microscope can basically image nanostructures as well as measure the devices. And this result is, of course, published in the Optics Express. And you can see, and much finer details about these various waveguide structures with our microscope. With the conventional coherent light microscope, you cannot see the fine structure, but with our partially coherent structural microscope, you could see beautiful structure here. This is how we use our microscope for basically we use for sickle cell anemia, malaria. Mainly we are working in cancer, and also we are using profilometry of micro nanostructural devices. Macrophages, of course, we have made the images of holographic images as well as fluorescence images. Sperm cell we could quantify, because for IBF technology, in IBF technology, the quantification of this kind of cell is very important. So at present we are working on human embryo. So for IBF technology, so after this human embryo is developed into four cells are there, 6 cells. So how to select one cell out of it, which is most healthy. So that can be done only with holographic or quantitative phase microscope. So this is what we are working right now. So, and more details you can find all this. This work is published in the scientific report, Biomedical Optics Express of many lab on a chip is a very beautiful work we have done. And Optics Express, more on Optics Express scientific report. More details you can find all these data. So let me just finally 5 to 10 minutes. Can I just show some overview slides of our current technology?
Yes, sir. Okay. Yes, sir.
Yeah. So now we, apart from this biophotonics, in biophotonics, we have been working fluorescence microscopy, nanoscopy, holographic microscopy, optical coherence tomography. Apart from that, our group is also called green photonics and biophotonics. So we are working in green photonics that we call laser-based solid-state lighting, sunlight harvesting for daylight saving, luminescent solar concentrator, high efficiency solar tower or solar thermal system with using a big solar concentrator. And I'll just show you the couple of slides that we also build that holographic microscope like a field portable microscope. So right now you do a lot of pollution monitoring, and by simply counting the number of particles, but we wanted to see what is the structure, what is the real size of these PM 2.5 PM10, or we also develop heavy metal sampling unit. So we developed this one in collaboration with some industry under the MHRD project. So we have been successful. So it is, the technology is ready to be launched in the market. So apart from not only the concentration, what you are given report in the newspaper is like PM 2.5 is so much, PM 10 is so much, and PM 1 is also there. PM 2.5 means particle size is about 2.5 micron, 10 means 10 micron, but there are particles in the atmosphere, they are less than 1 micron, that we call PM1. So our microscope can see or can give you images plus concentration, everything of all these ranges, PM1, PM 2.5, PM 10. This is what is one of the important technique we, apart from biophoton, apart from that, all biophotonics. And of course, we are using this smartphone based point of care diagnostic devices. And this is, of course, all those techniques, what I showed you is the laboratory based, but I felt that whatever we are doing, this should be useful in the hospital, and directly nurse, a doctor should be able to use it for particularly for cancer detection. So I will show you a glimpse of our work. So this high coming from first from green photonics, recently we have technology transferred that we have made a high efficiency solar tower array based on photovoltaic system, which is basically non-mechanical tracking solar tower with mirror reflection and mechanical tracking. It can go to up to 5 kilowatt within 1/3. So efficiency from improvement is from 15 to 20% higher efficiency with the conventional solar systems, and within the 1/4 of the land space. So our system can go to 5 kilowatt. We are thinking about megawatt, and that is non-mechanical tracking. We have also developed a mechanical tracking solar tower with a mirror reflection, and that gives me up to 3 kilowatt. But we have now recently made up, again, this one is also 5 kilowatt. And with this tracking and concentration, we can achieve efficiency something like 20 to 25% higher efficiency. And this has been now the transfer technology. Now this company is building this technique for electrical vehicle charging station, rooftop high efficiency solar power generation for independent houses, schools and hospitals and shops and IT, and vehicle mounted solar tower and tracking for power generation and for agricultural purpose. So many things you can do. So what we have done is basically unique thing. So I will show you that photograph I cannot show you because this is patented, and that technology is given to this company. So our system is very useful for standalone. Basically, it is a standalone system, can generate sufficient power for any house, any hospital, any building, and particularly for electrical vehicle charging station, with the efficiency of 15 to 20% improve the efficiency within the land space area of 1/3 or 1/4. And tracking, also not very rigorous tracking. We have our invention is basically very unique, so you don't have to use a lot of power for tracking. Also, this is the uniqueness of our system. So why I did this? Because being an optical engineer, so I did not concentrate on making a solar cell or doing such a solar cell. But the major problem was how to improve the solar irradiance on the solar panel. So this is how now we are able to improve, and solar irradiance we can make double almost every time. So with this system, apart from that, this is another unconventional solar energy harvesting system, like very high efficiency water heating system. You can see behind the segmented mirror and huge Fresnel lens, the focus spot will be always on this plane. So we could see about 90 degree or 100 degrees temperature in somewhere in the month of October, November. Here, huge temperature. And with this system, much more temperature we can increase. This system, basically a non-mechanical tracking. And then, of course, we tried to use with this for solar cell, but solar cell gets damaged. But this system is very good for water heating, efficient water heating, and also for light collection. And we use this light for bringing light inside the room through the fiber. So you can see in a small room, about 10 feet by 10 feet room is illuminated by this fiber light coming from sunlight. With this system, this is what we are working. So we are very much interested in the rooftop itself. You can see huge amount of light is basically coupled to the fiber. Apart from that, we are also heating the water very, very efficiently. So a combined system was developed. And then this is a new kind of solar simulator we are concentrator we are making. What we call is basically luminescent solar concentrator. So that will be useful for agriculture purpose for making rooftop. And we have made a huge one. about 20 centimeter by 20, so something like 20 centimeter by 20 centimeter large luminescent solar concentrator we have made. And we all these work has been patented, and also some part of it is basically published in journals. This is basically for solar energy, and this is for cancer detection. So we have been working for the last 3.5 years with the AIIMS hospital for developing this multimodal cancer detection in real time during intraoperative procedure of breast cancer and oral cancer. So this is our field portable device, which is comprising multimodal. Basically, it is having ultraviolet light, blue light, that too specific, not any blue light, not any ultraviolet, specific ultraviolet, specific blue light. This particular setup is used now in the AIIMS hospital breast cancer surgery for finding the tumor margin detection, and it gives you spectroscopy, imaging, everything, and microscopy, because it is an endoscopic head. And this is used for oral cancer. It also gives you spectroscopy, ultraviolet based spectroscopy, blue fluorescence spectroscopy, imaging, and microscopy. And this is for cervix cancer. So all these units are being in place in the hospital, and these are some of the images taken by our device. And you can see that this our device with the naked eye, of course, this fluorescence guided surgery can be easily done with our device. And oral cancer kit is being used by these two doctor and this thing technician, and all our kit is being used, and you can do the point of care devices for AIIMS. And this technology is ready for 2-3 companies are now approaching us for real time detection of oral and breast cancer surgery. And of course, we are thinking of this one. So unique thing is spectroscopy. Spectroscopy comes directly from molecular level, interaction of electromagnetic wave with the molecules of the cancer cell like proteins, and they have the designated peak shift. And that is what is our unique thing. And the selectivity, sensitivity, and the repeatability is the most important for any sensor. Once if you don't take into account the selectivity, sensitivity, and repeatability, 3 parameters are very important for any sensor. If you are not taking care of those 3 parameters, then that sensor will never work. So our technique is totally spectroscopy, which is highly sensitive, highly specific, and highly repeatable. So that is why. So this is the final slide I would show you that apart from just counting the pollution monitoring particles, PM 2.5, PM 10, we could see this is a 3D structure of our holographic microscope, which is field portable. These are 3 units. One is the IIT Madras, one is here, and one is in the industrial unit about the Noida. So all these are giving you images. So this is how the images look. So those PM 2.5, these are all PM 2.5. The bigger one is basically cluster. So after sticky, basically this is a structure. So they are irregular shape. Most of them are circular, but there are irregular shape and a variety of things you can see here. And sometimes they come in bigger size. This is the at 0 time. When we start our holographic microscope in the rooftop, there is no pollution right now. Immediately at 0 minute, you could see nothing. And after 15 minutes, this is the deposition. You can see different shapes and different sizes. So you could also see the point PM1 smaller spots here. So those are more dangerous for our lungs, and variety of sizes, and for 15 minutes, 30 minutes, or 60 minutes. So this is, and from this image, we distribute the shape. We can identify what is the shape, how many particles for within 15 minutes, what was the shape of different shapes of the particle. Then we calculate the concentration and count. So what at present in the market, the device gives you is only count. PM 2.5 is this much, let's 240. But we can give you so many PM 2.5 were having this conical shape, cylindrical shape, spherical shape, and so many particles were below 2.5 PM1, so many PM 2.5 plus concentration. So all our software can calculate, and this is 1 hour on a very dusty roof environment in our rooftop in our laboratory. So you could see huge deposition on this one. So this is the first time in the world how to see the images of PM 2.5. And this is a heavy metal sampler we developed in our IIT and was transferred technology to the Envirotech, and they are basically now sampling, and particularly lead and all those heavy metals we are targeting on. And I would like to thank my PhD students, my collaborators from AIMS, and some of the work was done in collaboration with the Tromsø, Norway. And then thank you very much.
Thank you, Professor Mehta, for the elaborative and very informative talk on micro and nanoscopy. We can take a few questions from the panelists. If anybody has a question, they may ask, please.
Thank you so much, sir. I mean, it is like it's out of this world. It's amazing to listen to you and to know that how advanced these microscopic techniques have gone to image these live cells. So, quick question, sir: what kind of conditions do you maintain when you image these live cells?
Yeah, so we normally basically we make some cell culture and buffer solution, and we have a collaboration with here a biological department. They prepare sample for us. And normally samples are on a glass slide or a petri dish in some solution, so they will be always moving and in dynamic. So I've not shown you a lot of holographic work we have done. So we can measure the dynamic membrane fluctuation up to 10 nanometer fluctuation. So particularly combining the holographic concept with the nanoscopy, we can not only see, but also measure, and that both static, see measurement of thickness, height variation, morphology, refractive index, or let's say the oxyhemoglobin, dry mass, all these parameters are important for any biological specimen. So we are very, you can say in the forefront of this holographic microscopy. So cell culture is well in the live environment. So we don't have to freeze, we don't have to kill the cell, no fixing, nothing. Or moreover, suppose you can also put some whole blood, take a drop of blood, put on a glass slide, and immediately you can see. No. Sometimes we are not requiring any labeling also. So this is what.
The last one you showed in up to 60 minutes was on glass slides only.
Yeah.
And sir, these are all near field microscopes with like flat lenses and all.
Yeah. So very important point. All the microscope. So since all these microscopy, or you can say the nanoscopy, you can say nanoscopy and holographic microscope, because that lens, objective lens, the maximum limit is 1.4 numerical aperture. Nobody can make an objective lens larger numerical aperture than this. So all these nanoscopes and holographic microscopes, they use that standard lens only. So we have to play with the light field only. Means we have to build a holographic concept, we can build a structural animation, you can build the standing wave pattern kind of thing. So play remains only with the light. That's it. And secondly, we don't want the sample cell, because the optical nanoscopy is very important for biology. So sample should not be disturbed at all. It should be and measured as it is. This is why this optical nanoscopy has become important. Otherwise, this SEM, TM, AFM is powerful enough. You could see single atom level. But now these optical nanoscopes, the maximum, the minimum size they have shown in the STD microscope is 20 nanometer. So single molecule protein they can see.
Thank you so much, sir. I think others also have some questions.
Yeah, really excellent talk where you have shown that if you have the passion, you have the dedication, you can break the rules of the physics also. And that part basically the Nobel Prizes in the microscopy give that how the people has come at, especially when we are talking about the optical microscopy.
Right.
So now
thank you very much. But I just want to add here. So what happened, since 1962 till 1990, all the optical microscopists gave up. Well, the diffraction limit is this one, so nobody should work. Nobody should go beyond there. But there are some scientists who think differently. Then there's nothing impossible.
That's what basically we taught the student at lambda by 4 is your maximum resolution, you can read the limit you can get. But with this double beam microscopy, all this the participant has seen that you have the passion, you have the noble idea, you can create the history. And especially the 2014 was such a year when the Nobel Prize was given to the both Nobel Prize in physics and chemistry was given to the light discovery only. In physics, it was for the LED, and for chemistry, it was for the fluorescent microscopy.
Important.
So,
very good.
So that was the era when we have got all these Nobel Prizes. So really excellent talk. And I appreciate that India is not behind, especially the leader like you is making the step forward to match with the international standard. And very soon we are able to see the Make in India system, which is going to be exported outer world. So thank you very much for really excellent talk.
So I would like just add here, Professor Sinaji, our cancer detection system is low cost compared to anything outside. Right now, all the hospitals think that any equipment they would rely or they believe is coming from either America or Germany. We have basically hit the heart. That is basically by combining the spectroscopy and Raman spectroscopy. The Americans and Western countries also will be using the same technique. We are also using the same technique. We'll also detect same molecule. They will also detect same molecule. Hence, there is a possibility in future that our technique can basically be used in this.
Yeah, with the Make in India initiative, I hope that very soon we are in the process to export this product, at least not to the developed country, to the developing countries.
Right. We hope so. We are hoping.
Please, Robin, you can take the question, please.
Okay, any other question from the panelist?
Thank you so much, sir, for such a nice talk. So what will be the approximately cost of this optical nanoscopy?
So the one which is built in Germany, it is about 2-3 crores. Our system will be something like 40 to 60 lakhs.
Okay, much less than that.
Yeah, much less than that.
It's really nice. So if you can go for this nanomaterial characterization by this, nothing like that.
Yes,
instead possible. Of electron microscopy.
Right. Possible.
Thank you so much. Thank you.
Advantage with the optical is that you need not to make any specific sample preparation. That is an added advantage, like atomic force microscopy. So any question from audience?
Okay, so if there is no further question, then let us thank Dr. Mehta for his wonderful lecture. Thank you, sir. Thank you very much.
Okay, thank you very much. Thank you, organizers. I'm very happy to share my knowledge to all you Nanotechnology group and whoever have attended this one. So most welcome anytime in IIT, and I'm here. And half of time I spend in the rooftop of our building for solar sunlight harvesting. So I am also having the passion that lot of energy is being wasted outside, and we should utilize that. That's my next dream.
That's what basically the way you have shown that the light using the optical fiber can be transferred to a room.
Right.
So basically, we are going to, if we adopt that process, probably we are going to minimize the energy consumption at least in the daytime, because you see where the many people are the light in that way.
Correct. You're correct.
Hopefully, with this such kind of the innovations, we are able to save the energy for our next generation, and India will be going to be energy independent in coming few years with such kind of the discovery. Thank you, Professor Mehta, once again, and we look forward for such more lecture to our students during the this academic session. Thank you.
Okay, welcome.
Thank you.
Okay, namaskar.
Yes, thank you, everyone. Thank you to all the speakers, and thank you to the coordinators of this session, Dr. Robin Kumar, and thank you to our smart my coordinator, Mr. Rohit Sharma. Thank you for handling the entire session. And I think so we should now break for the lunch.
Yes,
And
I will.
yes, okay. So you can announce for the lunch. Meanwhile, is Dr. Huda with us? Do you really want to
He
check
was here.
whether you're visible or
He was
not?
here. No, he was here, and he has shown his face also. So probably he is able to join.
Okay, fine. Then Rohit, you can announce the lunch hour and
Okay, ma'am, I will do that. So with this, our morning session has come to end. I once again thanks everyone for their patience and being a part of this workshop. It's a kind reminder to the participants to take an assessment which was conducted at the end of the session. So the links will be shown in the chat box. Kindly attempt the question and have hope you will enjoy this. So thank you for your patience. Let's take a quick lunch break and meet again at 2 p.m. Thank you, everyone.
Thank you all. See you at the 2 p.m. sharp.
Good afternoon, sir.
Good afternoon, Pooja. You are all ready? All set?
Yes, sir.
Dr. Deka, can you hear me?
Yeah, I can hear you.
So just see if you're able to share. IT support, can you give sharing support to Dr. Deka?
Yeah, it is there already.
Okay.
Yeah, can you see my slides?
Yes. So will you be presenting in PDF? So can you get rid of the side portion?
Yeah, I do not have this animation here.
Okay.
Side person, okay. No, I can make it first. Is it okay?
Yes. This is okay. And your video, just see if you're able to turn on your camera.
Sure.
Yes, you're visible. Welcome.
Thank you.
So we'll start at 2 p.m.
Good afternoon, Dr. Deka.
Good afternoon, sir.
How are you?
I'm good. Thank you.
Thank you for the accepting our invitation and agree to deliver the talk in very short notice.
It's my pleasure, sir.
So who is the next? Already 2 p.m. So let's start.
Dr. Deka is starting this session. He'll begin the first talk and then followed by Dr. Bipin Gupta and Dr. Manish Huda.
Okay. Pooja, start please.
Okay, sir. Welcome back, everyone. After a short lunch break, I, Pooja Bhattacharya, welcome all of you to the second technical session of the day, day 3, Nano Era. The faculty coordinator for this session will be Dr. Sumant Upadhyay. The first talk of the technical session will be delivered by Dr. Shashanko Deka. Dr. Shashanko Deka is an associate professor in the Department of Chemistry, University of Delhi. He received his master's degree in chemistry from Guwahati University, Guwahati in 2001 and a PhD degree from the National Chemical Laboratory, NCL Pune in 2007. He then moved for his postdoctoral research to the National Nanotechnology Laboratory, NNL, CNR INFM, Lecce, Italy, and the Italian Institute of Technology, IIT Genova, Italy. He has been awarded the TMS Foundation Sriram Arora Award by the Minerals, Metals and Materials Society, TMS, Warrendale, USA, DAE, BRNS, Young Scientist Research Award, RSC Best Oral Talk Award, Institute of Physics, IOP, UK Best Cited Paper India Award. Dr. Deka has published more than 65 research papers in several international peer-reviewed journals. He has successfully handled several extramural research projects for DST, CSIR, SARB, SARB, DBT, DAE, etc. His current research interest deals with synthetic nanochemistry, multifunctional hybrid nanocrystals, noble nanocatalyst for energy research, and nanomaterials for energy storage. Today, he will deliver his valuable insights on the usefulness of nanostructured materials in energy conversion and storage. On this note, please join me in welcoming Dr. Shashanko Deka. The virtual platform is all yours, sir, and you have 45 minutes to deliver your talk, followed by a question answer round of 10 to 15 minutes. My humble request to you to please restrict the talk in the timeline. Thank you, sir. Stage is all yours.
Okay, thank you. Thank you for the introduction, and very good afternoon to all of you. Today I'm delivering this talk on usefulness of nanostructured materials in energy conversion and storage. So, as the theme of the workshop is on nano era nanotechnology for global sustainability, so this energy conversion and energy storage is also a part of that, the global sustainability. So therefore I choose this topic, and that in my lab actually what we do, this is nanochemistry laboratory. We do mainly synthetic nanochemistry. We are from chemistry background. We do a lot of different kind of synthesis to get 0D, 1D, 2D, etc. complexes, nanoparticles. We do their characterization, and we try to do some application as part of quantum dots, supercapacitor, and other part, as I said, that is the sustainability part, that is the water splitting for the hydrogen generation and oxygen generation. Okay, so as we discuss about the sustainability, global sustainability. So there are mainly 17 main goals. Out of that, what we are discussing, that is the number 7, that is the affordable and clean energy, because that is one of the very important part for the sustainable development. So in this way, so if we go for the affordable and clean energy, what is our task? That this sustainable health and care system, that is a part of the clean sustainable energy, and that is a combination of the social, environmental, and economic part of our daily life. So when we say the sustainable life, so we have to get clean energy, because without the clean energy we'll get a lot of population, and this thing nowadays it is taught in the school curriculum also, that we should produce less carbon footprint, less carbon dioxide greenhouse gases. So for that, as I say, one of the way of sustainability is the use of safe and clean fuel. That is the energy to reduce pollution, reduce carbon footprint, and reduce greenhouse gas. And if we see this slide here, we can see what are the safest and cleanest source of energy. If we see this list, and we know that coal is the greatly used all over the world, then oil, the natural gas, biomass. And if you see the bottom part, solar, wind, nuclear, and hydropower. Out of that, if we leave the nuclear part, then the hydropower, wind, and solar. Here we can see on the right side, this is only 5 tons or 4 tons greenhouse gases emitted from this process. However, in case of coal or oil, we can see 820 or 720 tons of carbon dioxide is produced. On the right side, you can see the debt related to each of these event or each of these energy sources. And this data you can see in our world in data organization. Okay. And then further, if we see that what is the share of electricity produced by source, and as we discussed in the previous slide, these are the different kind of sources, and from that, this is the share of electricity. Still, if this is 2002 data and this is 2019 data, from this you can see still in 2019 we are using coal mainly, coal and gas, whatever the natural gas we are getting, and still you can see that means we are still producing a lot of carbon dioxide. And you know, using of carbon dioxide gives us a lot of pollution, then it is still we are having a lot of carbon footprints, and we are not able to reduce that much of greenhouse affecting gases. But one positive point is that, as reported by U.S. Energy Information Administration, that renewable energies or renewables will collectively increase by 49% of global electricity generation by 2050. Now, if we see this data, what we found that the positive thing is that if it is a comparison from 1985 to 2020, that this share of renewable energy, it is increasing, and fossil fuel, it is overall it is remains same, but still you can see renewable energy part is increasing. That is a positive thing. So what we learned that, so we should use renewable energy sources or renewable energy to get the electricity or get the energy, and by that way we can reduce carbon footprint, reduce carbon dioxide, and reduce pollution, and that we can get clean energy. So that is the goal of the sustainable development or global sustainability. So there are many types of renewable energies. I want to say that, as it is asked that there are that the audience level is different, as it is a bachelor, postgraduate, research scholar, faculty. So I have tried to put general thing also in between, because then it will be easier for the newcomer to understand. So there are 5-6 types of renewable energies: biomass, hydropower. All of us know about all these things. Hydropower, that is a dam. From the dam we get the electricity. Then wind power, that is the turbine from this we get near the seashore. Then solar energy, the solar panels, geothermal energy, and biomass. So these are the type of renewable energies, but from where we can get clean energy, clean electricity, where no say fuel, carbon fuel is used to get those electricity. Now, out of this 5, so one more energy is nowadays it is say discussed. So hydrogen energy. Actually, hydrogen is not a fuel. Okay, it is not a fuel. It is an energy carrier only. But for general term, we use hydrogen as gas, hydrogen as a fuel, or hydrogen as energy. So when we say that hydrogen will be also a renewable energy, green energy, when the hydrogen is produced from renewable energy sources, means hydrogen is produced by many factors. We will discuss all these things in the next slides. But when this hydrogen is produced from, say, wind power, okay, or it is from solar panel, that the energy source to produce the hydrogen is those things, say wind power or solar power, then only we can call those hydrogen as a or the clean energy source. Okay, to understand more, we can see this one. So as we said that this, from this slide you can see hydrogen is produced from different sources. Then this hydrogen gas is used in the fuel cell car, or in industry, or in domestic purpose also. Means the electricity we are using, which is produced from hydrogen gas. And in this slide, we can see that this is the global demand for pure hydrogen from 1975 to 2018 data. And you can see that it is increasing from 1975 to 2018. You can see it is almost 75 ton of hydrogen is produced or demanded, as against 20 from 1975. And out of that, you can see the major share is coming from refining, means that hydrogen is produced from the gas or from the oil that is in the refinery. Then other part is produced from ammonia, and the remaining part is only from the renewable sources. And out of these 3 different sources of hydrogen, that passenger car, this is using the hydrogen produced mainly from the renewable sources. As I said, that hydrogen is produced from renewable sources, mean the electricity used to produce the hydrogen is from the wind power or from a solar panel mainly. And what are the other parts where we use hydrogen gas? That is vehicle refueling stations, buses, electrolyzer, trucks, building, heat and power, etc. and power generation. There are many applications of hydrogen gas. So hydrogen production caused by a production source, you can see that if we produce the hydrogen from natural gas or coal or natural gas with carbon capture, so the cost is less. And that's why if you go back to this slide, you can see the major source of hydrogen gas still remain refining, because the cost of the production of hydrogen is very less in these cases. However, when we go for renewable sources to produce hydrogen, the cost become very high. Okay, so what we learned about that hydrogen is also a say we can say energy, but it is energy carrier. And when we have the hydrogen gas, when we produce the hydrogen gas, so how it is utilized? We utilize it is in a fuel cell. A fuel cell is a cell where hydrogen gas, where we react hydrogen gas and oxygen gas to produce electricity, and we get water as the byproduct. Now that is the clean energy. Why people are looking for it? Why people are spending billions of dollars or billions of rupees for this kind of research or to get this kind of output? You can see this is a fuel cell where from one side we are giving hydrogen gas, from the other side we are getting oxygen from the nature, from the air. They are reacting in the electrode, okay, electrolyte interface, and then electricity is means electrons are produced, that is passing through the circuit, that is giving electricity, and water is out as the byproduct. So no other greenhouse gas is produced from this process. So I hope now it is understandable that why hydrogen is called a green energy source. So why hydrogen is important, as we discussed till now, we found a lot of things, and few more points here I want to share. That hydrogen is a zero emission fuel, and by virtue it is the highest gravimetric energy density. It contains highest gravimetric energy density of any known fuel. We have a lot of fuel: petrol, diesel, kerosene, and all these things, LPG, CNG. But out of that, hydrogen is best because of the gravimetric energy density. Means for same amount of hydrogen, we get more energy from hydrogen. Same amount of volume, we get volume or weight, we get more energy from hydrogen than the rest of the fuel. Zero emission of carbon dioxide. You have seen from the fuel cell reactions that there is no carbon dioxide output. Then it is environmentally safe. Then good recycling performance. And if you see here, these are the ways by which we can get hydrogen gas. To understand this diagram, we can see this one: hydrogen production reactions. There are four ways, as already few of them already we discussed. That this is the steam methane reforming, that is from the refining, and this is the coal gasification. This we are getting from these two parts here. These two parts, refining and ammonia. And other two, which is from the renewable source, we can get, that is the water electrolysis and water photocatalysis. Okay, so this, which is shown inside the red rectangle, you can see that if we get hydrogen from these two processes, that is the water electrolysis and water photocatalysis, then that is called the renewable energy, renewable hydrogen. And now we can see here, this hydrogen we can get from these different ways. And one more we see, that is the biomass conversion. Biomass conversion is also very good to get clean hydrogen. So how these things work? So first one is that solar energy driven artificial photosynthesis. So this is just mimicking the things what is happening on the plant leaf. So plant leaf, in that one, that it takes the solar energy and the carbon dioxide and water is reacted to get the product. And artificial photosynthesis, what is done, that the same water now it is splitted and it is broken into hydrogen and oxygen. Okay, the energy is equivalent in both process. So this is called artificial photosynthesis, and this is a simple diagram we can get everywhere. This is for a splitting of water molecule by artificial photosynthesis, or it is called photocatalytic reaction. When we have a catalyst here, a particle, I'm still not using the nano thing here. So that it is a semiconductor particle, and it contains some active sites, that is the metal deposition. So when we irradiate the system with light, so the semiconductor, it receives the light, so there is a generation of electron and holes, that is called the exciton generation. And because of that, we have to separate the electron and holes, and then we have the splitting of the water. So one, that whole part is going for the oxygen part, and electron is going with the hydrogen ion to give you hydrogen gas. And this is the simplest way by which we can explain the photocatalytic reaction. This is this continuation of the previous slide. Here you can see that when we have the separation of hole of the electron, that proton is transferred, that it reacts with the oxygen, and then finally the proton is reacting with the electron to give us hydrogen gas, and holes are reacting with the oxygen ion, or it can call water, to give you oxygen. But lot of problems are there. The reactions are not so easy. We'll discuss in the later sections. And this is a simple mechanism step. You can see this is from our reaction. So this is a semiconductor, graphite carbon nitride. When we irradiate with light, we can see the generation of hole and electrons. The holes are reacting. The electrons are reacting with the proton generated during the reaction. It gives us hydrogen gas, and the holes, they are reacting with the water to give us oxygen gas. And one more process, that is called photoelectrochemical water splitting, which is slightly different from photocatalytic reaction. So photocatalytic, in this one, apart from the light part, we are doing the water splitting reaction under light, but using potential bias, potential difference. So we have the semiconductors. One part is photoanode, one part is photocathode, and it is irradiated with radiation, and the reaction happens at the we get the hydrogen in the cathode and oxygen in the anode. And because of the presence of this electric means bias voltage, we are getting more hydrogen gas in this way. Then the last one is, I'm going back here again. So as I said, water electrocatalysis and water photocatalysis. So photocatalysis, two parts I discussed, that is the photocatalysis and photoelectrochemical reaction. The other part is called electrocatalytic water splitting. So in this way, what is called, there are two parts. One is called hydrogen evaluation reaction, other part is oxygen evaluation reaction. So the reaction is done, means there used to be, one is anode, one is cathode, one is positive part, one is negative part, and we apply it is an electrochemical cell, and electricity or current is given to the cell, and because of some voltage difference, or that I will discuss in the next slide, so the water is splitted, and that gives us oxygen and hydrogen. Okay, so that is the thing, that is the way how we can get hydrogen gas. Now I come back to now our Indian scenario. This is a recent newspaper cutting where it is, the title was the running cars on hydrogen. What is India's national hydrogen mission? So our Delhi became the first Indian city to operate buses running on hydrogen spike, or it is hydrogen max CNG gas. Okay, it was there in the news, and they wanted to see what is the fuel efficiency, how much waste gas is produced during this one. And other thing, what we know from this one, that South Korea and Japan especially are focused on moving their automotive markets to hydrogen and the potential of the fuel cell. So that means we understood that hydrogen gas is really important. Our Indian government is also taking care of that because they are interested, because we know how our Delhi is polluted, and our government actually there are sections, scientific sections, they think that they thought that if we can replace our at least Indian vehicle, our daily vehicles means with hydrogen spiked CNG, or if we can produce more, we can run more cars on hydrogen in Delhi, so we can reduce the pollution level. Okay, already EV vehicles are there, but still in some cases this hydrogen spike CNG are better than EV. So what we learned till now from the presentation, that we know about the sustainability, that we have to get clean energy to get less pollution. Then we learn about clean and safe energy resources. These are the points we have learned till now. Then we know hydrogen. We know about the hydrogen. We learn why hydrogen is important, how important it is. Then also we learn what are the procedure followed for the production of hydrogen gas. There are 4 procedures. Out of that, 2 are called renewable sources, renewable way to get hydrogen gas. That is the photocatalytic and electric catalytic. So this thing I hope we learn from this previous slide. Now we go for the main topic of the workshop, that is the nanotechnology for sustainability. So what in that way, from my work, what we can show that we can do the synthesis of nanoparticle, we can do characterization, we can check the properties, and we can do the application of this nanomaterial for to get clean source of energy. Okay, that is the way how we can contribute for the sustainable development. So as we know, there are a lot of application of the nanoparticles, from biomedical to environmental remediation, from construction to food packaging, then electronics to renewable energy. So these are the different examples, but we can find more examples in the literature, in the market, if we check the literature. And this is one slide what we can see that. What we can do the process development, that is the synthesis of nanoparticle, then property characterization. Then we can use this nanoparticle in different way. If we see the right top corner, that is the environmental part, where carbon dioxide capture and conversion, that is the reduction of carbon dioxide to different commodity useful materials are there. Nowadays it is going on. Then use of this nanoparticle to get hydrogen gas, make better batteries, make better supercapacitor, capacitor, etc. So I will try to focus few of the things in my talk. So as all of you are doing nano, so we know how small a nanometer is. So a small 1 nanometer, in 1 nanometer we can contain, say, 1 water molecule, 1 hydrogen, 1 nitrogen, 1 oxygen. So small it is. This 1 nanometer, that is not into the scale, but this is for the imagination. So how small it is. And we always say nanoparticles are very good, it has high surface area, but because of the high surface area, actually what we get for the application part, because because if you see, if you have seen all this talks from first day, we see we are all using nanomaterial. But why these nanomaterials are so important? Say for example, catalytic. Not only catalytic, there are a lot of other parts also. Why it is? So I'm giving one simple example here to make for the understanding of the students. So when people ask that why nanoparticles are good, we always say it is having high surface area. But because of the high surface area, what we get? Actually, what we get lot of unsaturated atoms at the surface. Okay, a lot of dangling bonds, means lot of free electrons at the surface. So to that, you just consider this slide and do a simple calculation. What you do, you take 1 nanometer cube and 1 centimeter cube. Okay, so in both cases, you first calculate the volume. Very easy. These are the equations are there, and then you calculate total number of surface atom in both cases. Okay, and you take the total ratio of surface to total atom. Means total atom means it is the bulk inside the cube, and the surface is surface. Okay, in the 1 centimeter cube, you will get the ratio is 6 into 10 to the minus 8. But in case of 1 centimeter, 1 nanometer particle, this is very small, this is 0.6. That means in a 1 nanometer particle, we have 10 to the power 8 times more atoms at the surface. So these atoms are at the surface, they are free atom. They have dangling bonds, or we could say unsaturated surface atoms. So that's why they become very reactive. There are more other advantages of becoming a nanoparticle, high surface area, as we said, and because of that, we have a lot of unsaturated surface atoms, dangling bonds, active sites. Then we can get porous structure for intercalation reaction. Then we can construct preferred facets. Then we can tune the band gap for the semiconductor, etc., etc., etc. Okay, these are the advantages of being nanoparticle, and we can use these nanoparticles for catalysis and energy sector. So based on that, we have done a few work in our lab, and as I said, that because of the nanoparticle property only, we can construct different facets, because all these facets, as we are chemists, so we know that a crystalline material, it has H-scale planes, then the crystal facets. So few facets, for every crystal, that few facets are there. If you see the XRD pattern, you will see few of the peaks are very highly intense, others are not. Those intense peak, mainly they have high electron density. Okay, they have become more reactive, or sometimes it is opposite also. They are become inactive also. So from theoretical DFT calculation, we come to know that few of the crystalline phases for crystalline material, they are highly reactive, and by nanocrystal nanochemistry, we can actually do nano engineering, and we can grow a nanoparticle in that way that few of the required facets or surface are exposed, and that's give lot of reactions. So these are Etherium oxide, nanocube, nanoparticle, and nanocube. In both of these papers, we prepared this nanoparticle with 110 and 100 facets, which gave us lot of good activity, say 100% conversion and 99% selectivity for this paraxylene to terephthalic acid conversion. And these are characterized by extensive studies where from the high resolution TM we found that these are only 100 and 110 surface exposed nanocrystals, and these because of the surface exposure, and they have lot of defects, and we could able to calculate the defects. You can see it is 1.42 into 10 to the power 21 per centimeter the number of defects we have calculated, and those gives us lot of good reactions. And similar one more type, this is a cerium oxide nano rods. So as we said, we get prepared facets, and we can do lot of organic transformation reaction and with high activity. Furthermore, not only oxides, we could prepare alloy nanoparticle also with defect or without defect, and we can nicely actually do the engineering to get the different facets for the different kind of catalytic reactions. So this is silver alloy nickel, and this is one core graded alloy shell nanostructure. So what we learned that this nanoparticle definitely they have high surface area and all this part, and it has porous structure, then tunable band gap. Now what we do that when we do a lot of synthesis as a nanochemist, people do, so we can get different kind of nano shapes. You know that is the 0D, 1D, 2D. That is based on the quantum confinement of the nanoparticle. Okay, so how you can see the quantum mechanical calculations and quantum calculation, and from that you can find out that if it is 0D, it will confine in all direction. If it is 1D, only one dimension. In 2D, it is the confinement in 2 dimensions. And each of different this morphology shape, they have different advantages. So now we come to the water splitting part, that is the sustainable energy. So these are the four reactions actually. How to split water, because already we discussed that water is split to water, oxygen and hydrogen, right? So we'll not go back to that discussion again. So I said that either by electrocatalytic or photocatalytic, we split the water to get hydrogen gas. But the main point is that when we split one water molecule, that to get hydrogen, getting hydrogen is very easier. That is at 0 volt we can get. But to completely to that, but you know that, see, hydrogen and oxygen, they only give water. Means if we break oxygen water, then we get hydrogen and oxygen. That means we have to get oxygen gas also at the same time. But getting the oxygen gas, that is the most difficult part of the reaction. That is 4 electron reaction. There is a sluggish kinetic, so it requires 1.23 voltage. Okay, versus reversible hydrogen electron. Or we can say to break one water molecule, we need 1.23 volt. That is very high voltage actually. Hydrogen we can get 0 voltage. Okay, so basically most of the researchers they are trying to get some good catalysis where we can do oxygen evolution reaction easily. So one term here, it is called overpotential. Overpotential is that there is a potential difference between the theoretical potential and the actual potential of the material. So we need a very low overpotential material for this kind of reaction. So these are different kind of mechanism put forwarded. So Volmer, Haveski, and Tafel mechanism, they are based on how the hydrogen ion or hydroxyl ion they are absorbed on the surface of the catalyst, and they are calculated from the Tafel's law. So these are few of the recent reports they are giving. Say it is came in science. This is in energy and mineral science, that these people produce lot of good catalysts, either photocatalyst or electrocatalyst to get this hydrogen gas and or oxygen gas in laboratory condition. Now I come to my work. So I hope I already gave some basic idea about the basic. I gave some idea about the basic things about the hydrogen evolution, about the oxygen evolution, about the nanomaterial application. Now I simply go to my work. So this is one work in 2017, one of the most downloaded work. So we prepared copper cobalt sulfide nanosheet using copper nitrate, cobalt nitrate, and thiourea by a hydrothermal synthesis method. The method was very, very simple. We have characterized and we found these are nanosheets, and actually they are forming open hierarchical structure if you see under the FECM. And from the AFM, we found that atomic force microscopy that these nanosheets are around 60 nanometer thick. Then after all calibration, we made this electrocatalytic study. So we made the three electrode this one OER oxygen evolution reaction study. We made a working electrode by making the catalyst. Catalyst means copper cobalt sulfide. Then solvent, then Nephron. Nephron is the binder. We made a dispersion ink. Then we put on this glassy carbon electrode, that is the working electrode. Then platinum wire is a counter electrode, and silver chloride is a reference electrode. And see, these are the data we got. That is the result. Actually, our sample, it was showing as it at that time in 2017 12 hours efficiency, means our current was exactly same for 12 hours. There is no change. And these are the LSB cycle. You can see in the first cycle, after 5,000 cycle, after 10,000 cycle, it is similar and it is same. It is superimposing, and the over potential, that is the potential required for our material, and the that is the difference between our material and the theoretical. The theoretical is 1.23, and our is you just add 0.310 volt to that one. So that is by our material. So at that time, this is one of the best material. And then it shows that your turnover frequency is also very good. So this is the study. You can see when we have done the electrocatalytic study, we can see the bubbling. That is the oxygen in one side and hydrogen in one side. Then further, we have done a lot of study to find what is the reason behind this excellent oxygen evaluation reaction. We found that from the XPS, we found that there is that cobalt 3 plus is the high intensity cobalt 3 plus, means cobalt 3 plus is more. This is a spinel structure actually. And there is interaction of copper and cobalt with the oxygen and sulfur. And from EPR, we found that this cobalt 2 signature is absent there in around 3,500 gauge, the signal line. And that is actually showing it is a cobalt 3 plus is more with the high spin state. So to further make it this one, I will come to this slide. It will be better to understand. So this copper cobalt sulfide is a mixed normal spinel. And some theoretical study, we found that octahedral we know that in spinel there are two sides. One is octahedral, one is tetrahedral. So in general, octahedral sides of spinels are catalytically active. So from our experience, we found that cobalt 3 is there, which is in the octahedral side in a normal spinel. Then from EPR study, we found that the high spin state of copper 3 plus, that is there in the form of ferromagnetic interaction we found. So it is a T2Z4 high spin state of the cobalt. So that's why it was showing highly reactive OER oxygen evolution reaction. So further, one more material prepared, that is a CO3 as per hollow nanoparticles using a high temperature colloidal synthesis method. We have used 5 ml of OLM, olealamine, then 0.1 gram of topo triethyl phosphate oxide. We did vacuum, then nitrogen gas, and then we injected sulfur in olealamine. And we got very nice spherical nanoparticle, but those are hollow nanoparticles. It is a cobalt sulfide. The holes are happened because of the Kindle effect. And these nanoparticles, beautiful nanoparticles, hollow nanoparticles, they are found to be a robust and hollow, low-cost pH universal oxygen evolution catalyst. So what is that? If you remember, I have shown here that oxygen evolution reaction, there are mainly the reactions are done in alkaline and acidic media. And in alkaline and acidic media, the reactions are easy because we have either hydrogen ion or we have hydroxyl ion. But in neutral pH, at pH 7, these reactions are not so easy. You can see the potential is very high here. But because of our this structure of the nanomaterial and few characteristics, I will discuss that one. It was showing oxygen evolution in KOH, in sulfuric acid, and in PBS. This is buffer solution pH 7. Okay, and when we try to find out the reason, and we have done XPS, EPR, and this electrochemical active surface area studies, we found these are the factors. We are not going to read all of them. That one is the one important factor is that there is a lot of these species, cobalt OOH species are formed, and that is because of the high spin state of cobalt 3+. Then other thing is that this material, it has ECSA, electrochemically active surface area. It's very high, that is 58.75 centimeters square. So and one is that high roughness factor, that is also very important to have lot of surface active sites. See, what is ECA? Is ECSA. ECA is a electrochemically active surface area. We always say nanoparticles are having very high surface area, but all the surface area, it may not be electrochemically active because we may have 100 meters square per gram, but the entire 100 meters square per gram area may not be chemically active. So it should be electrocatalytically active or catalytically active. And in this, our material was very active electrochemically. It has lot of sites. So that's why we got very good activity. So this is another study where we have prepared PDSN nanoparticle, alloy nanoparticle. This is for hydrogen evaluation reaction, definitely. So it was a very simple synthesis. We have first prepared, I'm just discussing the mechanism. So we have first prepared tin nanoparticle. We just reduce the tin salt with sodium borohydride, and then hydrogen hydride, and then we get tin nanoparticle. This is a tin nanoparticle. Then we added palladium chloride. Okay, what happened? Still, since the reducing agent was there, palladium, there is a formation of palladium nanoparticle at the surface of the tin nanoparticle. Then we put the reaction in hydrothermal autoclave. Then what happened? There is a self-tapling method followed by autogalvanic replacement, because the potential, the reduction potential of tin and palladium is little bit different. And because of that, there used to be an autogalvanic replacement process. So the tin from the core is fused and come to the surface, and it forms an alloy layer, and then there is a formation of the cavity. And since it is a metal alloy, so there used to be lot of synergistic coupling between the palladium and tin, and because of that we got very good catalytic activity and we got very high current density. And this matter is with this material we can go up to 48 studied hours. Okay, no deformation, no deactivation during this course of study. So I come to the photocatalytic part. So as we know that semiconductors are very good for the photocatalytic reactions. But the main problem is that the recombination of hole and the electrons. So that is the excitons, right? So if it's a semiconductor, if inside a semiconductor, if hole and electrons are recombined, we get generally radiation. Or sometimes it may be irradiative recombination also. But we don't want any recombination, because if recombination happens, then we cannot separate the electrons, and we need the electrons to reduce the hydrogen ion to hydrogen gas. Okay, so people use titanium oxide mainly in this study, but there are some disadvantages of titanium oxide, because there is one you can see in the bold metal hydride formation inside the lattice. That is called hydrogen environment. And because of that, there used to be degradation of catalytic activity. So we found in our study that metal sulfide will be very good. That is a copper sulfide, what we have shown in the electrocatalytic material. So same material, we for the first time in literature we studied as a photocatalytic activity, and we found that it is showing very good catalytic activity. We can see it is 25.9 millimole per hour per gram of hydrogen evolution, that is equivalent to 633 milliliter per gram. So that was very good activity hydrogen production. And why? Because why? And we have to study that also, because just our focus should not be only the synthesis part or only some application. We should know what is the reason behind that. So we have started a lot of optical studies. We from Kubelka-Monk plot we calculated the exact band gap for the first time. It is 2.24 electron volt. That is very good for visible light absorption. Then from Motzkotky plot, we find out that it is a p-type semiconductor because the slope is on the negative side. Then we calculated from this plot the valence band. The valence band is 1.07 electron volt. Okay, and from this panel, we know the band gap is 2.24 electron volt. So just subtract it, that we can get the conduction band of this material. So conduction band, you can see minus 1.17 electron volt. That is very good for hydrogen emission. Okay, then from valence band XPS, we found the Fermi level. The Fermi level is 0.47 electron volt. And then from this Motzkotky law equation, we calculated the number of the donor concentration. You can see donor concentration is very, very high, 7.2 into 10^28. So these studies that gives us the information that this material, copper sulfide, is it has a lot of active sites. It has a lot of donor concentration. The band age means conduction band position, valence position is unique to get very good electrons that are going for the hydrogen evolution reaction. That is the reduction of the hydrogen gas with this kind of mechanism. So this is the actually what already we discussed about this one. So I think I will not discuss in the photocatalytic part more. I will in between, I just want to show I will run through this one little bit about the photocatalytic, good photocatalytic activity by our nitrogen rich polymeric carbon nitride nanosheets. So carbon nitride is a very good material. It has a nanosheet structure by nature itself, and it is a combination of two units. One is called heptazine, one is called melamine, and it is a if you read this one, it's a novel metal-free pi-conjugated semiconductor polymeric constructed from two-dimensional sheets. It has a structure like graphene. So it's a very good material. It is a band gap of 2.7 electron volt. So we prepared this material using a very simple synthesis method. It is called direct thermal polymerization. We take melamine, ammonium carbonate, and we just heat it at high temperature, and then we etch it. We got very good graphitic carbon nitride, and you can see generally graphitic carbon nitride, it is C3N4. By definition it is Z3N4 is main formula, but what we written here ZC3N4.8. So that is the means that is a lot of extra nitrogen, and we have calculated using the CHN analysis and EDEX analysis. Okay, the thickness of the nanosheet is ultrafine, 5 nanometer thickness, and it gives a very good activity, 2500 micromole per hour per gram. Okay, I will finish the talk. This is 5 minutes. Then one more material here with C3N4 only. It is again showing good hydrogen evolution reaction. So these materials are good for sustainable development. So I'm going to the last few slides on the energy storage. So energy storage is also part of the sustainable development, clean energy. And we know about the battery, and one part is capacitor. And nowadays this new term is coming, supercapacitor. So supercapacitor is very good to store energy, electrical energy. There are differences between supercapacitors, their mechanisms, EDLC, pseudo, battery type based on their CV, their galvanostatic charge discharge mechanism. So we have started few work long back. We prepared cobalt oxide, and we found it is our earlier studies. We found those are very good for energy storage. Then we come for some device application. So I will finish just in 2 minutes. Okay, so this was in 2018. We prepared mixed metal oxide, nickel copper oxide, and from this material we prepared a cell device which can be good for 2000 cycles, and there is no deviation from the specific capacity you can see. And these are the characteristics data of the material, and this is the electrochemical data. Here you can see that material, it can store energy up to 10 minutes and there is no fading away. Just I'm coming to this last slide. So this is a recent paper, the super bending. It is a flexible supercapacitor. So flexible supercapacitor means nowadays these devices are coming. It is used in the mobile phone. It is used in the wearable clothes. And when we need energy, instant energy, we use these devices. So that supercapacitor, it has to be flexible. You can bend it, twist it in any direction, and it should be able to. So this is the synthesis scheme, and this is the new scheme we have developed. We made a new substrate as well as a new electrolyte also based on this EMM-IM-BF electrolyte, ionic liquid electrolyte. Okay, and this cell, this is the performance parameters. You can see these are the octahedral nanomet particle, and we can see this is the banding, the material. This is the hand of one of my student, Bindu, and these are the, you can see different banding condition. You can see the light, it is lighting after charging of each side. Okay, and these are GCT curve at different angle and time. And finally, this is a recent paper just published, and this is a copper cobalt layered double hydroxide nanosheets based polyhedrons for flexible supercapacitors. So we prepared hydroxide nanosheets, and one important takeaway point are there. This cycle, number of cycles, actually 20,000 cycles means five years lifespan of this cell. Just we are trying how to contact with the company or manufacturer, or means it is very difficult to collaborate. They are not interested on R&D, and we cannot do the manufacturing. That is the problem. Let's see how to solve this. And finally, I would like to thank my student Meenakshi, Kallan, Mukesh, Imani, Bindu, Ankur, and Lex for this wonderful work they have performed. Then my collaborator, Dr. Gopinath, Dr. Amar Das, Dr. S.A. Hasmi. And I would like to thank University of Delhi for different facility, for lab, for characterization facilities, then DST, then SCRB, 2 projects, then DST, Technology Mission Development, CSR, USIC, then DVT also, and BARC for funding, lot of funding. And this is my university on the left side. It is vice regal building. This is arts faculty. This is our stadium. On the right side, this is our department, and this is our chemistry department. And finally, I would like to thank all of you for your kind attention. Thank you.
Thank you so much, Dr. Deka, for the wonderful talk and mentioning us about the role of nanostructured materials in clean energy generation, basically hydrogen production, and also the role in supercapacitor applications.
Well,
so I would like to ask panelists if they have any questions to the speaker.
I have a question. Professor Deka, wonderful talk with wonderful publications.
Thank you, sir.
I want to know what is the thickness of cobalt copper substrate?
16 nanometer.
16 nanometers.
From 16, 1/6.
1/6. How many layers are there? One layer, how much thickness?
One layer, how much thickness? Yeah, actually, we have done the calculation. I don't remember. It is around 3 to 4 layers actually. 3 to 4 layers based on that our value, H-scale value, what is the thickness of the material. So it was 3 to 4 millimeter. And one more thing, I think related to your question, I can check one more thing, that that we can calculate means how much layer also required to cover the electron. Actually, that is a point asked by our reviewer also. So means when we do any kind of this kind of study, so we have to see how much material or layer is enough to cover the electron or glassy carbon electrode or that surface, substrate surface. Because if we put lot of material, what will happen? Resistance will increase, right? Conductivity will come down. So we have to know that thickness also.
Is thickness has any effect on its property?
Yes, it is there, because if we increase the thickness, a different thing will means it will vary based on the thickness.
Yes, I think that thickness can affect the band structure, band gap, which
yes,
you have calculated using one thing I would like to ask Dr. Deka is, like you showed graphitic carbon nitride with nitrogen, heavily doped nitrogen. What was the, what kind of effect do we look into this material?
Okay, well, so this nitrogen, so first thing is that where is the nitrogen? That is the thing, because as part of formula, we should have only C3 and 4. So we have done XPS studies, then EPR, a lot of all these studies we have done. Then what we found that and the DFT also, one recently published one paper, that we found that this nitrogen atoms, that excess nitrogen, they are on the ring of this melamine ring or heptazine ring. When they are at the surface, and as a means nitrogen is there, then hydrogen also means NHX. Okay, NHX. So they are at the surface of the material. So now I'm coming to your question. What is the effect? So because of this nitrogen, so there are many things. First thing is that band gap is reduced. So generally, when the nanoparticles are there, as per quantum confinement theory, band gap is always increased. But here in this case, band gap is reduced because this Z3 and 4, it's a pi conjugated band gap. So since we have a lot of lone pairs there, actually it's reduced the band gap. And then since amine group is there and hydrogen is the lone pair is there, and that is helping in the reduction of hydrogen ions. Sorry.
So is it creating any kind of defect in the band structure which you have calculated using DFT?
Yes.
In the valence band region or in the conduction band?
1 minute, I have to open. It is in the conduction band. Between conduction band and Fermi level.
Because I can see like in these carbon nitride structures, like I have just now finished my calculations on C2N. This is wholly nitrogenated graphene. Yeah. So in which we saw that this valence band is majorly composed of carbon and nitrogen both. Right. So I'm quite surprised to see that this nitrogen can help in getting or is giving you some other energy levels or defects in the conduction band. Because in that case, I think you have used this material for hydrogen evolution reactions.
If you permit me, I can show. Can I show, or my time will not be there? Or I can send you that one.
Yes. So, okay, sir. Okay.
Yeah, that is the case. Actually, this is one thing is that nitrogen. It is question is whether nitrogen is doped or nitrogen is on the surface. These two factors. And if you do the calculation, no, if you do the doping calculation, then you will get different thing. And if you presume that nitrogen is on the surface of the material, not as a doping, then you will get different calculation, different results.
Maybe in that case, you may have got higher energy values of your system using DFT calculation. But maybe I'm just presuming.
Yeah. And one more thing, that in XPS we found additional NH peak from XPS, and that is also one thing. Okay, so that is also there, NH peak.
Thank you, doctor.
Yeah, thank you.
Now we have any other questions from panelists?
Thank you, Dr. Deka. Thank you for accepting our invitation, and I congratulate you for your excellent publications. A quick question on supercapacitors. Like generally, we say that graphene is the most happening material for use in supercapacitors. So, as a general message, what would you like to say about that? Like, what other materials are mostly coming up in the form of a good and efficient supercapacitors with high specific capacitance?
See, as we see that there are two kinds of supercapacitor. One is EDLC. For EDLC, definitely graphene oxide, RGO, all carbon type material only. But for other part, if it is a pseudo capacitor part, we see. So it is nowadays all mainly metal hydroxides and metal oxides they are taking place. So If you see layered double hydroxide and nickel hydroxide, copper hydroxide, iron hydroxide, all these materials are very good. They are showing very good things.
I think there's a question in the question answer box.
Okay, I think we should take questions from the participants. So, Dr. Deka, the first question is, do heterostructure materials will be beneficial for HER reactions, and what criteria should a material to have be a good HER catalyst?
Yeah, I can read the question. Do heterostructure material will be beneficial? Yeah, it is. See, what do you mean by heterostructure? This is who asked. Rohit Sharma. Okay, heterostructure means when we say about nanomaterial, so heterostructure means we generally say it is a core cell material or say it is a hybrid material. Means one side we have one with cobalt oxide, it is attached to some cobalt and all this thing. Now, if you say, I don't know what you understood or what you meant by heterostructure, but if you go for that any kind of material, if it is a say, if it has to fulfill all those criteria what we discussed. See, a material means will not see few materials are good for hydrogen evolution, few materials are good for oxygen evolution, few materials good for supercapacitor, and few materials are good for both hydrogen and oxygen. So it depends on the material characteristics. So if it is a heterostructural material, it can show or you manage, so it depends on the material. And what criteria should a material to have a good HCR catalyst? I think we discussed this part. HCR catalyst to be a good catalyst, it should be a good conductor also. You should go for the volcano plot, where we see platinum is at the top. So platinum used to be the best catalyst in the world till now. And out of, if you see near the platinum, there are some other material which resembles the property of platinum. So those materials show very good. Now HCR you are asking, I do not know for photocatalytic or electrocatalytic, I cannot understand. But in general, you have to follow this. If it, I am answering, it is from the electrocatalytic part. So if it is electrocatalyst, you just go for the volcanic plot. You see there what are the property for platinum and good catalyst. You see that it has to be conducting. Insulation or insulator or semiconductors are not good for that one. Then also, if you go for some DFT papers, theoretical paper, you see that the material which have a optimum hydrogen absorption energy, that is around 52 millivolt, those materials are near plus minus few. Those metals are very good for HER. At the same time, it should have high surface electrochemically active surface area. It should have good surface area also. All these factors they have to follow.
Okay. Thank you, Dr. Deka. The next question, I think this is the last question. How do you see the future role of perovskites and organic solar cells as the renewable source for generation of hydrogen?
Yeah, actually, I don't know much about that because this perovskite solar cell, I never go for that because already enough for me in this site. So I cannot comment on that.
Okay, I think there are no more further questions. So let us thank Dr. Sasank Deka for his excellent talk. Thank you so much, Dr. Deka, for your enlightening talk, mainly on this hydrogen generation and supercapacitor applications. Thank you so much.
Yeah, thank you, and really, I'm honored to be part of this workshop, and really nice to meet all of you virtually. Thank you. Thanks for your invitation. I'll be here for some time. Yeah. Thank you. Thank you.
I think we should call our next speaker for this technical session. I request Pooja to please introduce the next speaker. Over to you, Pooja.
Pooja, you are muted.
Yes, ma'am. Am I audible?
Yes.
Thank you, sir. Our next speaker in this technical session is Dr. Bipin Kumar Gupta. Dr. Bipin Kumar Gupta is working as principal scientist in the Photonic Materials Metrology Subdivision, Advanced Materials and Device Metrology Division at CSIR National Physical Laboratory. He obtained his PhD degree from Benares Hindu University in 2004. Then he joined as lecturer at the Department of Physics at Lucknow University. Afterwards, he joined NPL as Scientist B in 2007. He spent 1 year at Rice University, USA as an IUSSTF fellow. His current research interest is focused on the development of luminescent material, bulk or nano, luminescent graphene quantum dots, and 2D new emerging material for application in luminescent security ink, security codes, optoelectronic devices, biological fluorescence labeling, fluorescence quenching, field emission displays, and luminomagnetic nanophosphors as a nanoprobe for drug delivery and external magnetic tracking applications. He has more than 150 papers in several reputed journals and 7,000 citations. He received the Indo-US Fellowship Award in Physical Sciences 2010 and 11 and APAM, Asia Pacific Academy of Material Fellow accommodation in 2017. He was recognized as the top 10% highly cited author in the materials portfolio of RSC Journals 2019. Today, he is going to enlighten us on the conceptual understanding and state of art of nanomaterials for emerging nanotechnology. On this note, I welcome Dr. Bipin Kumar Gupta on this virtual platform. Sir, you have 45 minutes followed by 10 to 15 minutes of question and answer session. I request you to please restrict the talk in the timeline. Over to you, sir.
I am audible. Hello.
Yes, sir. Yes, sir.
Okay. So thanks to Pooja and thanks to Dr. O.P. Sinha who invited me just few days ago. And although there are some prior more engagement, but anyhow, because I feel like that the MIT is the second place where I'm always to say like that, okay, I will give the talk, because either in the nano or either in the applied physics department. But last 10 years, I'm much more interact with these departments. So that's why I never say no. So that's why it's a one choice to, I should accept it. And now I'm going to share, then I will discuss about the, can you able to see my slide? Hello?
Yes, sir. Yes, sir.
Okay. So as already I discussed about the, today I will discuss about the conceptual understanding of the state of the art of nanomaterials, because most of the time when we think about the any kind of the technology, the building block is material, and nano is a very fascinating word people using. But when you talk about the some device or like reproducible device or what is in hand, then very difficult to say, oh, this technology we are using because of the nanotechnology. But obviously there is certain devices they are in the market that can be used for the based on the nanotechnology. So basic understanding is very important. So basically I will cover it to like start with some fundamental aspects of the nanomaterials, how we can recognize it, how a student can understand why we can say nano and how it is different from the bulk. Then I will discuss about some about the work on the graphene and how we can make like graphene quantum devices. Then if time will permit, then I will discuss about the other material for the like security ink, because normally this work is more popular than the other research work because it's related to currency. So most of people want to listen more about the application that can be part of the money. So anyhow, means this is the idea to conceptually what I can put in the slide, but it's a privilege to many students here. So I will try to discuss like most my interest to discuss about the motivation to how we can capture mind of the students, how they can become in the science and how they can realize science is important. And nano is a platform that make the least distance between the physicist, chemist, engineers or mathematician. So this is a right platform to, you can say, a material scientist. So basically, so in these aspects I will start, but before I can start, I will just put this slide. It's very important because he's my PhD supervisor, and just because of the pandemic coronavirus, no more with us. So I can say, and regard to this presentation and dedication to my PhD supervisor, I can say about him, he's a composed like a man, a book of learning of infinite chapters. If you interact him, so if you get the chance, you can learn a lot. So I am just a piece of that learning part. So that's why it's very important to remember him. And I can say he's a person, an iron man of the science, and example of full of dedication, consistency, and hard work with science as a passion. So he lived with the science, and he even left us with the science. So that's why the remember to him is very important. So now I will start with the work with the first we should understand why we do the science. When we talk about as a scientist, then our dream is like a person like the less interactive, or it's like so many dreams people are thinking. In my concept, a scientist is someone who, if they want to receive a respect from the society, they should observe wonders and listen to ideas to others, conduct experiments and ask the questions, use your tools to solve the problems. If suppose some problem in the society, so you can do the science and solve the problem of the society, and explore the world around them. Whatever you discover, to try to understand this is really invention part or innovation part, or what it is. So basically science is nothing like science is a creation of knowledge, and technology is the application of that knowledge, and innovation is the application of that technology. But sometimes people saying like that this work I published this place or this platform, and this technology may be like that, it may be come to future. So they never understand the difference between the invention and the innovation. They just lightly use what they like innovation. But if you try to understand the difference, when you do some discovery and there is no commercial aspects, then it is part of the invention, not the innovation. When you talk about the innovation, means you discover something, there is some impact for the society or system that can be utilized it. So there is a commercial exploitation. So this is a big difference between the invention and innovation. So these terms are very important to understand for the beginners before they can enter in the area. So then why innovate? Then people think like in their mind, why we should innovate? If I am not much intelligent, so how I can be innovate? So this is a learning pyramid. You can understand the intelligentsia is not a one kind of the matter you can discover the thing. This is a survey from the USA. Bethel is a place where the average minded students are there, and how they can conceptualize the learning. If you do the just to listen the lecture, means you gain nothing. If you do the reading of same thing, then you can just gain the 10%. If you do the audio visual, then 20%. When you demonstrate to others, then 30%. When you discuss with the others, then 50%. When you practice to doing, like in your lab, then 75%. When you teach about your findings, then you will get the 90%. That's why sometimes we are saying the our teachers are very important, because they are passed through the pyramid of the base. So that's why they're getting the knowledge of the more than 90%. Then question comes, if you discover something in India, then people said like that, how we can do the in product? Yeah, it's a really a big problem. If you discover something, it is not like or not guaranteed that it can convert into like product, because if you see this scenario in the research to product development, there is a bridge required for the government of India, or like any government. They should provide a bridge for the foundation of the structure. If suppose you do this some science, if you do this some product, want to convert into commercialize, then you need the structure. Like you can see the current scenario, like the vaccines. So if you have infrastructure, or the current scenario of the medical equipments, so if you have infrastructure, then you can able to convert to R&D to product. But if you have no infrastructure, like just like a small projects, but there is no longer vision to how it can be converted, then it's a big problem. And sometimes we realize it like the current scenario. So it's very important to, if you do the R&D, the government has responsibility to make a bridge. Then only it can be not like Death Valley. Otherwise, most of research is going to Death Valley. It's a very important, and we shall know to make the vessel for this. So life is always challenging. Just like previous speakers say about the hydrogen storage, and I have the privilege to work with a person with a hydrogen man. People call as a hydrogen professor, and we work on the hydrogen storage material. And not only we work on the storage, but we drive the so job after completing the PhD after 8 years, involving in the hydrogen work. Then the life coming the another challenge. And challenge was to the area which I joined, like fluorescent material. Like whatever I had done, I have to start with the new, concept to new areas. So challenge always give you the, opportunity. So you just take the challenge and take the opportunity and convert into goal. This is the, one of the funda of my life. So similarly, people should do like that. New people always like that I had done this thing or I learned only these things, I cannot do other. So you can see the best example, and I will just to, whenever you are doing the science, you always do the dream. When I started my work in 2003 in 99 in the PhD in BHU, that time I just dreamed, can I make the lab after some time? The same person can visit my lab. So after 15 years, when I made the lab in NPL for the single layer graphene and the fluorescent material, the Professor Joshi came in our lab and fulfilled my dream. So why I shown these slides, just like to motivate to students. If you have dream, you have ideas, if you have concept, definitely you can achieve the goal. Like two of my major work, although I have done many, I always feel myself as a material scientist. I never, classify as a like the work for the fluorescent material or like the hydrogen storage material or like the supercapacitor or like the field emission. So if you have the basic knowledge of the material, then and if you have the systematic understanding of the material and if you realize it, definitely you can make the goal for the product or application. There is no need to any, specific requirement for, you can say like that for this area I am working, I cannot do. As a material science can do anything if they have the conceptual knowledge. So it's very important. So that's why I will discuss about among the two work which is recognized for the one of the work, the security, because India importing a lot of security pigment from the abroad. So our Prime Minister asked to go the RBI and the institutions to, can you make these kind of the pigments? So we made these pigments, and we are trying to substitute the indigenous development by the import substitution. And second kind of the work like the graphene and the 2D materials, because I realized from my PhD time, we are importing the CVD systems or MOCVD system from the abroad. We never trying to make it. So we made our indigenous development for the single layer graphene, and we done the work. After that, the developing such kind of the CVD system in our lab, and you can easy to make like the graphene as well as the MS2, WSC2, that I will discuss here. So these are a few the recognitions during the when these kind of the work is published. So many times in the Nature India platform, and Dr. Harshvardhan also recognized this work for the security, and they announced for the use for the currency application. So now I will discuss about the main work, because these are just few slides. Earlier was to just to motivate the students, because you can do the revolution by the using the science. So now I will discuss about the single layer graphene device, how come the idea in my mind to make the setup, and why it is important for the do this kind of the research. So before that, just like to, because this is the online webinar, so just like I can show the graphene work which is done in our lab. So just a small video for the 2 minutes, and then I will discuss about the work.
Hello and welcome to Science Monitor, a show that brings to you the most significant news from the world of science, technology, innovation, research, discoveries, and much more. I'm Ashwarya Kapoor, and here are this week's headlines. Single-layer graphene material synthesized using indigenously developed technology by scientists at CSIR's National Physical Laboratory, New Delhi. Open discussion organized with the authors. Graphene is a single layer of graphite. The remarkable thing about it is that its crystalline structure is two-dimensional. Graphene is strong and stiff, amazingly thin, almost completely transparent, extremely light, and an excellent conductor of electricity and heat. However, synthesis of graphene is a tedious process. But now, scientists at CSIR's National Physical Laboratory in New Delhi have successfully synthesized graphene, which can be used in next-generation quantum devices like high-speed computers and memory devices. Science Monitor brings you a report.
Graphene is an allotrope of carbon. It is the form of a two-dimensional atomic scale, hexagonal lattices in which one atom forms each vertex. Vertex is the basic structural element of other allotropes, including graphite and charcoal. Graphene has become a versatile material, as it is the lightest and strongest material along with an ability to conduct heat and electricity better than any other. Earlier, it was believed that synthesis of graphene is not possible. However, isolation of graphene by dissecting it from a piece of graphite made the picture clear and instigated scientists to focus on synthesis of graphene sheets. Therefore, many researchers have tried to synthesize graphene, but very few of them succeeded because the manufacturing and maintenance cost was too high. This challenge was very well taken up by a team of researchers led by Dr. Bipin Kumar Gupta from the Advanced Materials and Devices Metrology Division at CSIR's National Physical Laboratory in New Delhi. They have successfully synthesized metal-grade graphene by using indigenously designed technique in India, which is much durable and cost-efficient too.
Graphene is a very... So I will discuss about the work. Before that, I just to make the conceptual understanding about the nanomaterials, because it's a very important before this kind of the specific field to start. So basically, it's a well-known definition of the nanotechnology. Most of the time, people using the definition like nanotechnology, a diverse topic, and can be loosely defined as the ability to work at the atom or superatomic level to create materials and device superior to the macroscopically assembled analogs. How it can be different, that I will discuss in later slides. And this idea is from in 1960s, a most famous scientist, Richard Feynman, and they said like that there is a plenty of room at the bottom, which is that time they are using the statement, and now we are realizing. So how a layman can understand the nanomaterial? If you suppose a block and you are trying to cut it and cut it and cut it, ultimately you can cut up to a certain level that can be changed the property. How they can realize the property? So you can understand. This is a very basic understanding, and normally it's a missing from the most of the lecture. Like how we can realize with the bulk and the nano. This is the four major difference, which is you can understand that you can make the difference between the bulk and the nano. Like gravitational forces become negligible in case of the nanomaterials, but we talk about, and electromagnetic forces are dominating. Why? Because surface charge is high, so these forces will be dominate to gravitational force. The quantum mechanics is the model used to describe the motion in the case of the bulk, but in case of the nanomaterial using the quantum mechanics. And if you talk about the surface by volume ratio in case of the nanomaterials, it's important to understand, but I will one by one put this slide and trying to demonstrate you how you can realize it, those phenomena. Like random molecular motion becomes more important in case of the nanomaterials. But why when we were saying the nano, not only like the dimension, if suppose in the nanometer or like atomic range, and you can say like if you magnify it and ultimately like 1 nanometer, and we can say the nanomaterials. How we can say like that? This is just example I'm saying what the mean of the nano, but you try to understand when you will say the nano. When we are saying the nano, it means the material from the bulk, its chemical properties should be changed, like reactivity and catalyst properties should be changed, thermal properties should be changed, mechanical properties should be changed, optical properties should be changed, electrical properties should be changed, and magnetic properties should be changed. So few of the example I will show you in these properties, how you can realize it. So these things are very important. And best example, you can understand the surface, how play the role. If you make the unit cell of the 13 atoms, then if you spread it on the planar, then the surface atom area will be 92%. When you conjugate with the 2 unit cell, ultimately what we are doing, if unit cell is going to conjugate, then we create the volume. So if you increase the number of unit cells, it means its behavior is going from nano to bulk, and the surface atom is going to total number of atom will be high, but surface atom going to reduce. So you can see here, if one cell, then 92%. If two cell, even this kind of experiment you can do yourself also. You can make a cage and try to put the atom, try to adjoint it, and try to calculate the surface area versus the number of atoms. So if 7 cell, then 35% the surface area. It means if you add the cells, the surface area is going to reduce, like 92% to 35%. How we can realize the catalytic activity? Best example, you can just use the spherical iron oxide nanocrystals, and if you see the bulk behavior as the nano behavior, below is the x-axis the particle size, and the y-axis is the percentage of atoms in bulk of on surfaces. So if you see it, a clear difference in the nanomaterials. It's just like drastically change. Means after the confinement, it's the sharp change in the energy. So that's why this kind of the behavior is totally different from the bulk. Another best example, you can consider a cube and try to cut it up to like 24 times. If the cube dimension you can consider like 5 centimeter cube, then the side will be 1.7 per side. So if you spread it like 160 yard football ground, you can able to cover it. So this is, you can realize it how the surface by volume ratio is going to impact the role when you are trying to say the nano. Best example in Diwali, in layman, you can say the Asbury carbon. If you put the energy, the volume convert into surface. And I hope everyone in the childhood, they make such kind of the nanomaterials. And so this is the best realization how you can understand the, so like optical property, how you can understand. If like you can make the silver nanoparticle meter, if you reduce the size, then what you see here, the sharpness of the, if you see the image of the optical image, the sharpness is going to increase in case of the nanomaterials. Why? If you put the light, the scattering amplitude will be less in case of the small size and higher in the case of the bigger size. So that's why sharpness is increased in case of the lower dimension like the 40 nanometer, but the higher dimension the scattering is high. So there is a several way. The best, Victor Kilmov, this article should read everybody, because if you understand the nano, then you have to explain why the band gap is going to increase. If you ask anyone, they say, okay, if you make the nano, then it's going to blue shift. Then why is blue shift? Like the person, the previous speaker, they are saying like that the most of the case of the quantum dot, it's the band gap is going to increase, but our case in the C3 and 4, the band gap is going to decrease. You have to understand the pi stacking is not like the what we are talking about the nanocrystals. Totally different. We can be out of the plane, any atoms is going to organize. It is not part of the like this kind of the confinement effect. So they are kind of the coordination of the atom from the top surface on the planar structure. So that's why they are the quenching of the band gap, not like these kind of the quantum dots. But if you're talking about the quantum dots, it's a clear confinement you will observe in the UVBs also, because if you see here the bulk, there is the continuous band of the valence band and the conduction band. When you talk about the nanomaterial, what the mean of that? If you come closer to nanomaterial, it means you change the particle size up to level that a confinement region you can achieve. If you want achieve the confinement, then the sub level is going to play the role. There is a splitting in the sub leveling SPDF, and the surface charges will be high in case of the nanomaterial because of the confinement. Because change in energy is very sharper, it will only happen when surface charge will be very high. So if you see in those situations, then the Coulombic repulsion will be very high. Then band gap is automatically is going to enhance. And how mathematically you can try to confirm it? Like if you calculate the band gap of the quantum dot, then the base band gap like the bulk plus h cut pi square upon 2 meh r square, means if you reach the confinement region like the Bohr size, then what will be happen? Then the r will be very small. Then the perturbation term of the h cut pi square upon 2 meh upon r square will be very high. So in that cases, it will be like the band gap is going to high. When you are talking the bulk, then r will be very high. Then total effect will be very low. So then why in the bulk structure, the h cut pi square upon 2 meh r square is very less contributing. It's like negligible. But in quantum dot, because r is very less, so component will be very high. It is in a denominator. So that's why we clearly realize the high band gap. And confinement, you can realize like the clink. If you do the UV with like the scanning rate is very small, then you will see the several clinks of the SPDF. So that will not realize in the bulk. So this is the way you can understand the bulk and the nano difference. Another way you can like the if you density functional theory, like if you putting the density in like the density as well as the energy graph. In case of the 0D all confinement, so it's like the like wall kind of the like quantum walls kind of the confinement like x and y and z direction. When you talk about the 1D, then the confinement in the one region. That's why one behavior is parabolic and one behavior is like the quantum wall. So it's if you join it, then it's like the this kind of the structure. In the case of the 2D, the confinement is two direction, x as well as the y. That in that case, it's like the stair kind of the D versus E graph will be there. In case of the 3D, as they are well aware about the Schrodinger equation, it's like the parabolic behavior. So these kind of the way you have to realize it, and there are several applications of these materials. So already many speakers talk about the applications. So already I just listed here. So I will not put much time about the applications, but there is few applications like it is used for the like TiO2 coating by the players on the mask, and they protect the sun, and like many applications of these kind of the zinc oxide like antibacterial effect. So even in the movie there is some fascinating term trying to use in nanotechnology. Like you can see in the movie like the Hulk, they are trying to show like this kind of the concept. So now understand that why it's so fascinating and why it is important. So basically these kind of the material, you have the two approach to make the material, like bottom up nanotechnology and top down nanotechnology. If the assembly of new molecules or assembly of molecules into the machine modification of the existing material, then it is called as the bottom up nanotechnology. When you are trying to start from the nucleation at the molecular level, then it's a top down nanotechnology. So best example you can see here, the bottom up nanotechnology. This guitar is the one, the size of the like flower is size of like few microns, and you can see here in the slide. And if you talk about the bottom up approaches, so you can see the nucleation of the nanocrystals, and you can see here. Then the question comes, when you talk about the nanotechnology, so when we will use the bottom up, when we use the top down. So it's a clear cut comparison. In the case of the top down methods, begin with the pattern generated on a larger size and then reduce to nanoscale, like you seen in the case of the guitar or flower they are making. By the nature, aren't cheap and quick manufacture, slow and not suitable for the large scale production. If you are making some like quantum device or nano chipping, then it's okay. But if you want in bulk scale, then you have the bottom up method, because it start with the atoms or molecules, build up the nanostructures, and fabrication is much less expensive. So that's why most of the laboratory kind of the quantum dot or like any kind of the chemical synthesis, that a part of the bottom up method. And if you talk about the like FIB or like ion etching kind of the fabrication, then the part of the top down method. So this one example I can see here, you can see the CSIR NPL written by the FIB, focus ion beam, and it's a few micron. So then question comes, how we can make these kind of synthesis. So broadly you can characterize it, the physical method and the chemical method. So in physical method, if you start with a solid and deposit as a solid, so like carbon arc, laser ablation, vapor trapping, and chemical methods like reactant A to reactant B make the some product. So I listed here like the sonochemistry, microwave synthesis, microemulsion, hydrothermal micro encapsulation, sol gel, and the wet chemical method. So depends upon the which kind of the synthesis you want to in your experiments. So different kind of the like gaseous phase methods. So there is listing several methods you can use. For the liquid phase fabrication, you can like molecular self assembly or supramolecular, sol gel, single crystal growth. So depends upon the your requirement, like liquid phase synthesis. So it's very important to understanding the method, because if you are required nano rod and you are trying to some method, so that will be not beneficial. Now the question comes, now we are thinking about the nano and we are understand the conceptual, the how nano can be differentiate. Then nowadays, why we are talking about the 2D materials? It's very important to understand why we are talking about the 2D materials, because in the recent trends, like the graphene, HBN, MOS2, WSC2, and fluorographene. So if you see here, what is the beauty of these materials? The one beauty of these materials is a planar material. So if you make the device, it's easy to make the like flat devices and lightweight because of the atomic thin kind of the material, and the flexible in nature and easy to make the heterostructure to change the properties. So if you see the 2D liability, like if you see the metal like graphene, if you see in the insulator like HBN, if you see the like semiconductor like MOS2, WSC2, or like ZRS2, if you talk about the insulator like BN or like 2D oxides, or if you talk about the superconductor like BSSCO, so all kind of the 2D materials are in the liability. So that's why people trying to think in the new lightweight, flexible, tunable properties with these kind of the material for the upcoming future. So these kind of the basically work started from the, if you talk about the thin film or thick film, there is some book listed I am here. So they started from the thin film and ultimately they reach up to atoms or molecules and then talked about the 2D materials. It is nothing but people start with the like sheet, thick plate, foil, thin film, and ultimately, so there is some debate also in India, like the people they are working on the thin film, they are saying they are already the father of the like thin film technology from the earlier. Now people talking about these kind of the 2D materials, but yeah, it's a fact, like the resources from the 2D material is started. If you see what is the beauty of the 2D materials, so you can compare it like the electron flow is stable in case of the ultra thin 2D uniform metal particles if spread in the like monolayer or bilayer, but in case of the thick film, if you, it's a, like the electron flow is not stable, so like they reduce the noise or hindrance. So if you improve the electron flow property or like electron transport property, this kind of material is very important. The brief history, if you talk about like 1937, these kind of the 2D crystal could not exist, but people are thinking in that, like Landau and the other scientists. So 1947, Wallace calculate the band structure of the single layer graphite, because that time no graphene word was there. 1962, Botham and they terms as the graphene, but 1980 theory studies on the graphene confirmed the massless Dirac equation and anomalous Hall effect. So ultimately in 2004, the graphene was discovered by Andrejim and Nolosov, and ultimately they realized from the 1930 to 2004. So discovery of material is just not a joke. So you have the basic understanding and all kind of the concepts. These are some new materials. There are also like new class of the 2D materials. So now I will little bit focus on the how the graphene is going to discover. So if you this is also very motivational, so I will definitely discuss. So like graphene discovery is a very important and very interesting and very inspiring story. Earlier, the Novolosov and the Andre Jaim working on the geckos, and they are thinking about how the geckos footprints, how the geckos stick with the walls, and they are trying to study in deeply in these kind of the geckos and trying to make the some polymer based ultra thin films and trying to see the interatomic force effect in the what kind of the dimension it will be more. So ultimately they make like this kind of the mimic cake and trying to 140 gram of the Spider-Man, and they're trying to stuck it because interatomic force is higher because of thin this kind of the fibrous kind of the wall. So because capillary action is very high in those kind of the structure, so ultimately how this idea came in their mind, so they're trying to study the trying to each gecko's footprint, how much force they contributed as a fiber. So ultimately they realized 10 to the power minus 7 Newton per centimeter square was a single fiber. So many millions of the fiber in the footprints, and ultimately they measure the angle between the wall and the fibers, and they make this kind of the material for the like polymer. They're trying to it is possible like that the some material that can already exist in the universe, and that can be they start from the muscovite, biotite, and ultimately they're trying to talc, and ultimately trying to like graphite, and graphite because the highest slippery nature and easy to make the cleave from the surface to surface. So they ultimately they get from this cost step method and they get the Nobel Prize. So because of the extraordinary properties of the graphene. So I told about the graphene and why it is using the graphene and why graphene is important, that already discussed. Now the question comes because putting the conceptual, it's very important to between the among the students. So that's why I'm trying to in the third time to put whatever fundamental I can do. Like people can ask like why the C60, C70, and then the carbon nanotube, why not that time the graphene was? The reason behind that, because people trying to the minimum energy configuration structure is the reduce the dangling bonds. The best structure to reduce the dangling bonds at high pressure and ultimately like buckyball structure, like the spherical structure. And if we talk about the how the CNT going to discover, then if graphite sheets are, if the different aspect ratio is length is higher and width is less, is if rectangular shape trying to cleave it, then the dangling band is going to saturate, it's like the cylinder. So then ultimately why people thinking about the single layer graphene or bilayer, the reason behind that, in those structures, because the if you see here the covalent bond between the structure is utilized because of the in plane, but the delocalized pi electrons, if you see, or like the dangling bonds, because the curvature structure, it's utilized only on the edge mouth or like the outer surface. But in case of the graphene, you can fully utilize the covalent nature of the graphene sheet as well as the dangling bonds around the sheet as well as top and bottom. So that's why people trying to discover this beauty structure of the graphene. So ultimately there is very important, because you can see the compare with the study with the gallium arsenide or silicon, because I'm trying in terms of the quantum devices. So ultimately it's a very high mobility as compared to this material. So that's why it's a best choice. So ultimately now I will discuss about the work, which is because already if you see in this area, the 2 Nobel Prizes in this area, because one of the quantum Hall resistance and graphene not only getting the quantum showing the quantum Hall resistance, but even its discovery itself showing the breakthrough in the area of the carbon material. So now the question comes, why we are talking about the graphene like the band gap or like Dirac points. But if you see here in the 3D concept of the like the bulk material, the energy is like h cut square upon k square 2m. But in case of the like graphene, it's like the planar structure and it's like hexagonal and structure. And if you see the graphene, if you see the graphene lattice, then the corners 6 atoms. So if you first bring one if you by red color, and second is like the yellow. If you see here, projection is like the conic. So because of the conic structure and touches to each other, no band gap. So these kind of the material not is finger, but that can be explained by the Dirac. So that's why we are called as a Dirac point, and the conduction band and the valence band to each other. So there is a lot of examples to do the graphene like. Now I will discuss about why we should quantify graphene like 1 layer, 2 layer or 3 layer. Why it is important. So if you see here like monolayer and bilayer, how we can make the difference. If you do the spectroscopic, in the case of the monolayer, 4 kind of the concept is like electron hole interaction, hole interaction, hole electron interaction, or like electron interaction. So like 4 kind of the interaction in the case of the single layer. In case of the bilayer, like 9 kind of the probability is possible for the transitions. So in that sense, we can, if know the FWHM, we can understand this is a single layer or a bilayer. It's a very important, because of this behavior, you can do the make the device like quantum devices. So now question comes, how we can make these like materials. So there is several techniques of these materials. So like the exfoliation, CVD, epitaxial. So depends upon which kind of the application you want. Like if you make the like chemical exfoliation, you want to electronic properties, you will never get. If you want to like the electronic property, you have to do CVD, because pure system and the dangling like delocalized pi electron density will be high, then only you can get the electronic properties. Like the exfoliation, if like intercalation or like functionalization, you will not get the electronic property, but chemical property can be you can able to get. So there is several ways to like if you ask anyone, like you do the chemical method, how you will realize the it's a good quality of graphene or graphene oxide, then it's very hard to get the answer from the people, because they are saying we've seen the XRD and we are getting the like around the 25 degrees then it's like 002 like reduced graphene. You talk about the like the geo, it's like on the around the 8 point something degree. So it's a like geo, and the around the 25 degrees like RGO. But if you see seriously here, if you do the Raman, even FWHM of the geo is less than the RGO. Same I told about the when you talk about the single layer or bilayer. And other method is how you can realize like C by O ratio. If you talk about the chemical exfoliation, then if you see in geo, the deconvoluted the like the reduced graphene and graphene structure. In the case of the geo, you can see here the peak around the 60 degrees, 60 around the ppm is higher in the case of the density, but in the case of the RGO is like is around the 120. So what is the mean of that? The mean can be realized if you do the XPS, means if you C by O ratio calculate in case of the reduced graphene like 3:97 or like 4:96, but in case of the reduced graphene like 20:20 like 80 or like 30:70. So you need to understand like which kind of the material, what is the cost, how we can do this kind of the synthesis, and what is the beneficial route for the making the device. So I will just to go my work because there is several ways to we can metrological tool to characterize this kind of the material to quantify the real is the graphene is the graphene. So I will just to go now the my work directly because almost putting the concept a lot of time I taken. So very quickly I will go. Like NPL is also like metrological lab. So as you know that the SI unit is going to redefined. So in those sense, it is important to make the quantum devices to precise measurement of the current and the voltage. So because if you see the fundamental units, it's going to redefine like ampere is like electronic charge, mass is like velocity of light, and time is like the frequency, and like mass is like the Planck constant. If you see the like the temperature is like the Boltzmann constant. So for this definition, it's important. Like I'm talking about the quantum Hall resistance. Why important? So if you define the mass, then you have required the correct measurement of the Planck constant. So for that, what is the idea of that here? Like the electromagnetic mass is going to equivalent to gravitational mass, and for the if you when you dying to do this kind of the equivalence, then you require the current and voltage. If you need to correct measurement of the current and the voltage, then you have need to make the quantum Hall resistance, means resistance should be precise. So that's why these kind of devices encourageable to make the like high quality graphene for the quantum Hall resistance device. So the reason behind that, you can see here the gallium arsenide, if you compare with the graphene, the low magnetic field required for the this kind of the splitting of the characteristics lines of the graphene. So you can realize like the plateaus for the making the quantum Hall resistance. And if you see the temperature required the less as compared to the gallium arsenide, and if you see the accuracy is much good as compared to the gallium arsenide. So ultimately, our director asked me to make a material like the graphene single layer, and that required for the quantum Hall resistance. And they provided. Then we said like that, okay, we can do like that. We have required one room and 20 lakhs, and ultimately they provided the 6 lakh and without room. So ultimately, we made the device indigenously and made these devices like single layer graphene to reproduce. And you can see those the quality of the graphene which we made here. And we not only make this kind of the setup, we change the concept of the mass flow meter of 3 mass flow meter required for the graphene kind of the setup. We have required only 1 mass flow meter, and this is a very cheaper setup as compared to the setup which is imported from the abroad like 70 lakh and 80 lakhs. This is only less than the 5 lakhs. And the quality of the graphene you can see here, the single layer graphene. If you see here, we trying to repeat the experiment several times, and single layer high quality we get. If you see the HRTM, the single layer clearly you can see the edge of the figure B, and if you see the resistance, the range of the single layer, we repeated several times, and ultimately if you see the quality of the graphene, so this is the way to transfer the graphene. So if you see the quality of the graphene, it's like, and we trying to compare this quality with the mechanical exfoliated pure system. So quality as much good as produce the graphene from the CVD system. So we also checking the quenching effect of these materials, and ultimately we made the quantum devices, and we went to TFR to make these quantum devices measurement, and ultimately these devices, we single layer devices, we make the in TFR by the FIB technique, and ultimately shown the QHR and the resistance in the range of the what aspect. So this is one of the work I told about the graphene. So similarly, many works we done in the area of the graphene, like we make the Y functional graphene, it can quench the fluorescence, it shows the own fluorescence. And recently we make the twisted bilayer graphene. It's a very important, because if this kind of the graphene, recently I published in Carbon in 2021. So in this case, we are trying to make the graphene like bilayer, and we done the temperature dependent studies. If you change the temperature, graphene is going to twist, and twist angle can be changed. So why this twist angle is important? Because we trying to make the coupling decoupling reaction with respect to temperature. So if you know the G and D and 2D position, we can able to estimate the twist angle, and this twist angle, if you plot it, then we seen the at the high temperature twist angle is low, at the lower temperature twist angle is high. So it means that if twist angle will be very low, the coupling will be very high. So we can trying to several to observe in this, and this kind of the phenomena and how they can be contribute for the science, like we can discover like superconductivity, like one half singularity, G band resonance, chemical reactivity, optical absorption, and interlayer decoupling. And recently, after our this experiment, people realized, and they also cited in their review in the 2021 recently, few days ago, and they quoted our data. And also, if you see in the science paper, they get the tunable superconductivity in February. So twist angle is very important. If you change the twist angle up to 1.1 degree, so and what our study is going to contribute, if you change the temperature, then superconductivity phenomena can be tunable, like twist angle is going to change in our case, like 2 degree to 14 degree. So this is some of the experiment we done with graphene. Similarly, we also make the setup for the MOS2, WSC2, and these kind of the furnaces we taken from the dump yard and make it for the calibration for the temperature standard, because it is the meteorological lab. So we done the growth zone temperature calibration, and ultimately we make these kind of the material. And you can see here these material have same quality as people publish in the Nature material or other journals. So we started from the I started from the mechanical exfoliation, and we understand the quality of the MOS2, 1 layer, 2 layer, 3 layer. Then ultimately we published this paper, and then we started with our CVD system, and we indigenously developed this CVD system by single zone. Normally people using the double zone furnace for the MOS2. So in this we made like monolayer, bilayer, tri-layer kind of the material, and we also explain the why the edge is coming in the case of the even monolayer in the photoluminescence, because the bion and trion kind of the transitions taking place because of the, if you convert into like the single layer or double layer or triple layer. So if you excite it, then because of the confinement, the sub level also play the role. So because of the 2 electron combine and make the transitions, or like 3 electrons, so that it's called as the bion or trion, like the charges like A minus or like B minus. Ultimately also published like 4 days ago in the material chemistry. So and now the question comes, what these kind of, so we understand why we like this kind of triangular or hexagonal structure. So what we had done trying to understand the phenomena. So if you see like termination of the dangling bonds by the sulfur or like the molybdenum, you can change the structure. Like if termination, and how you can control this termination, these can be controlled by the molybdenum and sulfur ratio. If you change the ratio, it can change the structure. So like or hexagonal, this kind of the structure. So similarly, we are also doing the MOS2 like different structures, and also we trying to see the thickness of the structures. And similarly, we also done for these same equipment ultimately we are also making the of heterostructures like WSC2 and RESC2 like atomic thin diodes. So ultimately we are taking N type and P type of the single layer and trying to make the sandwich. So these kind of successful synthesis we have done in our setup. Recently, last work I will discuss about the nanomaterials like we published recently like ultra-sensitive variable stress sensor that is based on the carbon nanotubes. So we are growing the carbon nanotubes in the several dimensions of the height, and ultimately we are using for the sensing application. So this work was recently in March considered the Nature India platform, and they put as the highlights of the research, and this work is published in ACS Supply Interface in March. So basically in this we are making a device like the aligned carbon nanotubes and trying to make encapsulate in the polymer and trying to cut it. After cutting we are trying to make like the device, because the cut surface is producing the conducting surface, because if you put the polymer, then polymer cannot conduct. So first we freeze in the polymer to like this kind of aligned nanotubes and cut it and trying to see the different dimensions of the nanotubes, which is showing the more strain capacity. And before that we are previous year we are trying to understand the mechanical properties of this kind of CNT, and that was published in the SSR interface. So ultimately we make this kind of device, and I can visualize use. You can see these videos. If the person bending the hands, you can recognize the sensing property. So not only we are talking about the nano material, but you can see the real application. And particularly we are targeting the Parkinson disease kind of the patient, because they have required the 24 hours motion tracking. So you can see here even the finger is going to change, it is going to showing the sensing. Even if you scroll it, then it's showing the sensing property. So I think so almost I taken the 1 hour, so 5 minutes more I have required, just like to the last glimpse of my work. I will not go through all the work. So the graphene lab is visited by several eminent professors like Professor K.L. Chopra. Unfortunately, he is no more now. So Professor O.N. Srivastava and many more like Professor Ajay itself. So another work is just like to, I will put the glimpse. Our Prime Minister is talk about this, what I'm saying, like the why we should not import the pigment, why we
गांधी ने स्वदेशी के लिए इतनी लड़ाई लड़ी, देसी कागज तो उसकी तस्वीर छपती रहे। क्या मेरे देश के पास ऐसे उद्योगकार नहीं है क्या? तो कंपल किया जाए तुम्हें ये फैक्ट्री लगानी है, पैसा चाहिए दूंगा, लेकिन ये लगाओ बगल में, लाओ दुनिया से टेक्नोलॉजी लाओ, और हमारी करेंसी, हमारी नोट, कागज हिंदुस्तानी होना चाहिए, इंक भी हिंदुस्तानी होनी चाहिए, और मैं चाहता हूं कि आरबीआई इस बात को एक
So after this motivation we develop and
उपाय करने के बावजूद नकली नोटों पर पूरी तरह से लगाम नहीं लगी है, लेकिन अब नेशनल फिजिकल लैबोरेटरी यानी कि एनपीएल ऐसी स्याही तैयार कर रहा है जो नकली नोट के धंधेबाज को पूरी तरह से फेल कर देगी। एनपीएल का दावा है कि इस स्याही के इस्तेमाल से जो नोट बनेंगे उनकी नकल नामुमकिन होगी। वित्त मंत्रालय और नीति आयोग को इस स्याही का प्रस्ताव दे दिया गया है।
गांधी ने स्वदेशी
बनेंगे उन,
तो ये देखिए
किस तरह से नोट बनेंगे, कैसे।
So we are making a lot of new materials, and time to time
India will not have to worry about the fake notes or documents, as Indian scientists have come up with an innovative solution to tackle this problem. The scientists at CSIR NPL have developed an unclonable ink that can be used to give a unique mark to a special report.
Currency notes form the backbone of our economy. Newly based,
हर एक कंट्री अपने करेंसी नोट में यूनिक फीचर लगाती,
invisible misuse, 2 colors on the excitation of a single wavelength. The formulation is based on the combination of fluorescence and phosphorescence and has been tested successfully on the currency notes at the laboratory level. When these notes are exposed to UV light at 254 nanometer, The security feature made with the ink looks red, and when the source is switched off, the figure appears green.
So I will not go to these slides because it takes 1 hour more. So just like I just to make the impression what kind of the security ink we had made. So ultimately, if you this security ink, you can understand if you put your note in UV light, so earlier using the red color fluorescent ink, if you put in the new notes, it's showing the green color. What we are making the material, those kind of the two pigments, like one is frequency switchable kind of the red and green color showing the pigment instead of the single color, and we also make the color shift pigment, that is the substitute for the of the places where we use the our pigment. So ultimately I will just to pass through, world no currency has such kind of the feature, so India trying to this kind of to put in the notes, and very soon we will be going to success in this technology in our daily use. So I will not just to, because it take 1 hour more than, so I will just to pass on these techniques, and I will just to some of the slide taking 1 or 2 minutes. It's very important that I will be just like I will show you. So if you see here, we are also like luminomatic ink for the bank checks. Recently we published in the Advanced Material and Technology Journal, and this is cited by the Science Wire, Science Reporter, and many news, and Vigyan Pragati also. And if you want, anybody want to listen the conversation in the Nature India platform, so you can go to understand what will it be, take the money currency notes hard to counterfeit, the conversation between me and the editor, and many similarly we also develop a like the election ink that will be transparent in nature. If you put on the finger, it will show the red color excited with the UV light. So concept of the blue like the election ink, if you put in the expose in the air, it is going to convert into black. But now we are trying to develop a material that can be put on the finger. It's like invisible. If you excite it with the small LED torch, then it will be showing the red fluorescence. And this work was covered by the Hindu in the cover page. So recently we also trying to technique to detection of the COVID-19 virus. So we have the project with the DVT. So I will not disclose the technique because there are several techniques in the market. We are trying to some spectroscopic technique to how we can mRNA of the COVID-19 virus we can taken out, and we can use these kinds of fluorescent material, and how a common people can easy to detect. So this kind of the work related to that. Many applications more, or also I am doing the luminescent material, but just like to pass on because it's not time to, because already I have passed the time like the 1 hour. So I will quickly pass down, but some of the very important area which I had contributed, I just like to show you, like the white light sources, like DS Mehta shown a lot of the new kind of the technology. So similarly, one of the technology like laser induced white light is a new source of light in the coming generation. So we are getting from the FIAM industry a project. So blue laser induced white light, we make the device, and that device how it can be useful, you can see this video. So basic idea in these video to, you can penetrate it to like 500 meters by laser induced white light, blue laser induced white light. So ultimately we make this kind of the device by the some material the indigenously develop here, and we make the device by the blue laser induced excitation, and ultimately we compare with the other sources of the like the LEDs or like halogen, and ultimately we get the penetration much higher as compared to the any other sources. And ultimately we propose to railway, they can use in the rail engine headlight for these kind of the light, and we also demonstrated to Professor Joshi this kind of the work, new work, and also FIAM Industries the so yeah, just to like to many people to thanks to generate me like my Professor O.N. Srivastava, my guide, as well as the like Professor Ajain, as well as like the Kalam. When I met him, he's one of the greatest scientists. And when you do the good things, then you are recognized several places. That's not the part of the presentation. So really, this kind of the work is basically because of these efficient wheels, because a engine only worth when wheels are efficient. So ultimately, we put the engine with the wheels. So students are really backbone behind these kind of the work. And ultimately, I'd like to acknowledge to all my, and last slide to just as recently I joined as an associate editor, and I'm opening the theme, the agenda like metrological validation of the 2D materials using spectroscopic technique. So all are welcome to submit their work, and thanks.
Thank you so much, sir, for the enlightening talk and explain a lot of examples of using two-dimensional materials, especially graphene. And we are happy that you have developed this bioluminescent security ink for our nation and indigenously development of chemical vapor deposition setup. So with this, I would like to ask panelists if they have questions.
Bipin, thank you very much for really wonderful talk. I am aware about the slightly aware. I should not say the aware. I am slightly aware about your research work which is going on. So time to time we discuss together, and it is really wonderful. And that's what basically you are achieving and you are getting. And it was really it is heartfelt feeling for us that you dedicated the talk to our teacher, Professor late Professor N. Srivastav sir, who was basically a backbone for all of us in the Department of Physics BHU. And we lost not only we lost the greatest scientist, but the world has lost a person of the energy, especially in the energy material for storage. So I am really salute you for the dedication of your talk to him. And then it was really nice to see the blue luminescence material, which is already discussed in the Assembly, Government of India, and Government of India is in the already process of implementing your idea in terms of the printing of the currency. So it was a really wonderful talk, and I am looking forward for the another achievement which right now we have shown using the blue laser induced white light, and hopefully it will be going to change another scientific breakthrough, and that is in terms of the white LED, especially for the in terms of the this domestic applications. So really wonderful talk. Thank you.
Thank you.
Thank you, sir, for this exciting talk with so many videos. So thank you so much. Sir, I have a question to you. So whatever the indigenous setup you have developed for this single layer graphene sheet, so what is the how many years we can expect its life as compared to the setup what we import, which is much costlier?
Yeah, so basically the life you can say in terms of the indigenous setup always better than the if you do the something like dependent life, like if you purchase some out of the country like setup, and they once install your setup and they will not come back to you to any kind of the problem. Like what we have done the setup, every time we are standing with the any Indian, they can use same setup, we will be stand with them. This is the one of the advantage. Other is like the majorly like depends upon the coil. So like if you hitting coil, hitting metal coil is same like what you are using, what the other people using. If you are doing the indigenously, then advantage is to you can shift it, change it like whatever you can according to you. But if you once you are trying to dependent, like I can tell you a story. My boss purchased like Professor Srivastav 70 lakh equipment LPCVD in the BSU, and I can tell you it's not run even 1 year. The reason behind that the small pressure transducer is not working. And then ultimately what's happened, then he asked to, okay, we can able to purchase somewhere in Delhi or some local market. Ultimately, till date, no one able to get the transducer. Company never back to BHU. And ultimately, one day I told to my sir, it is better to, we can just to replace all the computer control system, and I can just to make the device, whatever we have made in our place. So you can use for the single layer or multi-layer. So ultimately, we dismantle the things, and ultimately we make the like simpler. So that's why I'm saying like that. The problem is to
all
like
the parts will be available in India.
Yeah,
Or
you
the
are
small
right.
parts also.
Only the thing like we have to be honest when we are talking about the indigenous. Like I will not decode the name, but like if you're talking about the some microscope, even though we cannot able to make Carl Zeiss making the lens, we are not able to make the monochromator. When people realizing that the make in India, so we have required to those kind of monochromator or like lenses in India to make. I'm not against those things, but sometimes it's happened like if you are talking about more about the indigenous, then you are out of the game from the world what science they are doing. So equally important both. You can high-end equipment which you are not able to make, don't make the pressure for those things, because even your mentors who is the very big hosts, they are trying to run the in India, they are not making any make in India device, only advice. So the idea is to, if you want to make the Nobel Prize, then we have to dedicate our science, but you're not away from the opportunity the science people doing the outside. So if any science is coming in India like after 20 years, 30 years, there is what use? I'm just saying like whatever the possibilities, you can replace those places, but not like trying to, this idea is very important, because sometimes we are conversating and a student thinking like that, so and they suffer longer for their PhD work, so that's why it's important to discuss.
Definitely, sir. Thank you. Another question, sir. Whatever the single layer you have developed, so the source is graphite or any other carbon material?
No, methane. I shown the
Methane.
hydrocarbon
Okay,
gas.
methane.
Yeah.
Yes, methane. So, or other carbon means gaseous carbon source, hydrocarbon source can be used.
The reason behind I can explain you in terms of the chemist, because I already told like material science cannot have the distinction physics, chemistry or mathematics. So if you do the double bond or triple bond, the bonding energy is required the higher. And the case of the methane is the, so if you dissociate it, that is the one aspect, like the higher temperature required. Second is the vitreous carbon will be more in those cases. So that's why we are using the methane or hexane.
Thank you so much, sir. Thank you for your answer.
Thank you, sir.
Sir, yes.
As we are running out of time, I'll take one question from the participant, which is how we can control the twist angles between graphene to such precision, like 1.1 degrees and so on.
Yeah. If you've seen my slide very carefully, then you can understand that what we had done, first we had made the pi-layer graphene, right, on the copper substrate. Then we transferred it to SiSiO2 as a bilayer. What I am talking about that, these bilayer, if you change temperature during the Raman spectroscopy, in situ Raman spectroscopy, if you change the temperature, then what's happened? The delocalized pi electron means electron-electron interaction is going to change with respect to temperature. So if you suppose, if you're doing some temperature dependent spectroscopy, so you can realize at what temperature, what kind of the twist angle will be there. If suppose you want to in some experiment for the device, so you can put that temperature and you can realize it, because we had done this kind of the experiment reversibly many times, like from lower temperature to high temperature, higher to lower, it is reversible. But if particular temperature you're putting like 450 Kelvin, definitely you will get the 2.3 degree. So similarly, if you want to low angle, some angle, particularly angle targeting, you first do the Raman spectroscopy and externally you heat it. So this is the idea to how we can twist the angle externally, because if you do the tri-layer, then the twist angle will be more twisting, because in the bi-layer, one graphene is going to with the substrate. So role play of the twisting is only with the upper layer. But if you do a tri-layer, then the two layer will be flexible. So then twist angle can be lower, like in science paper, they are putting 1.1 degree.
Okay, sir. Thank you so much.
So question from audience. Yeah. Question from audience. Participant.
I think we have one more question from Mehek Sharma.
Yeah.
Just like how in life sciences, chromatically orthogonal dyes, they are used for identification of varying cellular targets. Can such dyes be also used for security at different levels or for different parameters?
Yeah. Like I shown the one project, I got the DBT from the coronavirus detection. So concept is same like the people detecting like the antigen test or like other test. So similarly in the security ink also there is some parameter like excitation source, emission source, fastness of the light, quantum yield. So on basis of that you can qualify the criteria as well the particle size, because you know if you develop some technology you cannot make like a button and people make the cert according to you. You have to make the button according to cert. Like if you make the security ink, that will be fit with the offset printing or like the integral printing. Like currency people will not change the machine for the printing. So those parameters are very important, and obviously those parameters carrying in mind, then only we can develop and ultimately successful to make the ink for the usefulness as a like commercial use. Yeah.
Thank you so much, sir. Any other questions from panelists? So if there are no more questions, let us thank Dr. Vipin Gupta. Thank you so much, sir. Thank you for joining and enlightening us. Your talk on two-dimensional materials and state-of-art nanomaterials for their commercial applications. Thank you so much.
Thank you, Bipin. Thank you for your time.
Over to you, Pooja.
Thank you, sir. The last talk of today's technical session is going to be delivered by Dr. Manish Huda. Dr. Manish Huda completed his master's and PhD from Kurukshetra University, Haryana, and has joined the Semiconductor Laboratory Department of Space, Government of India in May 2004. He developed the key technology enabler process technologies required for micro electromechanical system MEMS device fabrications. Dr. Huda has successfully handled many projects for space applications such as pressure sensors, temperature sensors, humidity sensors, for reduced node micro thrusters, micro igniters, for micro satellite and spacecraft application, cantilever with implanted piezo resistor, and so many. He played a vital role in process integration for 180 nanometer CMOS technology on 200 millimeter silicon wafer at SCL, which is one of its kind facility in our country. Presently, he is the head of technology development division at SCL. Under his guidance, an exotic compound semiconductor manufacturing facility at SCL has been established for the development of devices based on new technologies. Group 3-5 and Group 2-6 compound semiconductors for high power and detector devices for futuristic India space mission. He has published several research papers and has 2 patents to his credit. His initiatives are real milestone towards the Make in India initiative, where semiconductor components can have manufactured within the country. He will share his research work on the technology trends in semiconductors. Sir, you have 45 minutes followed by 10 to 15 minutes of question and answer session. I humbly request you to please restrict the talk in the timeline. I welcome you on this virtual platform, sir. Over to you.
Dr. Huda, can you please turn on your camera as well?
Thank you for giving me opportunity to speak on this particular day of nano era for nanotechnology, sustainability kind of stuff. Nowadays, the world is going through the COVID scenario, and of course, whatever the role has been played by the nanotechnology is phenomenal. And this is not even possible without the contribution of the semiconductor technology in it, whether we are talking about in the domain of micron scale or domain of nanoscales. So here today we will be discussing during this online workshop on this nanotechnologies and its sustainability towards the new generation devices, particularly in terms of the semiconductor devices and their contribution towards the technology improvement of the technology, and sustainability towards providing the solution to the mankind for making a new world which is connecting towards together. So let me switch on my pointer. I think I am audible right now. Okay.
Dr. Huda, I would please request you to turn on your camera as well.
Sure.
Thank you.
Sorry for this. So I think I am not on now. So sorry for this delay. Actually, I was just waiting for the Time. So today we will be discussing about the trend in the semiconductor technology and what about the semiconductor technology in the new era can contribute towards the world and to provide the kind of a solution which is not possible without the help of the semiconductor technologies. This will not be a talk to particularly to tell you about the what people are doing, what people are doing. It's particularly giving you the information about on the technologies which is providing the solution for one kind of a solution to the another kind of a solution. Apart from that, how it has been connected with the nanotechnologies, how the device dimensions are being scaled down and for what kind of a application, and what are the real challenges associated with this in implementing all these devices at nanoscale. Apart from that, if I am implementing these devices for certain kind of application, there are still some challenges which we have to overcome before it can be implemented to provide the solution to the mankind. So I start with the talk, particularly the change happens and amazing way to deal with the changes in your work or in your life is just move with it. So change is inevitable and will be happening at an increasing rapid pace. We cannot wish it was not so, or we can get on with it. So that is what the world at present is facing. Either we have to go with the change with the scenario, or we have to find a solution to adapt the change around us. Adapting the change with the help of several forces is always welcome. I would say if standards are changing, then let's change them. If learning of science is changing, let's go with the changing with the learning of sciences. If demographic shifts are being changing, let's go with them. And if that can be changed with the help of the technology to provide a better platform for the mankind, that definitely is a most welcome thing to be happen. So today's agenda is we will be discussing about change in the standards and technology and try to find out kind of a solution which it can be provided or the identifying the areas of research where we need to still address the problems associated before implementing these devices to the technology node. This won't be a monologue title. You can interrupt in between anytime. And I would prefer if it can be interrupted at any stages and I can be helpful in answering your questions because it's a kind of a discussion, not a kind of a presentation which are supposed to be there. So it's an open house discussion, present and future words as projected by the semiconductor technology and the challenges associated with this. Before I start, you know, the electronics has been governing each part of our lives right from the beginning. If you say from the day-to-day life, from the education, from the office nowadays in the COVID scenario, everybody is sitting at home, even the students, office workers, they are sitting at home and doing their work from the home itself, which is providing the solution because of what is the electronic semiconductor technology, the form associated with it. Apart from that, medical industries, space industries, and even for the pet and animal gatherings, you can easily use all the kind of a technology semiconductor is providing solution each and every era of your life. So this is what, and what is the core heart of it is the metal oxide semiconductor transistor MOSFET devices. And we are talking about this MOSFET device at all right now, but just what are the trends, what are the technologies, how the limitation, why we are shrinking the device for what kind of application and where we are stuck up, and what are the challenges associated with this is what we are thinking about it. So world is shrinking. Before we start, actually what semiconductor technology is doing, connecting the world and trying to semiconductor in establish in your palm top. So you need every information, everything in your palm, and this is what is possible because of interconnecting technologies provided and supported by the semiconductor technologies associated with it. Let me give you a very frank example right now. Due to the COVID-19 situation, education is also leave their mark on the internet traffic, due to which internet traffic has increased by 15% in March as per the data provided by the Frankfurt industry. So every students and researcher, they are sitting at home still continuing with their job while being remain safe at their home. They have access to the devices and data associated with that. So what exactly we are thinking about, if what the semiconductor technology providing you the solution, sorry for that. So the semiconductor technology used to say that we need to provide the solution for the communication, interconnectivity, power, and cloud computing, artificial intelligence, and every part of your job around you shall be controlled by the semiconductor parts. And of course, when it is being told about, sorry for that, when it is being told about, then definitely we are thinking about embodying the system requirement, IoTs, connectivity, sharing data, and the world and communication, data security, artificial intelligence associated with it, pole-to-pole connectivity, high battery lifetime, self-powered source, and power management. Everything has to be addressed to provide a kind of a solution which can really work for long term and can talk to each other and can give the services to the mankind. And this is whole possible because of what? Because of the semiconductor technology beneath that. And the semiconductor technology, when we are talking about, we need to talk about always more and more power, less and less power hungry devices, more and more computation application, more and more security associated with it, and the connectivity to the worlds, each and every part of the world. And of course, apart from that, if the data handling or transmitting by these devices can be really handled via the cloud computing system, is always welcome. And then you can have the real world connectivity in your hand. This is what the desire is. And the semiconductor market application diversification, if you see, the mainframe, PCs, smartphone, tablets, and these are the earlier driving force for the technology to shrink for providing more and more efficient devices, less power hungry devices to you, and a compact devices. But nowadays, it is not more gone by the, I think my pointer is not on, not more gone by this particular thing. It is gone by the IoT, smart and autonomous vehicles, artificial intelligence, augmented reality, and virtual reality service, and 5G interconnectivity. Now, this is the driving force for shrinking the device, more and more powerful devices and less power hungry devices. And that's why it puts a thrust on the industry nowadays to give a solution kind of an industry to you, which can provide you the smartest devices or component in your hand, which can really communicate in a faster manner, efficient manner, secure manner, to provide each and every kind of a solution to you exactly. So what I would say particularly, this very particular thing, if we really note about this, the semiconductor will enable a low latency, high bandwidth, pixel heavy world soon to be spammed way and widespread because of the deployment of the 5G networks nowadays. But it is require a series of industry research before implementing this. What kind of industry research we are talking about is a process, because when we are talking about IoT things, when we are talking about smart devices, it is not even the security issues associated with, because it is connecting with many devices. Of course, it has to be smaller in size, faster, and less power hungry. Simultaneously, we have to adopt a business model where the architecture and the materials associated with to perform these devices should be reliable enough so that it can be used for this kind of application for long-term reliability. The central challenge is the processing of huge volume of the data a lot faster using as much low power raw per bit storage. And of course, when we talked about this, we need to make devices smaller at nanoscale level particularly. Today, the semiconductor industry, as we know, is giving and working as a 10 nanometer or 7 nanometer technology, and we are pushing it further to at the limit of 5 nanometer or making device 2 or 3 nanometers at the most, while keeping the power density constant, because the performance has not to be compromised before. If we are shrinking the device, the current handling capabilities and its communication capabilities and its switching capabilities cannot be compromised at all while we are shrinking the device at nanoscale. So the material, the architecture, and of course, the associated structure, which is responsible for giving you the final solution, remains a key importance while defining the devices which can be used for this kind of application. Now, industry growth, if you see, earlier it was gone by the analog RF devices, then the passive devices, then high voltage power devices, sensor, actuator, and biochips. But the governing factor is that I am shrinking now the dimension of the device or the IC or the technology, which really give you faster devices, which can handle more data in a faster switching speed, and more computational efficiency in a secure manner with a less power hungry chips over it, so that the battery life can be increased at a tremendous amount, and which can give you more and more battery life, so that you can still communicate with the device and technology or to the world, which is supposed to work in a connecting fashion. So in a secure manner. If we see the industry growth start driving source right from the 1960 to 1970, when we used to focus about it has to be a computer centric industry. But then we change about the mobile centric industry, and then we have go to the data centric industry. So today, when we are talking about in the era of 2020, 2030, we are talking about a data centric industry. Why is it so? Because of the IoT's Internet of the Things are coming and taking place with the kind of a connecting world in a palm, which we are supposed to be having. And now, which because of COVID scenario, everybody is sitting at home and they are doing their work. They can still be in touch with each and every part of the world, gathering information, giving information, doing their job. And this is all because of the computing or data centric industry, which is supported by the semiconductor technology for making the faster devices, connecting devices, and secure devices. So exactly the industry is now geared up by the 5 segments: the mobility, the IoTs, the HPC high power computing systems, and the memories. If you talk about the mobility and IoTs, these are the particular device range which are governing these IoTs particularly, or mobility particularly. And the workhorse of all these devices remains the semiconductor technology, where we used to make the device which can have more and more functionality per unit area. Making accommodating more and more functionality per unit area is a key requirement for this technology. And that, of course, when we talked about this, we need to bother about simultaneously the device reliability for the long-term usage of it. That's why we have to focus on the shrinking the device without compromising its performances. That's why we have to focus on the different kind of a material technology which can be adopted for making these kind of a devices in a much faster ways, particularly. And automotive, if you say, today we would like to have every and each and every information on your mobile vehicles itself, so that you can be traveling towards the vehicle, using these vehicles and doing your job, day-to-day activity. People would like to remain in contact with always with a lot of information in their hands, so that they can, while traveling itself or while moving itself, they can still be in work mode. And this is how they can be remain interconnected, providing because of this kind of a technology which is being supported by the semiconductor technology itself. If you remember, when we start about talking about the evolution of the mobile phone itself in 1994, right from there to the 2000, 2007, the evolution mobiles has happened just like anything. Then thereafter, we come into the terms of a smartphone by adding more and more functionality in the mobile system, so that you can have each and every aspect in your hand, and you can be always remain connected to your home, to your offices, to your vehicles, and to your services, which you are supposed to be in your hand always. And this has happened because of the shrinking technology of the semiconductor devices. And if I am talking about the IoT's Internet of the Things, then people are talking about the wearables, smart logistics, smart homes, smart cities, smart health, smart transport system, and smart energy system. All these is being supported by these kind of a device range: eNVM, non-volatile memories, advanced logic memories, RF-CMOS devices, MEMS devices, high voltage vehicles, and power management devices. And all these kind of a devices requires a kind of a change in the industry of semiconductor technology, where the industry really can grow just like anything to provide a kind of a solution. If we see in the last year provided the greasy after a start struggling growth of the previous 2 years, the main problem are the best understood in the context of the uncertainty caused by the US-China trade war. Then will mankind land up in the COVID scenario. And because of this COVID scenario itself, the US-China trade war itself rattling over capacity of the memory sector, which look luster like demand of the processors at the world data center and flattering smartphone sales increase just like anything. However, the industry suffers from kind of a advancement they would like to make the devices out of it. And then they come up with a solution of a kind of a artificial intelligence with the algorithm chips, which can be associated on these devices and can provide complete kind of a solution to the mankind. And however, the task has been performed till date in this direction for this. And of course, the really sensing things is the sensing devices, big data devices, and the application world everybody knows nowadays, where we are talking about the connectivity of homes, the wearables, the IoTs, and the smart meters. Everything is being governed by the semiconductor technology, and everything required a kind of a security of data to be communicated, data to be switched in terms of a fast information exchange. And of course, it has to be in a kind of a state where you can really rely on your component to give a viable solution to the industry. And if you see the kind of a growth in which we are landing up today with the home or on the home front, on the industrial front, on the connecting vehicle front, on the smart cities front, on the wearable infotainment front, health and fitness front, the volume of the device which is required exactly huge. And this is all, my dear friend, is supported by the semiconductor device technology. And the kind of a thrust or the force these demand on these device has been put is to make them more and more functional in a small unit space. They should be faster, they should be reliable, they should be less power hungry. This is only the demand. Apart from that, if I am talking about IoTs, definitely it has to be associated with the security features with this. Everybody knows how the US-China trade wars has begun because of the kind of a security issues associated with this device. Now, every country would like to design their own semiconductor chips, would like to fabricate their own semiconductor chips because of the breach of the contracts of the semiconductor information chips to be used for critical application in every domain, in the government sector, banking sector, industrial sector, where the information of the system can be really transferred to the another country, and you need not to even put your spies out there. Your spies are already in your laptop, tablet, and everybody is governing right nowadays. So that's why people are really, fed up with this kind of things, and we need to find out a solution where we can really adopt a kind of a strategy where we can secure our data, where we can implement all these kind of a features. Automotive products as well, another carrier of the IC technology, and everything has to be integrated with the kind of a device which is supposed to be required. The fleet of the vehicles, the collection, the key attribution, the transmission, the process, and the information, everything has to be worked in at tandem, and they have to make the secure. If we talk about the automatic packaging type of the requirements, that all the kind of vehicles, they are associated with the sensors, interconnecting devices, which are communicating with the different part of your vehicle. Nowadays, not to be surprised, when it is driverless car, it is to be communicated with the buildings, with the road, with the sign light, with the persons who are traveling or vehicle we are traveling on the roads. You might have heard a real news where the Chinese companies have really put the driverless vehicles on the road last month by the Uber industry with the intercity transfer. So there's no driver at all. What does this shows exactly? The technology can provide this kind of solution where a lot of information is being gathered, pursued by the vehicle while it is traveling at a very fast rate. At the same time, the information has to be analyzed, has to be fetched in a secure manner, and action has to be taken by the vehicle. You cannot rely that all the system, all the information can be transferred to the cloud, and from the cloud they analyze the data and transfer this data to the vehicle so that the vehicle can take it. This is not the way to provide a solution. So definitely we have to provide a kind of a communication system where the data can be transferred to the pole to pole, and the information can be gathered, and the processing can be done on the vehicle itself to take its own decisions. So this is how the things are being nowadays targeted. and being implemented. Myriad of the things of the data is particularly one, we are talking about the mobile automated system, cloud, big data computing, IoTs. If you even talk about the banking system nowadays, education system nowadays, your office industry data to be transferred from your home to your offices or vice versa, or to the client, to the server, or to the end user, they have to be transferred in a smart and secured manner with the kind of a decision making where nobody can access this data. So that was the only real problem when we are talking about to provide the solution out of the semiconductor technology or the nanotechnology, which we are adopting along with the IoT devices, which we are using. So now world is running on the data itself. Let me tell you clearly on this part. If world is running on the data, then what is the real problem nowadays if we talked about the world is running on the data and the kind of a solution exactly what it needs to be provided. So nowadays, if you see about the Internet of the Things, a broad term is being used, particularly on what kind of application the broad term is being used. The broad term is being used to device sensors and everyday items which are not ordinarily considered to be the computer, but have a internet connectivity and computing capability. That is what IoTs are being doing. These objects includes consumer goods. It could be having a consumer goods. It could be a car. It could be a truck. It could be an industrial component. It could be a healthcare monitor system. It could be a device working together to create a concept like a smart cities. Now what we are talking about, the smart cities, a lot of not like us in India, but of course, where the kind of a solution and security system and a kind of a facilities to be provided in within your house itself. The object particularly collect the data from their surrounding, which are then transmitted remotely particularly, and then analyzed and create a new insight in this and deliver the services and control to the other items. It is projected that there will be 100 billion of connected devices by 2025 where the data has to be transferred to and fro in a very fast manner and a secure manner without interfering the information which are being exchanged at the same cloud, at the same bandwidth, at the same rate. However, there remains a significant challenges associated with the IoTs, which must be addressed in order to the technology to reach its full potential. And these challenges include the issue of the security, privacy, okay, and the standards which are to be adopted by implementing these devices so that nobody can breach into and can steal, you can take your data and can misuse it. There has to be a regulatory authority which can take a right decisions and address the issues associated with the data theft and the readiness of the emerging economy and its adoption with it particularly. So if we are doing this kind of a application, definitely the kind of a solution which we are talking about, they can be really provided and can be implemented with the big data. So real problem, what it is associated with, sorry, the real problem associated with this is the kind of a data security system which is required nowadays. Many Internet of the Things are being designed to a background operations where a lot of data is being handled, as this figure is really showing the kind of a data which exactly is required to be handled by the devices when we are talking about the IoTs devices or the smart cities or the smart vehicles or AV systems. If this data is being handled, the device has to be very fast, the device has to be very smart, the device has to be secure enough so that nobody can tamper with your data and you only the person who can really access the data. So if you see where really we are landing up, let me give you the real figure. They are the IC makers, they are the tier 1 module where the module makers are working, then the vehicle makers are working. The IC makers are making the semiconductor devices which is much faster and smarter nowadays. Okay, if this is the case, they are the persons who are really dealing with the tier 1 module makers which can give you the complete system which really can work for this kind of application. And then the car OEM systems who will be end user of these components and device or systems or modules which can be incorporated in the vehicles, in the office system, everywhere. And then they can really use this based on the policies which has been devised by the government and the local agencies, where they can use this kind of a device and data. And of course, the semiconductor industry, the algorithm, the system, the service applications, which is being used for this kind of application remains a critical challenge to address all these kind of issues. Now, the technologies which are associated really make you helpful in making this device possible in the near future. Let me tell you one thing here. From any time, any place, the connectivity of the anyone, we will now have a connectivity for anything. So this is what the scenario is now in the present world. If you see about that, really defining the definition of the IoTs, there are several definitions. But initially, I would say that the Internet of the Things is also called the Internet of Object, refer to the wireless networking between the object. Usually network will be wireless and self-configured, such as household appliances. This was the earlier definition which we used to be about when IoTs come into the picture. But nowadays, what is the exactly IoTs is? I'm going to the number 4, where the latest definition of this is coming out. Things having identities and virtual personalities operating in smart space using intelligent interface to connect and communicate with the social environment and user context. Now, this is the IoTs where things are being really, working with the virtual environment, or we are talking about the systems which are virtually talking to each other, taking their decisions and providing you the solutions. And how we come onto this stage? Because of the Internet of Things. Earlier, if you say in 1990s, only 100 million, 100 this million devices are being used, and billions of the devices are being done, and this much of a devices are being used nowadays. With the Internet of the Things, particularly exactly, in 2022, that device, everybody now having the smartphone with the internet connectivity, they can really use and this kind of a system and technology for their own kind of applications, where they can really access each and every kind of information on your palm top. And this is because of every people in this country as well as abroad, they are having the information in their hand, and this is possible because of the semiconductor devices. Now the scenario of intelligent home, where you would like to have your automatic light system, speaker system, window shades, laptop, TVs and tablets, which is particularly being gone by the also semiconductor devices. Particularly, they are interconnected to each other, and they are talking to each other and taking action as per the requirement, as per the human mankind comfort. If you see in 2012, the kind of a devices are used are only with a currency load of around 571 million. But if in 2017 is almost around 2.6 billion dollar devices are being used nowadays. If you take about the scenario nowadays, scenario is being, if you are entering into the shopping mall, they are tagging your, identifying your tags on your shirts, then they are camera systems are locating you, and then take to the desired counter. You take the items, rate is written there, you tag swap the card, your card has been swapped, then you go out from that. And of course, at the same time, the digital system integration will tell the shop owner that this item has been taken from this area, and you can refill the cartridge. In this scenario also, the IoT is taking place and taking is working into action, where that information is being exchanged from product to the centralized server in the houses, in the shops, and the information about the consumer who is coming into the shop exactly. So this kind of information is being exchanged. And of course, if you like to adopt this kind of a technology for the healthcare monitoring in the country like India, then this can really give a big kind of solution. And everybody knows nowadays it can be used and it can be directly transferred. And this is possible because of the 2G, 3G, LTE forms network, telecloud, 5G, internet connectivity services. Because of this, nowadays we are landing into the kind of a scenario where we are really sitting at home and work our duties day by day. But things are, imagine a world with the connectivity, what we can achieve. Ask Google now, where is my keys? Google will tell you. Where is my kids? Google will tell you. But on the other side, if you'll ask, please avoid asking where is my spouse from the Google. So if you want to avoid problem at your home. So how to convincing user that are the IoT's technologies with the protecting of their data privacy when tracking this. The potential solution, particularly issues associated with implementing all these solutions with the technologies into the real world. the legal and regulatory issues, the technical control issues, the social ethics issues, and market self-regulation issues. These issues has to be addressed before implementing to make real digital world around us. We have to address all these issues, and there has to be a regulatory authority which is governing all these kind of issues and which can provide the solution to the mankind also. So the total challenge with this kind of a technology implementation remains that technology standardization is the most area are still remain a fragmented. Chips architecture, data storage, data connected material, silicon and compound semiconductor. I can provide the solution. Everybody can provide the solution. And we are shrinking towards that. And nowadays the technology is being providing a solution at 7 nanometer, then 5 nanometer, 2 nanometer. But of course their road is closed. Whether I'm smart enough to give the solution to the mankind with the increasing demand over it, yes. With the nanotechnology, we can provide the solution up to the 2 nanometer, 5 nanometer. If I really would like to increase the complexity and functionality on the system on a per unit area, definitely it should not go for the a two-dimensional solution. I can go to 2.5 dimensional solution. I can go to the 3-dimensional solution, and of course, while I am doing this kind of a solution, I have to also be very careful in providing privacy and security. In providing, in the absence of government, there has to be a law regulatory and vulnerability to the internet attack so that nobody, if they are connecting with together, can harm each and other with the kind of a data theft or the kind of a security which is required to provide the security to each and every person who is connecting with the systems exactly. So now AI in the emerging data economic data systems particularly is giving you the complete solution. And with the AI, artificial intelligence system needs to process the massive amount of data, while the performance of the general purpose chips has to improve sufficiently to a kickstart, a new generation AI technology need to be provided the complete solution out of it. And if it is really so, then I have to make a hardware system with the algorithm, with the architecture, which can give the security faster and in a smarter way. And that's how we can really work together and we can provide the solution to the mankind of the industry for this one. So with the emerging data technologies, with the innovations associated with this, with the big data handling security system, the all solutions is being provided by the semiconductor technology. And if this is the way, then the real core heart of this is the integrated circuit technology, where we have to make these devices smaller, complex, less complex, and low cost and very high reliability. And the core of this technology is the CMOS technology, complementary metal oxide semiconductor, which is silicon-based technology. Of course, there are the alternative sources also where we talked about the silicon and gallium arsenide technology. Silicon has two main frame out of there where the BJT and transistor MOSFET are being used. But the real structure of the CMOS as known to the many of the scientists and researchers around the globe is the planar technology, where we have a particular source and drain region being separated by a gate region. And the channel associated in between, I am shrinking the dimension, then the issue associated with the right performance of this transistor because of the short channel effect associated with the shorter gate lengths. If I am shrinking the dimension, I have to change the architecture also. In order to have a better control of the charge transfer, which is the core of the heart of the technology of any IC technology, then we have to change these dimensions also very well. So we turned into the FinFET kind of a structure. With the FinFET kind of a structure, with the ever shrinking technology, if you see in 1971, the process is having a dimension of around 10,000 nanometer. In 1974, the dimension are 6,000 nanometer. With the shrinking CMOS technology, at this level is the planar. And in 1976, it is around 3,000 nanometer technology. And if you see in 1982, it is around 1,500 nanometer. And if you see in 1995, it is around, say, 800 nanometer. And now where we are today not on even 16 nanometer in 2014, we are in 2020, where we are having the device 7 nanometer in our hand. And the structure of the device with the 7 nanometer is not even a single fin, it is a double FinFET, or the architecture also may change beyond that technology itself. Let us focus on the kind of a requirement which we have. This technology has to provide the solution to the market. The requirement is we have to add more and more functionality with low power consumption in a single unit area. And we have to reach where either it has to be with the advanced technology node, which has a limitation, how small device we can make, which we can make, or with the advanced packaging schemes. Anything can be adopted, or a hybrid solution also can be adopted, where along with the technology syncing to the optimum level, where the device speeds, maximum storage capacity can be enhanced with the 3D integration stacking, where the functionality of the system can be added either on the wafer level or on the chip level or on the packaging level with the heterogeneous kind of integration, where we can add a more and more functionality with the fast to provide a complete solution to the industry for providing this kind of a chips out of it. And if you see, particularly enabling technology for today's is the RFIDs, sensors, smart technologies, and nanotechnology associated in one to a complete system on a chip, which can really provide you the solution. And just a second, please. Hello. Jain bhai. Sir, I am on a meeting separately, so I will let you back. Okay, I will call you back. No, thank you. So sorry for that. The technological challenges associated with the roadmap, because which we are targeting to talk about, is particularly the dimension of the devices. And the dimension of the devices in the planar or in the FinFET. So as we are shrinking the device particularly, what we are doing, we are changing the architecture. And of course, when we are shrinking the technology, we are changing the material and shape or the structure of the device without compromising the current drivable capabilities of the transistor, which is a key performance matrix. Or what we can do, it is a Dinard scaling. Dinard scaling, I am shrinking down the dimension of the devices, but I am not compromising with the power densities per unit area. So by keeping all these, of course, at the simultaneously, I have to focus about on kind of a making the device less power hungry, much faster, more integrating more functionality in unit area. This is what we are targeting with the shrinking. So if I am targeting a future device by 2020 of the 3 nanometer, it is not a standard planar device anymore. It is not a single FinFET device anymore. It will be a particularly stacked gate all around technology device, which can overcome the short channel effects associated because of the shorter gate lengths, which can really make the device working and which can contribute to make the integrated circuit for the desired applications. And thus the nanowires and the FAT with the gate all around control come into the picture. But here with the gate all around technology, FAT might sustain the scaling up to 2025. But however, one need to take account of extreme engineering challenges, what beyond silicon and why we need to do that. If that is the kind of thing, I can shrink the technology up to with the implementation of the hardware or the adopting new materials into the process or incorporating the different architecture of the device, either FinFET architecture or double FinFET architecture or gate all around architecture in the CMOS devices. Or apart from that, making the device more shrinkable, more component complexity with the not standard integration capacity application, but however, defining the interconnecting power rails in the front end of the line of the process rather than on the back end of the line of the process. So if I can do that, I can go for a 2.5D integration of the device rather than the planar devices, or I can go for a 2.5D integration or 3D integration of the device. When I am adopting this, I can still reach to a technology where the device can be made faster. But if I'm shrinking the devices, then where I am playing with the parasitics with the RC delays. RC delays is if I'm talking about is the resistance and capacitance associated with the long running wire, which is the signal is fast changing out there. Their interchanging capacitance can raise to the lesser switching speed, giving me a bottleneck on that using the device while I am shrinking down the dimension. Of course, I have shrink down the dimension without compromising over the power density, but I am making the device slower, which is the other way around. So if I'm making the device slower, nobody will accept the device adopted. So I have to make a architecture in such a way that where the RC delays can be also be minimized. either adopting by the same metal technology or same routing technology between the different components to make a complete ICs, or making the DPR, making buried power rails in between on the front end of line of the process, and then interconnecting the device in the film form on the top of the line. Let me show you particularly 3 architectures which are being explored and which need to be addressed to provide a complete solution and nanoscale when I am shrinking the device dimension beyond 5 nanometers. Either the double FinFET devices, or a nanosheet architecture devices, or a fork sheet architecture device. Let me tell you here clearly, as in the very second slide, we have discussed about the heart of the technology, CMOS, complementary metal oxide semiconductors. So complementary metal oxide semiconductors is not a single N-type device, not a single P-type device, providing the complete solution while we are talking about the technology. To provide a complete solution, we have to have a NMOS and CMOS devices completely. So that devices making a complete logic either with the memory devices, then it has to give the complete solution out of it. So fork sheet architecture, if you really want to speak about, then particularly N-type devices and P-type devices on a different side, and then it has to be controlled with the fin in between. And if this is to be adopted, then we have to think about the buried power layer, which can really either go to the single level T or multi-level T transmissions. If it's a single level T and multi-level T transmission, definitely we have to find a solution defining the metal, which can really address the issues, either how many metal lines is supposed to be used when I am shrinking the device to make a complete architecture out of it. Either a buried power layer can be used with the fork sheet architecture, or with the nanosheet architecture, or with the complete FAT, CFAT, complementary FAT architecture. So if we are doing that, then the fork sheet architecture can really give you the provide a solution for further shrinking down rather than what thereafter. No solution. I cannot further shrink the device. Whether the technology nodes ends there, whether the technology nodes end there, no. If this is the kind of a device structure which is possible, making P device, making N device, interconnecting these devices in a kind of a configuration front end and back end of interconnect, making the RC delays addressed by either using the material copper, ruthenium, or molybdenum, or tin, or binary or ternary metal alloys, which can give you minimum RC delays, or still making the device which is particularly give the solution for the CMOS technology. Then what then thereafter? Whether the road ends there after 2 nanometer? No. Always listen to the market and change your gears. You may change your gears right from the for the substrate, beyond the substrate, and of course up to the silicon also. Now, if I would like to really still make the device more powerful, more rugged, and more application specific to integrate more and more functionality to the unit area, I can go for a 3D ICs technology where the integrating the different devices in a kind of a 3D structure where the functionality can be increased by redundance, interconnect delays, by exploiting the different process technologies, by mixed material systems, or by advanced optical device to be integrated so that the interconnectivity can be made faster, higher bandwidth can be provided with the microprocessors. Or you can go for a 2.5 or 3D kind of integration, which I call the heterogeneous integration of the devices, where the logic device, memory devices, as well as processor devices can be integrated with the bonding techniques interposer. If you see this kind of a technology, we can go for this kind of a 3D integration of the device with the tin interposers as a bonding technique with the pitch size of 700 nanometers with the TSV. If we can adopt this kind of a thing, then definitely it's going to be really exploiting the full scale of the shrinking of the technology while compromising the Dinard scaling and adding more and more complexity on a system on a chip to give a complete solution to the market. And in that case itself, I would say it's really going to be exploiting particularly the TSVs through silicon vias in a real sense, where the device on one platform can be really integrated onto the another platform. And this can also be think upon with the wafer level integration with the TSVs, where different structures can be fabricated on the different wafers, and then they can be integrated
Sir,
together.
it's a gentle
to give them more
reminder
and more
to please
functionality.
finish your talk.
So online help can be useful, but it is dangerous sometimes. So we have to learn and we have to find out the solutions for ourselves. Either changing the gears with the material, with the integration technology, with the architecture, with implementing algorithm with the architecture, or providing more and more power efficient devices. This is what is the requirement. So with this, because the time paucity, I have to stop. That's why I take you in a fast manner. A good lecture can inspire, can motivate you, can entertain you, can share the speaker's passion, can be an important educational tool, but is not the best way to convey knowledge, sustain student attention and motivation, develop basic skill, or development higher order skills. So with this, thank you.
Thank you, Manish, for really wonderful talk. And always listening you give us a new dimension in the semiconductor industry, and especially at the SCL Mohali is this leading this industry in India. I hope more and more this IC technology will be coming, and probably we are matching with this business, world business very soon, as the government of India is also giving the more focus on made in India. So
Yes,
your talk is really means from such kind of the lecture we are able to understand it, what the India is doing, how we are competing or we are about to compete with the world market. So really thankful for your really wonderful talk. And now session is open for the questions. Sumant.
Thank you so much, sir, for your very well talk, very well explained talk for the technology trends in the semiconductors. Now, I will ask the panelists if they have any questions to the speakers.
Yeah, thank you, Sumanta. Thank you, Dr. Huda. I mean, this is really, a journey you've explained. So, I would like to know, where do we lie? Where does India lie in this semiconductor technology comparison to the entire global records? What you've shown a lot of records here. How much do we produce? What things we especially import? And how do we export also something?
A very good question. So it's very hard to answer this actually. Let me tell you one thing: we are zero exporters in semiconductor technology. Very clearly, there's no vision of semiconductor technology to be established within the country itself. However, nowadays, government of India has initiated that with the Make in India initiative, they should set up some kind of a semiconductor technology industry within the country, which can provide the solution to the domestic market, and with the kind of a security issues associated with the using these kinds of chips at the area where we are using banking systems, defense systems, security systems, they have to really put this kind of a fab within the India itself. At India, we are only having one fab, as I told you, is semiconductor industry as 180 nanometer we are working with. 180 nanometer is around 15 generation behind where the world is now. So world exactly is working at the 5 nanometer technology. Production is in 7 nanometers, where the 5 nanometer is also in production by the Samsung. As the real challenge in there is the integration of the device technology, but that technology is required for a kind of a 5G integration and innovation with the Internet of the Things particularly.
But so
of
where
course,
do we lack? Actually, I mean, we have the brains. I know. I mean, but I mean, is it just because of the infrastructure we are lacking?
yeah, actually,
Some other
this is
reason.
nothing.
Infrastructure is main thing.
There is no ecosystem within the country itself. No ecosystem for manufacturing, no ecosystem to support these manufacturing houses. Let me tell you, setting up a micro fabrication facility or a wafer fabrication facility of a capacity of 10,000 wafer in India requires an investment of $2 billion US. And the investment of $2 billion US required another $1 billion US to sustain this investment, to make this industry in production future, where it can really generate the revenue out of it. So setting up a wafer fabrication facility required an initial $2 billion investment and additional $1 billion investment to run this facility, where it can start producing the product out of it. And the time scale required for this is minimum 5 years. And the kind of infrastructure required or ecosystem required for this, you have to have a high purity gas system, chemical systems, and other utilities required for supporting the fab houses particularly, which is not available within the country. There is no vision earlier with the governments to set up this kind of a semiconductor industry in the India. But with the last 2 or 3 years, I think government start thinking in that sense without setting up its own foundry within the country itself, which can really cater the market. It is not feasible to them, but they are looking toward the private partnership. Let me give you a very straight example to you. China model. There the government has put a lot of money. Taiwan model. Government had put almost around $300 billion to set up the industry and develop the ecosystem there. Then the China and Taiwan, they have come just like big giant in developing the semiconductor chips or component out of it. And now they are a world leader. TSMC is the world leader. Second part is the China. However, with the kind of a scenario with the COVID and Huawei war between US and China, China has been deprived of the kind of equipment setup to be supporting for this kind of technology. But however, presently, earlier US was the leader, then US came fabless, thinking of that it's a dirty business, so let it be to the Asian countries or somewhere. They can design, they can transfer their load their design. But with the existing scenario where the security system is the prime importance for any country, if they are using the chip from the outside fabs, definitely then they have turned out and they asked TSMC not to invest in China, but to invest in US. And now they are setting up the money. They are putting up 50 billion US dollar to set up a manufacturing facility in US. In India, government is reluctant to feed the money into the semiconductor industry. However, they are very keen to set up the fab within the country with the PPP, private partnership. If that is going to happen, definitely this scenario will change. But before that, Indian government has to take a step to develop an ecosystem within the country which can sustain this kind of a facility. Thank you.
Manish, recently we have gone through the one of the statement of the director IIT Delhi, V. Ram Gopal. Probably the committee has recommended to to establish the IC fabrication technique in India itself, or the technological this IC fabrication labs itself. You are in this field, so you know much better than me. But probably the committee has recommended to for the such kind of the establishment.
Yeah, Sinha sir, yes, Government of India has set up a high power committee almost. They are studying on setting up the kind of a technology fabrication facility within the country. But there is always dilemma. Who is going to put the money out there? Yeah. Setting up a fabrication facility is a different issue. You can spend $2 billion, but you have to have a allied infrastructure also. The supply chain of the chemical gases, high purity, purity of the gases and chemical required to run this fab. That has to come from the abroad. There has to be a model where I think this kind of a facility shall be first established within the country. Then you can talk about setting up the fab. Of course, they are very much keen in setting up the fab, and there have been proposals to Government of India by different institutes to set up this kind of a fabrication facility. But of course, there has to be a model. If we are setting up, what will be the timeline? Who is going to use the product out of it? And what kind of a technology node it is supposed to support? Of course, not a single node can provide all kind of a solution. And we are setting one fab of a single node, it can provide a certain products, not for whole portfolio of the product which we have talked about in this discussion. But for India, most prominent node to set up the fab is 45 nanometer nowadays. We cannot go to 7 nanometer or 10 nanometer. We don't have that kind of a technical expertise with us. And nobody will give you the technology so far.
With the time, we are still considering as a developing country. With the time, maybe in coming few years, you will find that the foreigner companies are coming and then they are establishing their center over here. Bangalore is becoming the hub.
Yeah, Sinha sir, you are right that way. If you could recall, in 2007, Government of India has started this initiative to set up the fab within the country itself. Then up to 2012, they just seeing, okay, either we should spend the money or the foreign company should come up with the model in that. Foreign company are reluctant to set up the facility in India because of they are not having the ecosystem here.
Lot of bureaucracy and other things are there. So
yes, sir, yes,
slowly
sir.
we are changing.
Of
so
course, we are
hope
changing right now. I think with this 2 or 3 fabs, which are right now in the proposal mode, if they come, definitely situation will change within the country.
and you
Definitely.
know that by investing around 400 crores, at least 2 centers have been established quite good. IIT Bombay and ISC Bangalore IUNAP facility. So
Sir, actually spending 400 crore is not sufficient enough. We have to go full-hearted this time. Full-hearted, you have to think about at least to spend $200 billion. At least 20,000 crore rupees, government of India, 20,000, 30,000. They need not to even create a wafer fab. They should also think about create the ecosystem also, sir.
Yeah,
So
but no, we are our population is so huge that the priority of the government are entirely different than those things. So anyway,
But
let's
see, if
be
you are
positive
thinking, there was a question, sir, that import of electronics. We
Yes.
are, our import bill of electronics is equivalent to crude oil import bill in
Yes.
2020. So we are importing the electronics from outside. If we are establishing a fab within the country itself, even 2 or 3 fabs, you can think the change, how things can be changed. Yes. Thank you, sir.
Yeah, let's hope for the better in
Yeah, of
coming
course, sir,
as
of
we
course.
are changing. The change is the policy, means the change is necessity of the development. So we are changing, and hopefully in coming years you will find that we are matching with the world leaders. So
Sure,
keep the
sir,
hope
sure.
in that leader. So
Yeah,
any
of course,
questions,
yeah.
Sumant?
Yes, we have, sir, a couple of questions from the speaker. The first question is, why silicon in bulk form is indirect bandgap semiconductor and becomes direct bandgap in nano form?
This is a question which is very, tricky. Of course, silicon as a substrate is a indirect band gap. When you are dealing with the atomic level, nano level itself, you can manipulate the energy band somewhat by interfacing with the interface layers between the epitaxial growth process, where mono layers of the epitaxial growth can be managed to make this very particular direct band gap, particularly up to certain level. But really, if you would like to go for growth more and more layers over it, it cannot be possible because of the nature of the interaction of the bond, outer 4 silicon bonds, which are interacting with the more silicon bonds. That's what that is.
So the next question is by Chinmay Shukla. Sir, can you tell how the devices are dealt with tunneling and electron conductance, which are sensitive to the slightest environment or parameter changes?
Of course, that's what we are talking about the architecture when we are shrinking the device itself. The main problem associated when I am closing the source and drain together, the channel length is reducing drastically. The channel length is reducing drastically, and it can lead to the tunneling of the carriers from source to drain, which is not required. Even at the off stage, device will be on. In order to avoid that, you have to make the mobility possible and controlled by the gate only. You have to mitigate the short channel effect either by mobility enhancement by the stressors, or by changing the architecture of device, making the fins in it 1 fin, 2 fin, or 3 fins, or doping the channel itself with the 3-5 materials within the channel itself, so that conductivity can be happened because of the gate controlled voltage only. It should not happen by any tunneling or any kind of other stuff.
Okay, sir, thank you. The next question is, sir, could you please talk about the life of these devices, how to improve it?
Yeah, the reliability is very important of making the device, and if any semiconductor products to be launched into market, the device is fully tested within the domain itself. Let me tell you the real, if you are using a commercial device, the life of a commercial device integrated circuit is particularly 10 to 15 years, even more than that. If you are talking about if the device is supposed to be used in the industry environment or a harsh environment, then it has to be tested and packaging in a certain way, and its reliability has to be tested up to 6 sigma, where the device will not fail even up to 15 years or so, despite it has been exposed to the high temperatures, high radiations, either in the in the reactor systems or high temperature systems where industry is using this kind of a component, or in the space environment. So that's what you can define the lifetime of the device based on the testing. And during the fabrication itself, either there's the three classes of the devices: for the commercial domain, for the specific application domain, and then for the space application or a defense application. And based on that, the process technology and the device design has been designed in that way, and the process technology has been processed in that sense to qualify all those parameters for which you are making the device. And of course, the packaging associated with this plays a vital role in defining the lifetime and reliability of the device for the kind of application where you would like to use these devices. Yeah.
Okay, sir. Thank you. Because of the time constraint, I'll take one more question.
Yeah.
The question is, sir, as 5G technology depends on millimeter waves for telecommunication with point-to-point nodes, how can Internet of Things be effective in terms of this heterogeneous CMOS and NMOS technology with respect to heat dissipation across these enhanced technological devices?
Sumant, who is the person who has asked this question? Can you tell me the name?
Deepak Kumar Sharma.
Deepak, really very good question. I appreciate that you asked this particularly. Let me tell you, the 5G technology is not based on the silicon technology only. It is a combination of GaN HAMT technology as well as the silicon technology. Because this is acting, as you rightly mentioned, shortwave. If you could recall during the talk itself, I am talking about pole-to-pole communication. Pole-to-pole communication, shortwave. You have the light pole in your cities. On the light pole, you can install your transmitter and receivers, which can communicate from one pole to another pole. The vehicle which is traveling particularly in that direction is communicating with the poles and the device associated with this and transferring the data from one area to another area. And same the way analyzing by the vehicle system or by the system who is using the data to be separated by this. Though all this technology, which is particularly if you want to take the faster switching speed or handling the data particularly, is the GaN technology is the workhorse for that, which is high electron mobility transistors particularly. And the backend for the processing analysis is the CMOS technology, which is NMOS and PMOS technology simultaneously. The 5G technology, because that kind of a data is being transferred with the speed with the high electron mobility transistor very fast. So your backend devices, which is the CMOS technology, has to be also faster and smarter to process this kind of a data, handle this kind of a data in the real time, and associated action can be taken by that. That's why the technology, where really 5G is playing a role at the shorter wave, the RF devices has to be at a technology node at the best of 10 nanometer. I cannot use a device of 28 nanometer with the 5G technology. So IoTs and 5G technology is the game of GaN technology associated with the 7 nanometer or 5 nanometer CMOS technology together. And with the pole-to-pole communication, this what you talked about, the shortwave communication devices is handled that.
That's why the device compatibility is very, very important when you are going to play with the 5G. You
Yes,
need
sir,
to
certainly.
change a lot of things.
Yes, sir, Sinha sir, bilkul.
Okay, so let us thank Dr. Manish Huda for this wonderful talk. He explained a lot about recent trends in semiconductor technology, the state of our technologies. Thank you so much, sir. Thank you for joining and enlightening us.
Thanks for giving me opportunity to share my thoughts with you. Thanks a lot.
Thank you, Dr. Huda.
Thank you, sir. Jain, sir.
Thank you, Dr. Huda.
Thank you, ma'am. Thank you.
Over to Dr. Sharu Naik.
I think let us hear from Dr. Robin Kumar. Dr. Robin Kumar, would you like to summarize today's morning session's talk?
Yes, good evening to all. Thanks for the opportunity to summarize the morning session. Today was a day filled with excellent talks by eminent speakers. In the morning session, we had 3 lectures, one by Professor Ajit Mahapatra, followed by Professor Ashish Kumar Singh and Professor D.S. Mehta. And there were approximately 203 attendees apart from the panelists. So in the first talk was on the utilization of nanotechnology in nanoelectronic, biosensor and thermoelectronics by Professor Mahapatra. In this talk, the emphasis was on the use of nanomaterials like graphene, quantum dots, nanowires, CNTs for nanoelectronic devices, nanosensors for biotechnology. He explained the approaches to realize nano devices, nanomaterials, electron transport through nanomaterials, and how the resistance changes when we go from 3D to 2D structures. Oxidization of graphene oxide for triglyceride and thermoelectric properties of calcium cobalt oxide were also discussed in length. He elaborated the angle deposition technique for contact formation to study the electrical properties of the nanowires along with the Peltier effect of aluminum nanowires. So the takeaway message from that he explained the different properties and different applications of nanomaterials, and he explained beautifully this angle deposition technique, which is very important technique for the study of nano materials and nano wires such as multi-wall nanowires or nanotubes. And the second talk was Dr. Ashish Kumar Sen on microfluidic-based lab-on-chip devices. It involved the basic application and energy sources, mixing processes used for the microfluidic devices. He discussed the component of microfluidic devices and lab-on-chip, and he shared a very important work from his lab that was blood plasma separation and measurement of gasotransmitter in blood for sepsis diagnosis. And this was basically done by acoustic energy, which was very interesting technique. Further, he shared the way how one can measure the S2S and S2O2 in the blood. Then the third talk was brought by Dr. D.S. Mehta, and it was on optical nanoscopy, a super resolution imaging technique for nano-size objects and living cells, wherein he explained various optical imaging instruments and the principle involved and the diffraction limitation in the resolution. Further, he explained the optical nanoscopy like STED, SIM, STROM, DSTROM, and he also gives stress on the application of label-free nanoscopy, biophotonics, green photonics, and high efficiency solar tower array based on the photovoltaic systems. And all these three talks were well suited, and they were meant for the enhancement of knowledge of faculty and the students. So this was about the first session. Thank you.
Thank you, Dr. Robin Kumar. Now, Dr. Sumant, would you like to summarize the entire afternoon session?
Yes, thank you, madam. On behalf of the organizing committee and panelists, I take this opportunity to summarize the second technical session of the day 3 of this Nano Era workshop. This session marked an important milestone in finding out the various ways of using nanostructured materials in energy conversion and storage, deep understanding and state of art of nanomaterials for emerging technologies, and recent technology trends in semiconductors. So there were 3 talks in this technical session. The first talk was delivered by Dr. Sasank Deka from University of Delhi, and he spoke mainly with the use of nanostructured materials in energy conversion and storage application. Dr. Sasank explained the sustainable development goals and emphasized the importance of clean energy systems. He explained that the fossil fuels, which means most of the world's energy demand, today they are depleting very fast, and also their combustion products, they are causing great danger to our environment and eventually on the life on our planet. And the current energy system needs to be replaced by the hydrogen energy systems, which is a clean, sustainable energy system. He also explained the mechanism of artificial photosynthesis with the use of nanostructured materials for hydrogen generation using water splitting reactions. He further explained the National Hydrogen Energy Roadmap of Government of India, and further he explained the flexible high performance supercapacitor cell based on nanostructured copper cobalt layered double hydroxide as a power source electrode material for the first time, where the copper cobalt layer double hydroxide hollow nano polyhedrons, they are developed by tuning the copper cobalt ratio in the hydroxide layers, host layers, and the emerging metal free carbon nitride, they offers prominent possibilities for realizing the highly efficient hydrogen evolution reactions. Further, he explained that its poor surface conductivity and insufficient catalytic sites can hinder its performance. So he demonstrated that a dimensional vermicular rope-like graphitic carbon nitride structures that consist of multi-channel tubular pores with high nitrogen content, and which he explained, which is fabricated through a cost-effective approach, having the final stoichiometry with more nitrogen content for hydrogen evolution reaction. The second talk was delivered by Dr. Bipin Kumar Gupta from National Physical Laboratory, New Delhi. And he started his talk by discussing about the bioluminescent security ink and LPCVD setup that have been developed by his research group at NPL indigenously. He explained the role and mechanism of band gap reduction in case of nanomaterials and other quantum confinement effects. He further discussed the different methods of synthesis of nanomaterials, including gas phase, liquid phase, sonochemical methods, etc. He further emphasized and discussed the role of two-dimensional nanomaterials in device fabrication and in other various applications. He explained the studies related to bilayer graphene and its characterization and role in device application. Dr. Gupta finished his talk by comparing the application of gallium arsenide and single layer graphene for quantum Hall resistance. And at the end, he showed the indigenously developed CVD setup based on single layer graphene and other 2D materials like MOSC2, tungsten diselenide, etc. The third and the last talk of the second technical session was delivered by Dr. Manish Huda from Semiconductor Research Lab, Mohali. Dr. Huda, who is actively working on micro electromechanical systems at SCL Mohali, gave a basic idea about MEMS technology. He started with the explanation of basic physical concept behind such devices and their potential applications by varying from mobile to medical to space applications. The fabrication process and characterization techniques were explained during his presentation. He further demonstrated various fabrication facilities available at SCL Mohali. Dr. Huda explained the use of micro and nanotechnology in defense sector also. He further explained the operating principles of various types of field effect transistors such as MOSFET, CMOS, ME, MESFET, etc. The importance of selection of materials for the fabrication of such devices was also highlighted. The fabrication procedures steps were explained, showing the images of state-of-art fabrication tools, the electrical characteristics of transistors for various applications, including switching, power amplification. They were also discussed during this talk. Dr. Huda's talk focused on the importance and ubiquitousness of electronic circuits and the chips that they have developed in the SCL Mohali. He made everyone aware about the application of microelectronics in biomedical, agriculture, consumer goods, and industry applications. Further, he also motivated students to align their minds towards the applied research so as to make India self-dependent in the technology. Thank you, madam. Over to you.
Thank you, Dr. Sumant Upadhyay. I mean, that's such an extensive summarization. I think somebody, if has missed the talks, they could have understood. Thank you so much. And special thanks to the entire team today who handled Dr. Robin Kumar, Dr. Sumant Upadhyay, Pooja Bhattacharya, and Rohit Sharma. Thank you all for a well-handled session. Entire day was well-handled. I must congratulate you. So the link for today's assessment has already been floated, and I already see 100 participants have already attempted. And yesterday also, it was good. The results were 85% people could attempt it correctly. So I'm so happy to see that we all are learning from this workshop. And for tomorrow, I've again floated the link of our website, just like yesterday. So you all can visit our website to look into the tomorrow's program schedule. It's there in the announcement section, and do visit the other parts, other sections of our website also. I'm sure it'll be of interest to you. And so see you all tomorrow at 10 a.m. We have 7 talks in the pipeline tomorrow. Very interesting talks. I'm sure everybody is going to like it. And so thank you all for this wonderful day with a lot of learnings. So have a good evening. Stay comfortable and enjoy your evening. Have a good night. Thank you so much.